Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I predominantly teach game development courses, but I also teach some computer science courses as well. I'm also the program director for our Bachelor of Innovation in Game Design and Development. I have 5.5 years of indie game development experience in a company I formed with my two sons, and now I have a one-man game development shop called Burning Teddy. This is a 4-week course, and in the first 3 weeks you'll have a programming assignment to complete, so each of those is worth 25% of your grade, totaling up to 75% total for the programming assignments. You'll also have a final exam to complete in the last week of the course, and that's worth 25% of your grade. I've provided lots of exercises for you to do, and although those exercises are not worth points, they're really valuable as you engage with the course material. The course will cover abstraction, which is all about deciding which details matter and which details don't as you develop your code. And then we'll look at the design and implementation of console app classes. We'll move on to taking a closer look at functions so we can understand even better how functions work, in particular how parameters work. We'll cover the design and implementation of Unreal Engine classes, and we'll cover strings both in C++ and in your Unreal games. We'll then move on to pointers, which I've been telling you throughout the previous courses in the specialization that we'll finally get to eventually. Well, it's eventually, and we'll get to those in the last week of the course. And finally, I'll teach you how you can play sound effects in your Unreal games. This course builds on the previous 2 courses in the specialization, so you should think of that previous material as prerequisite knowledge for doing the material in this course. If you don't have that prerequisite knowledge, you should go back and take those courses or learn that material somewhere else before you try to succeed in this course. As always, the forums for the course are available if you need help, and you can also search the internet to try to find answers to problems that you may run into as you engage with the material. I hope you have a great time in the course, so let's get to work. What will you learn about in this lesson? You'll learn what abstraction is, and people talk about abstraction in 2 different ways. They talk about abstraction, the process, which is the process of deciding which details matter as we try to solve a particular problem. And they talk about abstraction, the thing, the representation of the results of the abstraction process. And lots of people call an abstraction a model. That sounds pretty vague, I know. So over the course of the next few lectures, we'll actually get some practice so we can understand how abstraction works. Speaking of the next few lectures, we'll learn how abstraction helps us solve real-world problems, and we'll also learn how abstraction helps us solve programming problems. Recall from the previous lecture that abstraction is all about determining which details matter and which details don't when we're trying to solve a particular problem. In this lecture, we will get practice with abstraction by solving a problem. So, what's our problem? Our problem is that we want to implement a reservation system for a concert venue. That's where rock and roll comes from. And for this lecture, we will focus on the abstraction for a seat in that particular venue. What you should do at this point is you should pause the video and think about what details matter about a seat in that particular venue and what details don't for our reservation system. When you're ready, unpause the video and we'll talk about some of those details. Some of the details that do matter for a reservation system are the location of the seat, and that includes both the row you're in, which is often correlated with how far away from the stage you are, and the location in the row. So you may have a row that's further away, but you are more centered on the stage, so you prefer that instead. Certainly our reservation system will have to keep that information so that someone who's considering buying a ticket will be able to know where their seat will be in relation to the stage and use their own judgment to decide which pieces of location are more important to them. Another thing that matters to at least some people is the price of the seat. So we will have to keep track of in our reservation system how much it costs to sit in each seat for that particular concert. Because of course, better seats are more expensive, and so we need our reservation system to keep track of that information. Details that don't matter include how old the seat is, what color the seat is, what fabric the seat is, what materials the seat is made of, and all kinds of other stuff. They may be important to the designer of the concert venue. They may care about colors and so on, but somebody who's buying a seat for a particular concert probably doesn't care. To recap, in this lecture, we got some practice doing abstraction to determine what details matter and what details don't to solve a particular problem. In the previous lecture, we got practice with abstraction as we tried to figure out which details matter for a seat in a concert venue. This time, we will do a number of abstractions for a particular object, and we will see that the details that we decide matter are based on the problem we're trying to solve. So the big idea behind this lecture is that the details in our abstraction are directly related to the problem we're trying to solve. That means that there's no core truth about what the abstraction should be for a particular thing that we're trying to model. Remember, model is another word for the abstraction, the thing. And our example for this lecture will be a chair. Let's say our problem is that we want a chair to sit on. The details that matter for us, in this case, are structural integrity. We want to make sure that the chair won't break when we sit on it. And stability. We want a chair with two legs isn't very stable, so we want to make sure that whatever our chair is has appropriate stability. And those are the two details that matter if, in fact, we just want a chair to sit on. Let's say we want a chair that we're going to buy for our living room. So the details, of course, we still want structural integrity and stability, so if we're going to use the chair in our living room, but we also care about other things. We care about the style of the chair to make sure it matches the style of the rest of the furniture in our living room. At least my wife tells me that's an important thing. We care about the color to make sure we don't have clashing colors. We care about the fabric to make sure that it matches in some way or is a reasonable fabric or will wear well or something like that as people sit in it. And we probably care about cost. When I buy furniture, cost is an important consideration, so we probably care about that as well. So these details are different for purchasing a chair as furniture for the living room compared to just any old chair I can sit on. A third example is, what if we want to buy a chair as an investment? The details that matter in this case include the rarity of the chair, because chairs that are commonly available are not as good as investments as rare chairs. The condition of the chair, because chairs that are in good condition will be better in the long term as an investment compared to chairs that have been beaten up along the way. And cost, again. So if we spend a lot of money on a chair as an investment, it will take more growth in the value of the chair to increase our profit, rather than if we get a good deal on it. From an investment perspective, it's better to, here's a clue for you, buy low and sell high. That applies for chairs as well. So we do have cost here, and we had cost for the living room chair as well. And so we can have the same details in different abstractions, but the set of details as a whole is generally going to be different based on the problem we're trying to solve. To recap, in this lecture, we saw 3 different examples of doing an abstraction for a chair, and the details were different for each problem we're trying to solve. And to remind you, there is no core truth about a chair. There is no, this is the abstraction you should always use for a chair. The abstraction we use, the details that matter, depend always on the problem we're trying to solve. Last time, we learned that the abstraction we select is directly related to the problem we're trying to solve. In this lecture, we'll see how abstraction can help us in another way to focus on the details that matter. The example for this lecture is networks, and the problem is networks are incredibly complex, and we try to interact with networks in a variety of different ways. So different details matter depending on how we're trying to interact with the network. The solution to this problem is to model the network with different layers, typically 7 layers, and each of those layers contains different details based on the way people are trying to interact with that layer of the network. In essence, each of those layers in the network is an abstraction of the network. Let's go take a look at that 7-layer model of a network. As you can see, layer 1 is the lowest level of detail, so this is the physical layer. This is actually the physical medium, the wires that the bits are traveling across, how do we actually represent those bits, and so on. If we move up 1 layer to layer 2, we're looking at the data link layer, where we actually can do some error detection, where we can catch the fact that different packets have been corrupted in some way. We move up to layer 3, where we start worrying about how are we addressing these packets to make sure that they go to the right place. In other words, how should we route these packets through the network to get to their appropriate destination? And how do we flip the switches in the network to redirect packets different ways based on failures of particular nodes in the network and so on? The transport layer is the final layer contained in the transport service section. The bottom 4 layers are considered the transport service section. Layer 5 is the session layer, where we consider things like authentication, the user's identity as part of an internet session, if you will. In the presentation layer, layer 6, we think about encryption and compression and so on. And in layer 7, the application layer, we consider how do we actually display things appropriately so humans can actually interface with what's being provided to them. To recap, in this lecture we saw how we can take a very complex system like a network and build separate layers that contain different details based on how people would interact with that particular layer of the network, and each of those layers is really an abstraction in and of itself. In this lecture, we'll explore how abstraction helps us when we code. The big idea is that every detail that we decide to include in our code costs us time and money when we develop and maintain that code, costs us additional memory space, and can in fact cost us additional CPU cycles for processing as well. Abstraction helps us minimize those costs by letting us focus on only the important details and ignore the unimportant details. The implementation mechanism for abstraction in object-oriented languages like C++ is classes. For example, let's say we decide to store a location or a velocity in a vector2 object, where we've decided that the important details are x and y components of that vector. For the purposes of discussion, this is a good abstraction for 2-dimensional work, but it's a bad abstraction for 3D work because we're missing the z component of the vector. For another example, let's say we were going to store student data in a student object, and we've decided that the important details are the student number, the student course percentage, and the student's letter grade. For the purposes of discussion, this is a good abstraction if we're going to be assigning grades to students and being able to query those grades and so on, but it's not a good abstraction if we're going to want to calculate the average age of our students or explore gender issues or other things. As our final example, let's say we've decided to store our location using GPS coordinates, but the details that we've decided to include are latitude and longitude. For the purposes of discussion, this is a good abstraction if we want to know where we are or to support dynamic driving instructions, in 100 feet turn left. But it's a poor abstraction if we're trying to actually calculate altitude gain on a hike that we've gone on. So as a reminder, abstractions are not a core truth about a particular thing like location. They're suited to a particular problem that we're trying to solve. To recap, we've seen that using abstraction when we code can help us minimize the costs, development, maintenance, memory, CPU cycle costs by letting us focus on and only include in our code important details. One of the things we haven't even discussed is abstraction also helps the readability or understandability of our code because we haven't included extra stuff that we don't actually need to solve the problem we're trying to solve with our code. In object-oriented programming languages like C++, abstraction is implemented using classes and objects. What will you learn in this lesson? You'll learn how to design a console app class. You'll learn how to implement fields and getters. You'll learn how to implement constructors. You'll learn how to implement functions. And you'll learn how to implement a destructor. In this lecture, we'll design a console app class. Remember from our discussion of classes and objects in the first course in the specialization, every object has three things. It has state, behavior, and identity. The state is the characteristics of the object. The behavior is what we can tell the object to do or tell the object to do to itself. And the identity is so that we can distinguish from one object to another. And in practice, we get identity through the memory address of the object. We're going to design a die class. So the state, the characteristics of the object that we'll hold, will be the number of sides of the die and which side of the die is currently on top. We'll hold that information in fields, but we'll make that state information accessible to consumers of the class through getters. Now, that makes sense, right? You should be able to get how many sides the die has, and you should be able to get what the top side of the die is. It doesn't make sense in this particular case to provide setters for those pieces of state. Once we've created a die, changing the number of sides of the die, remember we're typically modeling physical entities. If you pick up a regular die and you try to change the number of sides with a file or something, that's generally considered cheating. So we're not going to let consumers of the class change the number of sides of the die once a die has been created or manufactured. We're also not going to let them change the side that's currently facing up. That's also typically considered cheating. If you don't believe me, you should go to Las Vegas and go to the craps table and roll the dice, and if you don't like what you got, reach over onto the table and change the sides that are facing up. That will be an important life experience for you. So sometimes we provide setters to be able to change the state of an object. Often our functions, our behavior will change the state of the object, but in the die class example, we're not going to provide any setters. For the behavior of the die, we'll let a consumer of the class roll the die. That's a typical use case for a die. So we'll let the consumer of the class roll the die, and we'll implement that in a function. For identity, we'll get identity when we create a new die object, which, remember, is called instantiation. This is a conceptual die, so in the innards, in that inner circle, we have our fields, the number of sides, and the top side of the die, but that's not what we expose to consumers of the class. The outer ring is what we expose to the consumers of the class, so we'll let the consumer get the number of sides and get the top side. Remember, no setters, just getters for this particular abstraction, this particular class. And we'll let them call a roll function as well to roll the die. This is a more traditional notation to use in object-oriented programming. This is called a UML diagram, or Unified Modeling Language diagram. As you can see, we have the fields specified with their names and data types, and we have the list of functions. I know it says methods here because I generated this with Visual Studio, which uses methods rather than functions as the terminology for functions in C++ programs. You'll also hear other people calling the functions in C++ programs methods as well, but you should just think of methods and functions as the same thing. To recap, in this lecture we designed a die class, and remember, this is one abstraction of a die. For other uses of a die, we might have a different abstraction, but for a typical die where we create the die with a certain number of sides and we roll it so that we can look at the top side to do something, this is a good abstraction of a die. In this lecture, we'll implement the fields and getters of our die class. Here's the UML diagram, and I've indicated what we're working on in this lecture with those orange boxes in the diagram. So let's go get to work. I've created a new project called the die development, but we're going to need to add the header file and the implementation file for our die class. So in Visual Studio, we do that over here in the Solution Explorer. We right-click the project name, die development, and we say add class. And over here, I'm going to call our class die. And while we could change the name of our header file and the name of our implementation file, I'm going to leave those as the default names. Sorry about that jerkiness. And click OK. And as you can see, Visual Studio has added both those files, the die.h file and the header files folder, which is called a filter in Visual Studio, and the implementation file, the .cpp file, there in the source files folder. So I've been calling the CPP files implementation files throughout the courses in the specialization, and that's a valid name for them, but you'll also hear them referred to as source files, so that's why the CPP files are put into the source files folder in Visual Studio. Visual Studio also opens up our header file, and I'll just copy the copyright notice in there and space things out a little bit, and I'll add a comment above the class just saying this is a die. What we're going to do is we're going to put our fields, which are also commonly called member variables, here in the header file, and we're also going to put our function prototypes or function declarations in our header file as well. Then we'll move over to our implementation file. We won't have to do anything about the fields in the implementation file because they're declared over here in the header file, but we will implement the full functions that we've declared over here. So we'll start by declaring our fields. Now it turns out that because information hiding is a best practice in object-oriented programming, that our fields would be private by default if we don't mark them in any way, but we should just be explicit and say that our fields are private. The way we do that is we provide what's called an access specifier. So this specifies who can access what follows this private colon. And we only want our implementation file for this class to be able to access our fields, because that's good information hiding. So we said we're going to have two fields. We're going to have num sides and we're going to have top side, as you should recall from our class diagram. Now we could initialize these variables to values, but we're not going to bother doing that because in the next lecture we're going to write the constructor that will in fact initialize these variables. So we won't bother doing it here. We'll let the constructor do that work, but that will happen in the next lecture, not in this one. We also said we'd implement the getters for the die class, and we want those getters to be visible and available for access to consumers of this class. In this particular project, that's going to be the main function in the die development CPP file or implementation file. But in general, we want to make our getters public so that consumers of the class can access them. The way we do that is lower down, and the order in which we do this doesn't matter, but I tend to put my fields or member variables first. But lower down, we can add another access specifier that says the stuff that follows this is going to be public. And we can put lots of these into our header files. You may not have noticed this in the earlier courses when we were dealing with the Unreal games, but the header files for the Unreal games, we've got private and public and protected, which we'll learn about when we talk about inheritance, and then other publics and so on. We can sprinkle these different access specifiers liberally throughout our header file. Okay. Let's write our first getter. The first getter in our UML diagram or our class diagram is get num sides. So the way we do this is we're declaring a function called get num sides. We're saying it doesn't have any parameters because there's no information that somebody who's calling this function needs to provide to us for us to be able to tell them, here's how many sides the die has. We've already stored that. Once we write our constructor, we've already stored that in our num sides field, so they don't have to pass anything into us as an argument when they call the function. The other thing we put is what data type we return from the function, and we're going to return an int because the number of sides for our die is an int. And finally, we end with a semicolon. I'm going to add some documentation here. Gets the number of sides. And I'm also going to fill this in number of sides. We do something very similar for our other getter, get top side. And again, I'll add a comment. Gets the side that's on top. And that's it for our header file for this lecture. So let's go over to the implementation file. Knowing that the implementation file is going to implement these two functions, getters are in fact functions, we will copy this code over into our implementation file. I'll copy it first, and then I'll add our copyright notice. But we need to change these functions to be the full implementation of the function, not just the declaration of the function like we put in the header file, but we actually need the code that does this stuff. Before we do that, one of the things that we have to do over here in the implementation file is we need to say which class these functions belong to. C++ actually lets us just put any functions in any implementation file, but we need to connect these functions to the die class. And we do that by putting the class name and colon. And this is something that I've got to confess I periodically forget to do, but we need to do it because these are functions within the die class. I'm getting red squigglies because I need to put my curly braces for the body of the functions. And now I need to actually implement the functions. So the getNumSides function is supposed to return the number of sides for the die. And we've stored that in our numSides field. Even though our numSides field is private, it is available to any functions that belong to the class. It's private to the class. So consumers of the class can't see it, but functions of the class can see it. And that's because of encapsulation, because we've encapsulated both the data and the operations on the data for the class all in one class. So of course we need to let our functions operate on the data of the class. That's what encapsulation is all about in object-oriented programming. So this is straightforward. I know what the numSides is. It's in numSides. I just need to know that I use the return keyword to return something from this function. And what I'm going to return is the value of numSides. I'll do something very similar down here. I'll return the value of my topside field. And I can compile now, and everything will compile fine. I do want to comment for people who are using Xcode. When you go to add a class in Xcode, you'll get a checkbox that says, do you want me to add a header file as well? Don't check that box. It's checked by default, so uncheck it. If you leave it checked, Xcode will generate a header file for you, but it will have the .hpp file extension, not the .h file extension. And if you want your code to be consistent with what you're seeing in all the videos and so on, you should say, don't generate a header file for me, but then you can add a new file that's a header file, and that file will have the .h file extension, so the rest of your code will look more like what we have here. For example, you'll notice I have a #include die.h here in Visual Studio because it generated a .h file. In Xcode, if you tell it to generate the header file for you, this will be #include die.hpp. Perhaps the most important problem with that is when you submit programming assignments, your code won't compile because the autograder assumes header files have .h file extensions, not .hpp file extensions. So if you're using Xcode, you have to use .h file extensions. Okay, so we've implemented our fields and our getters, but we can't test them until we have a constructor so we can actually create a die object. So testing these things will have to wait until the next lecture. To recap, In this lecture, we implemented the fields and getters of our die class, and we also learned how to use access specifiers to control the visibility of our fields and functions, remembering that getters are, in fact, functions. In this lecture, we'll implement the constructor for a standard 6-sided die. And don't worry, for those of you who want a D20, we'll implement a more general constructor in the next lecture. Here on the UML diagram, I've put an orange box around the constructor we're implementing, so let's go do that now. I've added a comment to our main function saying we're going to test the constructor and the getters that we've written, though we haven't written a constructor yet. Let me show you that we in fact get a default no parameter constructor if we didn't declare any constructors for our class. So I'll start by declaring a variable of type die because the classes that we define are data types just like all the other data types we've seen. Here we're developing what are called user-defined data types. So I'll call this test die 6 because it will have 6 sides, and I'll even say I'm calling it with no parameters. Now, I'm getting red squigglies under die, and you should be able to guess that the problem is that I have not pound included the header file that declares all of the characteristics of our die class. So we need to pound include die.h to make sure that die is visible to us. And it might take a moment or two for Visual Studio to catch up to us, and that's okay. So I do want to output the results of the getters even though we haven't written our constructor yet. So I'll add that code and we'll come back. Okay, I've added the code here to call the getter and output it for both the get numsides getter and the get topside getter. So when I run the code, I have 0 for numsides and topside. So those won't be what I have after I actually implement a no parameter constructor, but that's what I get when I do it with the default constructor. Okay, let's actually add the no parameter constructor for the die class. We'll start in the header file, and it will be public, and you can put your functions in any order you want. I typically put my constructors first. So a constructor has exactly the same name as the class, and it doesn't have a return value. So this will be my no parameter constructor. And I will document that this is actually a constructor for a 6-sided die. Because normal people, not necessarily game developers or gamers, but normal people think of a standard die as having 6 sides. So that's what we're going to use as our easiest to use constructor for the die class. I'm copying into the implementation file. And I'll have to clean up some spacing. And of course, I need to implement the body of the constructor as well. And what I want in the body of the constructor is I want to set the values of the numsides field and the topside field. So numsides is easy. We'll set it to 6. And of course, all these red squigglies are telling me that I need to prepend the class name and colon to the constructor to tell the compiler that this function, a constructor is a special kind of function, that this function is also part of the die class. I told you I sometimes forget, and there you go. I forgot already. So num size is equal to 6. What should we set top side equal to? I'll just set it to 1. I don't really care. The die has not been rolled yet. I've just placed it down on the table, this brand new die object that has 6 sides. I just put it down on the table. So we'll just leave the top side as anything we want, and I'm going to make it 1. Now, when we run our code, you'll see that num size is 6 and top side is 1. So the rule is, if we haven't declared any constructors in our class, then we get the no parameter default constructor. As soon as we declare any constructor in our class, whether it has parameters or not, that default no parameter constructor is no longer provided. There are actually still a couple of things we can do to make this constructor even better. The first one relates to topside. We can certainly assign topside a value of 1 here, but we can also go to the header file and just initial topside to 1 when we declare it. So let's do that since we have this line of code declaring our variable anyway, and that means that here in the constructor we don't need this line of code because topside is already set to 1. At this point, this constructor looks a lot like the constructors you'd see in Java or C#, where we're assigning a value to a field inside the body of the constructor. C++ has a feature called a member initializer list that actually lets us initialize member variables. Remember, I keep calling those fields, but they're also called member variables. So we can include a member initializer list that actually initializes num size to 6. The way we do that is right here, we add a colon, and then we provide the name of the field we want to initialize, and we provide its value between curly braces. And if we have more than one member variable we want to initialize, we separate them by commas and use the same syntax for each of them. So if I do that, I can actually get rid of this line of code as well, and I'll be initializing num size to 6 here with the member initializer list instead. Let's run the code and confirm that it still runs the way it did before. And as you can see, it does. So you might be wondering, why would we use a member initializer list instead of just using an assignment statement in the body of the constructor? And it turns out that a member initializer list can be a more efficient way of initializing variables, especially those member variables that are classes, because the member initializer list creates that object and initializes it all at once instead of creating the object and then doing the assignment statement in 2 separate steps. So it can be more efficient using a member initializer list than doing assignment statements in the body of the constructor. So we'll use that C++ feature in our constructors whenever we can. We'll actually see in a later course that there are times when we don't actually use the member initializer list, but this particular constructor is simple enough that we both can and should use the member initializer list. To recap, in this lecture we implemented a constructor for a standard 6-sided die in our die class, and we also learned that access specifiers apply to constructors. In this lecture, we'll implement the more general constructor that creates a die object using a user-specified number of sides. In the UML diagram, I've put a box around both constructors because we'll discover when we implement the more general constructor that we should refactor the constructor we implemented in the previous lecture. We'll start by declaring our other constructor in the header file for our die class. So we already have the constructor for a six-sided die. I guess I didn't complete my thought there in that comment. But we're going to add another constructor. It still has to be named die, the name of the class. But this time we're going to include a parameter. And the parameter will be an int. And we'll call it numSides, because numSides is a good name for the number of sides for the die. I'll add some documentation here. Constructor for a die with the given number of sides. I know I've gone off to the right there, but that's because I'm zoomed in on the code so much. And I'll say number of sides. We should cover a little terminology before we go implement this constructor in the implementation file. I said that this is called a parameter. When we're talking about declaring a function and we put one or more parameters here between the open and closed parentheses, that's called a parameter list, by the way. We have comma-separated parameters, and these look a lot like variable declarations. On the declaration side, they're called parameters. I actually restructured my main function a little because I know I'm going to be testing both a standard die and a D20. And I could test a standard die with our no parameter constructor, but to test our D20 die, I need to use the constructor that I just defined in the header. So here, this is an argument. And we'll actually see that again when we call functions that actually require arguments in the next module in the course. So back to our header file, I need to grab this and copy it over here into my implementation file, adding a body and saying it's a member of the die class. And I'll slide this down a little bit. So what should I do here? I should set numSides, the field, equal to numSides, the parameter. And although this compiles, it doesn't do what you want it to do. It's setting the parameter to itself. And what we really want to do is we want to set our field, called numSides, equal to the parameter, called numSides. The problem here is with something called scope. So our numSides field is visible throughout our class. In other words, it's available in all the functions in the class, including the constructors. This parameter numSides, though, is visible between this open curly brace and this closed curly brace, and so the parameter hides the field because they have the same name. Lots of beginning programmers will say, oh, I'll just change the name of the parameter so it's not the same as the field, but there's no need to do that. We decided numSides was a good name for the number of sides for the die, so we should keep that. We've actually seen in previous courses in the specialization, I have provided periodically as an argument in the code something called this. And the keyword this is a self-reference. It's a pointer to the object that we're in. So the way that I can make the left-hand side actually be the field is by saying this. And this says this object, its numSides field, is equal to numSides. And in fact, under the covers, the compiler does this all over the place for us. So if we look at our getter here, it's actually that. But there's no, well, it's actually this, not that. But we don't need to provide that because the compiler takes care of it when it can. In this particular case, the compiler couldn't know that the left-hand side was actually intended to be a reference to the field. So we have to explicitly do it. Now, I will freely admit that we had this discussion because I wanted to talk about using this to let us access a member variable that has the same name as a parameter. But of course, we won't do it this way either. We'll actually use another member initializer list that says, let's set numsides, the member variable, to numsides the parameter. And this will work just fine. We don't have to use this in our member initializer list because the compiler knows that we mean the member variable name here and we mean the parameter name here. And let's go back to our main function and see that we're going to call this constructor here. And if I control F5, we see that I need a line break, but the standard die works fine and the D20 die works fine as well. Let me add that line break here and we'll run the code one more time. And there you go. To recap, in this lecture you learned how to implement a constructor with a parameter, and you also learned how to use the this keyword so that we could access a field or member variable with the same name as a parameter. In this lecture, we'll implement our roll function. As you can see, I've put an orange box around the roll function in our UML diagram, so let's go do that implementation. As usual, we'll start in our die header file, and we want our roll function to be public, so consumers of the die class can actually roll a die object. So I'll just add that here at the end of the header file. Now this particular function returns void. It doesn't actually return a value. It just does its work and then returns from the function. So the return type that we put when we're declaring a function that doesn't return anything, we put the void keyword as the return type for the function. We'll call our function roll. And we know that our roll function doesn't require any information when it's called. It's just going to roll the die. So there's our function declaration. I'll add the documentation. Rolls the die. And we'll grab this and bring it over into our implementation file. Say that the function belongs to the die class, add some curly braces, and we'll actually come back to our main function and add some roll testing. So we'll roll the standard die. So as usual, we put the variable name and then we call the roll function, and now we can just check the top side to see what it is. And we'll do that a couple of times. And then I'll copy this code down here to roll the D20 as well. And I'll have to do some editing to do that, but it's not too bad. So at this point, the body of the roll function doesn't do anything. So we would expect top side to be 1 for all of these rolls. And as you can see, it is. So what does it mean to roll a die? Well, to roll a die, we need to pick the top side of the die as one of the num side sides. For a 6-sided die, that means the top side will be 1, 2, 3, 4, 5, or 6. For a D20, it will be some number between 1 and 20, and so on. And we need to do this randomly. We need to pick a top side from the number of sides randomly. It turns out that computers can't actually do random number generation. They do something called pseudo-random number generation. Let's look at how that works. So I've added a random header file for a random number generator for us to use. So we're not going to worry about the details of what is in this header file, except that we have a public function that will give us a random integer, and we pass in a max value, and that max value is the exclusive upper bound. And it returns a number that includes 0 but not max value. And we need to know about the behavior of this particular function because this is the function we're going to use to get a random number. You'll notice that the function declaration has static in front of it. That means that we won't create a random object. We'll just say random with a capital R, the class name, next, when we need a random number. In the implementation file for the random number generator, you'll see that when we call next, we check to see if we're not initialized. We're just checking to see if we've initialized the random number generator before we generate a random number. If we haven't, then we call the initialize function, which calls this srand function, and that's what I want to talk about. Pseudo-random number generators start with a seed, some number that is used to generate a sequence of random numbers. So this seed, in conjunction with some mathematical algorithm, will generate a sequence of pseudo-random numbers for us. So each time we call rand, which we'll get to soon, we get the next number in that sequence. That's why these numbers are called pseudo-random, not random, because if we know the seed, and if we know the algorithm that's used to generate the sequence of numbers, then we can predict each number as it comes along. That can actually be really useful if we're trying to debug and we happen to know what seed we used for our random number generator. We can then replicate the sequence of random numbers to help us debug our code. But in general, we're not going to be doing it that way. We're just going to seed a random number generator to initialize it, and then we'll just consume the sequence of pseudo-random numbers that get generated. So srand initializes the random number generator, and it's pretty common to get the current time on the current computer to use as a seed, and that's what I'm doing here. When we actually need a random number, we'll call rand to get that next number in the sequence of numbers. And then I've done some math here to make sure that what I return is between 0 and max value, but not including max value. So including 0, excluding max value. Okay, so that was an aside about pseudo-random number generators in computers. Let's actually roll the die. So I know that if I set top side equal to random dot next with num sides as my argument, well, I can't do it because random is undefined, because I need to pound include random.h. So if I do this, I'm going to get a number between 0 and num sides minus 1. And that's not exactly what I want. I want a number between 1 and num sides, but that's easy to solve. I can just add 1. So this function call will return a number between 0 and num sides minus 1, because remember the max value is an exclusive upper bound. And then if I add 1 to it, I'll have a number between 1 and num sides. And of course, I'm getting a compilation error that says illegal use of this type as an expression. Remember, our next function is a static function, and we don't use the dot notation to call static functions. Instead, we use colon colon to call static functions, and that gets rid of our compilation error. Now all we have to do is test our roll function, and when we do, you see that we get random top sides after each time we roll the die. Now I will say that it's certainly possible for us to get the same top side multiple times in a row, just like it's possible to roll a die twice in a row and get 6 both times. That's how random numbers work. It's not probable that we'll get the same number 3 or 4 or 10 times, but it is possible. So when you test something like that, it is not indicative of a bug if we get the same top side more than once or twice or 3 times in a row. That's just the nature of pseudo-random numbers. To recap, in this lecture you learned how to implement a function, and I should really say another function because remember, getters are functions as well. You were reminded that access specifiers apply to behavior functions rather than getters and setters, or in addition to getters and setters. You learned about pseudo-random number generators, and I will say, as part of game development, we often will actually fake randomness in our games. So instead of just letting a particular number appear 3 or 4 times in a row, we'll often add additional code to make sure that we don't have that happen. I've implemented in games that I've written a window of previous random numbers that were generated, and if the number I get next is one of those, I don't use it, and then when I get a unique one, I push the oldest one out of that window and so on. So we'll often do more sophisticated things with randomness in our games to make them more playable, even if the pure random stuff is sort of correct mathematically. And finally, we finished implementing our die class. In this lecture, you'll learn how to implement a destructor. We use destructors to do some cleanup when we're destroying an object, like closing a file we've opened, or closing a network connection we're using, or freeing memory that we allocated within an object. Destructors are called when a pointer to an object is freed, or when we reach the end of a block in which an object was created. We'll start by defining our destructor in our die header file. So I'll do that after the constructors. It can go anywhere, but I'll put it after the constructors. And we always start our destructor name with the tilde, and it always has to be the name of the class, and it can never have any parameters. So it's pretty straightforward coming up with the function signature for our destructor. And I'll just comment this as our destructor. So I'll copy this into our implementation file, and I'll give it a body, and I'll say it's part of the die class. And I don't actually have any cleanup I need to do when I'm destroying a die object, but I want to demonstrate when the destructor actually gets called. So I'll just output a message that says destroying die with num sides sides. So now when I run my code, I get all the behavior I had before, and at the very end, we get a destroying die with 20 sides and destroying die with 6 sides. Over here in our main function, we created one die object here and we created one die object here. And when those die objects go out of scope, which happens to be here at the end of the main function, the runtime calls the destructor for those dice. To recap, in this lecture you learned how to implement a destructor, and as a reminder, we only need to implement destructors when we have special cleanup to do when an object's getting destroyed, which doesn't apply to our die class, but I did want to show you how to implement destructors. I will say that just like constructors, if we don't actually implement a destructor, then the C++ compiler generates a default destructor for us. What will you learn about in this lesson? You'll learn how to define your own functions. You'll learn how to call functions, which we've been doing for a long time, but we'll look at that in a little more detail. You'll learn how to pass data into and out of functions, and you'll learn how we process data within functions. A function definition is comprised of a function header and a function body. In this lecture, we'll learn how to implement the function headers for the 4 different kinds of functions. So what information does a function header give us? It tells us the data type that the function returns, it tells us the name of the function, and it tells us what information we need to pass into the function when we call it. Here's the syntax for a function header. So we have a return type, and then we have the function name, then we have an open parenthesis, and we have a comma-separated list of parameters where, as a minimum, we provide the data type and the parameter name for each of those parameters. We'll see we sometimes add another word, but we'll get to that when we get to that. And then finally, we have the closing parentheses. There are 4 different kinds of functions. A function that has no return value and no parameters, a function that has no return value and does have 1 or more parameters, a function that has a return value but no parameters, and finally a function that has a return value and 1 or more parameters. Let's go take a look. Here's our starting code for this lecture, and as you can see, there's not much going on here. We just have the usual stuff up top, and then within our main function we say we're going to call all 4 functions. And that is a lie for this lecture, but it will be true in the next lecture. In this lecture, we want to develop the function headers for the 4 different kinds of functions. I'm going to start with the simplest form of all. It doesn't return anything, and it doesn't require any parameters. When we have a function that doesn't return anything, we don't provide an actual data type, we provide the keyword void, and that tells the compiler that this function doesn't return anything. I'm going to say that this function prints a message, and we don't get to decide what that message is, so we're not providing any parameters to tell this function what message to print. It will just print whatever we've implemented for the message. I'm going to put an empty body in here so that we can get our function to compile. And I'm also going to add a comment at the top of our function. And this comment will just say prints the message, "Hi, noob." That's a nice message to print. So this will print the "Hi, noob" message when we call this function. I can compile this code, and as you can see, the build succeeded. So that's it for our first function header. We provided the data type that the function returns, which is often called the return type. We provided the name of the function. We always need to put an open and close parenthesis when we're defining a function, so we need that in the function header. And within the open and close parentheses, we put the parameter list, which happens to be nothing because there are no parameters for this function. Let's actually give whoever wants to print a message a little more control over what gets printed. So again, we'll have a function that doesn't return anything, but I'll call this one print provided message. And I'm going to have a parameter here, and we haven't talked about strings yet, but I'm going to pass in a string and I'll call it the message. Of course I need two colons here. So we've actually been using string literals when we've been providing output to standard C out, but this time we'll actually pass a string literal in here for the message. Now that I've clicked elsewhere, the compiler isn't giving me any red squigglies anymore, so that's good. I'm going to add a comment. In this one, we'll say print provided message. And the documentation comment also says, well, there's a parameter here, so I'll mark it so that the documentation generator will pick this up in the documentation. Here's the parameter name that matches over here, and I'll just call it message to print. I'll compile again, and the build succeeded again. So we're halfway done with the function headers that we're writing in this lecture. The next one will have actually return something. So now we have a non-void return type. So this function will return an integer, and I'll say get random number. But we won't provide any parameters. And I'll provide the empty body of this function. And I'll say that this function gets a random number between 0 and the maximum. And I see I'm going to have a long comment here. Integer -1. So we won't have any control over the range of the random number we get. We know we can control the range of a random number we get because we did that when we were implementing the die class in the console app classes lesson. But here we're going to just get whatever random number we get between 0 and the maximum integer in C++ -1. I'll just say this function returns a random number. The final function we're going to write will again give the person calling the function some more control over what they get. For the print provided message, it was more control over what got printed. Here it will be more control over what random number they get. So I'll say int, because we're still going to return an int from this function, and I'll say get bounded random number. And I'll let the caller of the function provide a max value for the number they get. In my comment, returns a random number. I'll just use the same terminology as I said above, so gets a random number between 0 and max value -1. Here in the description of the parameter, I'll say exclusive upper bound. And for the return, I'll say a random number. And I actually forgot to compile after I wrote this function header and provided the empty body. And I'm going to actually have a problem in both of these last two functions when I try to build. So these errors say that those two functions that I said would return a value actually have to return a value. I can't actually compile with empty function bodies for these two functions because I promised I'd return something, so the compiler insists that I return something. I'm not actually going to implement these function bodies with correct functionality. I'll just say they each return -1. And if we ever actually got a -1 from one of these functions, it would be obvious that this was incorrect because the number is supposed to be between 0 and some upper bound. I can now compile again successfully, so we're done writing the function headers for the 4 different kinds of functions. To recap, in this lecture you learned what information a function header provides, and you learned how to implement function headers for the 4 different kinds of functions. In the previous lecture, we learned how to implement the function headers for the 4 different kinds of functions. In this lecture, we'll complete our function definitions by implementing the bodies for those 4 different kinds of functions. And we might as well call those functions as well. Okay, let's start implementing our function bodies and calling those functions from our main function. We'll start with print message, and we know how to do this. And of course I can add a new line at the end as well. Now that we've implemented the body of the function, let's go call it from the main function. And if I build, I get an error message that says identifier not found for print message. Here's the problem. The compiler starts at the very top of the file and works its way down, and when it gets here, it has no idea what print message is because the function definition for print message is down here. We could fix this by doing this. And now we can compile our code, and we can run our code, and it even prints hi noob for us. The problem is that a lot of times we don't want all our function definitions before our main function. We would prefer that they appear after the main function. Because the main function captures everything our program is doing, and most people would prefer to see that up top at the very beginning or near the beginning of the file rather than at the very end. So we'd like to structure our code this way, but still have it compile and run. The way we can do this is we can provide what's called a function declaration, or a function prototype is perhaps more commonly used as the terminology, to tell the compiler there will be a function later with a particular header. Because the header contains all the information the compiler needs to know to be able to call the function. It doesn't need to know the body yet, but it does need to know about the header. This is really straightforward. We can just take our function header and go above main and put the function header with a semicolon, and this is a function prototype for that function. And I'll comment this. So the compiler knows there's a function with this header that will appear somewhere in this file, and then it knows how to handle this call to the function. So I'll run it, and as you can see, that works fine. So we know we're going to need prototypes for all of these functions, so let's just do that now. Making sure I didn't break anything, so I'll build, and it built fine. So let's call the next function, the print provided message function. And I'll say hello world instead. Now I need to implement the body of this function. So I'll grab some stuff and we'll print the message and we'll follow it with a new line. And when I run the code, you can see I get the print message function results and the print provided message function results. Before we move on to the other two functions, I want to point out that we don't actually have to have two different names for these two functions. I can call this function print message as well. I'm going to rename it. I right clicked and I picked rename and I'm going to say I want to call this print message. And I'll say go ahead and do that. And you can see it actually renamed it up here in the function prototypes as well, because it knows this function prototype goes with that complete function definition. The reason we can do this is because these two function headers are different in the parameters that we're providing. And we've talked about in previous courses in the specialization that we can overload functions, that we can have functions with the same name and the compiler can figure out which function to call based on the parameters that we provide. So I'm going to run this again and you can see we get the same results even though we have these functions with the same names. It's probably more common to overload functions that do the same sort of job, like printing a message, with the same function name in different parameter lists instead of having unique function names for all of them. That's why you'll regularly see overloaded functions both in the Unreal Engine and in C++ in general, because that's a more common way to approach this issue. And the compiler can just figure it out based on the arguments that are being provided when you call the function, even though the function is the same name. Okay, on to getRandomNumber. GetRandomNumber is supposed to return a number between 0 and the maximum integer -1. Now you probably didn't notice, but I've included the random.h and the random.cpp that we use for our die class here in this project so that I can just call, here in randomh, I can call next. Now next returns a number between 0 and max value -1. So that's essentially what we want here. So we can just say return random dot, and we immediately get red squigglies because I need to pound include the random.h. And now I can call the next function, which remember is a static function, so I call it using dot dot. And I need to provide an argument for that exclusive upper bound or max value. And as luck would have it, the maximum value for an integer in C++ is int_max. That's a constant that's built into C++. Okay, so now we come back here and we'll just output the result of calling getRandomNumber. And when I run, you can see I got some random number, pretty big random number. I'll run again and I got a different random number and so on. Let's implement the body of our last function, though I'm going to overload the getRandomNumber function just like we overloaded the printMessage function. And this time we'll do this, except instead of using int max, we'll use the max value parameter that was passed in. And I'll call the function, except I'll call the other version of the function where I pass in some max value like 6. So when I run the code, as you can see, everything is working fine. There are a couple of things I'd like to actually do. First, for functions that return a value, I'm going to show you that, of course, I can put the result into a variable, as well as just printing it out to the stream. So I'll grab this, and I'll put it here. There's nothing visible to see here when I run it. It looks just like it did before, but I wanted to show you that many times when we call a function that returns a value, we are going to use that value. So we're either going to immediately use that value here, or we're going to save it because we want to do something with it. It's also possible to just call this function that returns a value and throw away the value that it returned. So this compiles fine and runs fine. It's far more common to use the returned value from a function immediately, like here, or saved into a variable, as I showed you moments ago, but it is possible to do this as well. Those use cases are less common, but you might want to do it if you want to sort of crank through the next few random numbers or something before you use the next one, or some other reason. But almost always, you're using it immediately, or saving it in a variable so you can do something with it. Okay, the other thing that I want to show you, just as when we used one constructor from another when we built our die class, we can of course call one function from another, just as we called one constructor from another in that die class. So this print message could in fact do this. It could say print message hi noob, and so inside this function we call the other function that actually prints the message. Let me show you that that works properly, and as you can see it does. So in this particular situation, I like this code better than the code that I just replaced. It's your call, but you should definitely understand that we can call functions from functions. And we've been doing that all along, right? Main is a function, and we're calling a function from a function. So of course we can do it. I like this form better than the previous one where I did standard C out here. Similarly, I prefer here get random number, just calling this function with int max. There is a cost. There's one extra function call which takes time, and it takes a little bit of extra memory as well on something called the call stack. So you get to decide how you want to do it, but this is my personal preference. And of course I made a mistake when I did that, because I'm no longer returning a value from that first getRandomNumber function, because what I really want to do is return the result of calling this getRandomNumber with int max. And when we run again, as you can see, it's working properly. To recap, in this lecture you learned how to implement the function bodies for the 4 different kinds of functions. You learned how to use function prototypes, and you learned that we can use or ignore the return value for functions that return a value. In this lecture, we'll explore the pass-by-value mechanism that C++ uses by default for functions with parameters. Let's go take a look. Let's write a function that tries to add 10 to the argument that's provided to the function. And I say try to because, as we'll discover, the pass-by-value mechanism doesn't actually let us do it. So our function prototype will be, we won't return anything, but we're trying to add 10 to the provided number. So there's our function prototype. And to make sure I get this correct down below, I'll just copy it down here. And I will say number plus equal 10, which would theoretically add 10 to number. I'll add a comment, even though the comment will be a lie. Adds 10 to the provided number. And I'll just say number. So the expectation from somebody calling this function would be calling this function with an argument. So let's go ahead and do that. And I'll initialize this number to 5. And I'll call the add 10 function with my number. And of course the argument here when I call the function does not have to be the same name as the parameter here in the function. I happen to be using the same name here, but they don't have to match at all. So let's output the value of number after we call the add 10 function. So as you can see, the value of number is still 5. Does that mean the math isn't working here? Let's actually add some more outputs here. And I'll say in add 10 number, and we'll print out the value that was passed in. And I'll get us back over so we can see that whole line. And in add 10, I'll say after adding. And let's run it again and see what's going on. So we've called the function and the value 5 has been passed in. So our number parameter has the value 5. After we've added, number has 15, but our number variable in the main function still has the value 5. The reason this is happening is because C++ uses the pass by value mechanism by default. What does that mean? It means when we call the function here, it doesn't actually pass number in. It passes in a copy of the current value of number. So it's not passing in the value of number, it's passing in a copy of the value of number. So it's not passing in this 5, it's passing in a copy of that 5. So we don't have any kind of reference to this variable inside the function. We don't even have a reference to this value 5. We've copied 5 into a new 5 that we then pass in, that this parameter gets assigned as a value or is bound to that value, but it's assigned this value. So now the parameter number has a value 5, but it's not the 5 that was the value of the number variable in the main function, nor is it the actual variable number. It's just a copy. So we can do whatever we want to this copy. But when we return here, the variable still has its original value. So think of it this way. Say we had a sheet of paper, and that is what's stored in the number variable. I know there's no data type in C++ for sheet of paper, but pretend that the number variable has this sheet of paper as its value. We copy it to pass it into the function. That's how the pass by value mechanism works. So within the function, we don't care what we do to that copy, right? We can color it, we can crumple it, we can chop it up with scissors, we can burn it, we can do whatever we want, because back here in the main function, even after we return from that function, we still have the original. And it doesn't matter what we did to the copy, the value of the original is the same. And that's the core idea behind the pass-by-value mechanism. To recap, in this lecture you learned about the pass-by-value mechanism that C++ uses by default for functions with parameters. And the big idea is that the actual arguments aren't passed into a function, copies are. I'll also say that when we return a value from a function, that's copied as well. At this point, we know how to pass data into a function and return data from a function. In this lecture, we'll write a function that gets valid user input. So our problem is that every chunk of code that we write to get valid user input looks a lot like every other chunk of code that we've written to get valid user input. The solution is to write a reusable function that gets valid user input for us. So let's go do that now. Our function will return an int, and we'll call the function getValidInput. And this function will have 4 parameters. So we're going to see a parameter list that has more than one in it. We'll have a string for the prompt. So I'll call that prompt string. And our parameter list is a list of comma-separated parameters. So I will also add an error string. So when the user inputs an invalid input, we can print that error and prompt again. We'll have a lower bound for the valid values that we're trying to get from the user, and we'll have an upper bound for the valid values we're trying to get from the user. So there's my function prototype. I'll grab it and bring it down here. And now I'll add a comment above it saying what it does. Gets a valid input from the user. And even though these parameter names are self-explanatory, I'll add a description, a brief description of each of those. And finally, we'll return the valid input value. Within the body of our function, this is our standard pattern for getting valid user input. So I'll just type that in and then we'll come back. Okay, so I've declared a local variable here in the function, and I'm going to print the prompt string and read in the value. While the value is less than the provided lower bound, or the value is greater than the provided upper bound, I'll print a blank line, I'll print the error string, I'll reprint the prompt string, and I'll read in the value. Once this while loop is done, that means that value has a valid value, so I'll return it, because I promised I'd return an int from this function. Let's see how we can call this function multiple times from our main function. So let's first say int numScores. So we're going to ask the user how many scores they want to enter. And we'll set that value equal to getValidInput using a whole bunch of arguments here. Our first argument is the prompt string. So how many scores do you want to enter? And we'll give them a range, 1 to 10. Our next argument is our error string. So number of scores must be between 1 and 10. Our next argument is our lower bound, and our final argument is our upper bound. We'll just print out the value we get here. And we'll get rid of this code momentarily, but we want to see that we actually get a correct value returned from the function. When I run the code, first I'll enter some invalid possible number of scores, and then finally I'll enter a valid one. And we do get one back, so that's great. But we've added extra code to do this. Here's where we get the real benefit. We'll say int I equals 0, I less than num scores, I plus plus, and we'll read in each of those scores. Now, I will say, typically, right, we'd put this into an array or vector container. I'm just going to read them in to show the reuse of this function, but that's the real power of functions, is that we can reuse them, and by providing different arguments, we get different behavior. So I'm going to say here, in the body of my for loop, I'm going to say score. So I'll just say enter score, and a score can be 0 to 100 on a typical test, for example. So that will be my prompt string. And here I can say score must be between 0 and 100, so a different error string that I'm using. And then, of course, my lower bound and upper bound change as well. So now when I run my code, first I provide the number of scores I want to enter, and showing you, of course, that does the error checking, and let's say I'm going to enter 3 scores. So now I ask for a score, and I'll say it's -1, or it's 101. And then I'll enter 100 and 99 and 98. And I'm all done. So a huge benefit of functions is once we set up the function header to say what data type is returned, what's the name of the function, and what are the parameters for the function, we can call that same function with different arguments to get different behavior out of the very same function. And that is a huge win. To recap, in this lecture we wrote a very useful function that will get valid user input, and you can reuse this function over and over again in your code. Recall that C++ uses the pass-by-value mechanism by default when we call a function that has parameters. In this lecture, we'll explore how we can have C++ use the pass-by-reference mechanism instead when we call a function that has parameters. This will actually be a pretty short lecture because we only need to make a change to the way we specify our parameter to make C++ use the pass-by-reference mechanism rather than the pass-by-value mechanism. So the change we make is, instead of saying pass an int in, we say pass in a reference to an int, and we add the ampersand at the end to make that change. Now I know we use the ampersand as the address of operator as we've seen in previous courses in the specialization, but that's not what it means here. It means a reference to an int. Now we haven't talked about references, but references are just aliases for a particular variable. So remember, variables are a named space in memory, and so we can have this number as a variable, a named space in memory, and if we say we're going to pass by reference, this number here, the parameter, will act as an alias for the number variable in memory. So now we have two references to that one location in memory. One is the number variable in the main function, and one is this number parameter. They both refer to the same location in memory. So now when I run my code, we see that when we enter the add 10 function, number is 5, and remember, number, the parameter, is referring to the same location as the number variable in the main function. This second line of output says that number, our parameter, has the value 15, but when we exit the function and come back into the main function, you'll see that we actually changed the number variable to 15. So with that simple change, telling C++ to use pass by reference rather than pass by value, we actually can change the value of an argument that we passed into the function from within the function. Because pass by reference doesn't make a copy of the value of number, it just passes a reference to the memory location that the number variable occupies. To recap, in this lecture you learned how the pass by reference mechanism works. You learned that a reference is an alias for a variable, and the big idea with pass by reference is a reference to the argument is passed into the function, so any changes we make to the parameter are made to the argument that was passed in as well. In this lecture, we'll learn how to pass containers into functions and how to use those containers within functions. And although we'll demonstrate the pass by value mechanism with containers, you should always use the pass by reference mechanism with containers to avoid copying all the elements of the containers as you're passing an argument into the function. For our starting code, I've implemented a couple of functions, one called fill vector and one called calculate average, and I'm going to scroll down to those now. So fill vector just fills this vector with the numbers 1, 2, and 3, and then this other function calculates the average of a vector that's passed in as an argument. Let's look at the fill vector function first. So I'm going to call the fill vector function with my scores vector, and then I'll print out the values in my scores vector. So I'll write the code to do that, and then we'll come back. So this is just a simple for loop to print out the scores vector. Let's go ahead and run the code and see what happens. As you can see, there's nothing in the vector. So what this demonstrates is that by default, even with containers, C++ uses the pass by value mechanism. We know that if we want to change the value of one of the arguments we passed in, we need to pass by reference instead. So let's do that. And of course I need to change my full function definition as well. And I'll scroll back up. And when I run the code, you see the vector actually gets filled in. So as we discovered a couple of lectures ago, pass by reference lets us change the arguments we pass in. And this is the way we needed to do it up until C++ 11. And C++ 11 gives us one more mechanism that we can use, and it's called the move mechanism or move semantics. And using move semantics is the appropriate way to program in C++ if you're using C++ 11 or later. Let me show you how we make that work. So first of all, I'm going to say this function actually returns a vector of ints and I'm not going to pass anything in. I will grab this and move down to my function body. But now we no longer have this vector, right, to fill in. So what we do is we declare a local variable and I'll just call it vector. That'll make it easy. And now I can add 1, 2, and 3 to this local variable. But at the very end of my function, I actually return this vector. And when I do this, it actually uses those move semantics to move this vector into scores. So there's no copying here. It's actually a move. So now when I call the function, I will take the result that's returned from the function and put it into my scores variable. When I run, we see that the scores vector gets filled in with 1, 2, 3 as expected. So in C++ 11 or later, you should use move semantics for containers so that your functions look like, in general, the arguments or the parameters are for information that you're passing into the function. And those are often called in parameters. And the result of the function is returned from the function. And that way we avoid using what are called out parameters. So that intermediate one where I had a pass by reference to the scores vector, I was changing that scores vector within the function. And that was the way we needed to do it in the past, but we don't have to do it that way anymore in many cases, including when we're passing containers or returning containers. So that's the first function, and I showed you the first function uses pass by value by default as C++ does for parameters, and then we changed that to pass by reference, which we learned about a couple of lectures ago. But then I showed you using move semantics, which is the right way to return containers from functions. Okay, let's go ahead and average as well. So I'll set an average variable equal to calculate average. And we know I need to pass in a vector, and that's scores. And let's print out the average as well. I'll just say and average and let's see what happens. As you can see, the average is 2, which is expected with 1, 2, and 3. I want to show you one more thing. So I passed the vector in by reference. And I did that because I don't want to have to copy each element of the vector into a new vector. I want pass by reference to avoid that copying. So all I pass is a reference to that variable. And remember, now I have an alias, right? I have values that refers to that vector, and I have scores that refers to that vector. I guess I should grab it here, but it's the same scores, right? So we have two essentially variables referring to the same location in memory. And that's all great, right? It saves me the copying and so on. And it's all great unless I'm a dork and I do something like this. Values 0 equal 100. And if I do that, when I run my code, you'll see that I've changed the first element of my scores vector to contain 100 rather than 1. And of course, that's why we pass by reference, right? So that we can in fact change the value of our variable that we passed as an argument. But we don't want that to happen here. We want to make sure that the values vector can't be changed within this function. I know this feels like an artificial example. Why on earth would you do that? There are lots of other subtle ways that you might change an argument or change a parameter here in the function where you didn't want the argument to be changed. So C++ provides us a mechanism to say we do not want to actually be allowed to change this parameter. And the way we do that is we say const. Just as when we are defining a constant, right? We're telling the compiler we do not want this variable or constant to be able to be changed as we run our code. Adding that keyword here before the parameter tells the compiler you're not allowed to change the values vector inside the function. And whatever data type you have as your parameter. Const works that way for all of them. So now we get a compilation error. And as you can see, it says you can't assign to a variable that's a const. So providing the const keyword protects us from making a mistake, perhaps a more subtle mistake than this, that changes the parameter, which will also change the argument that we use to call the function if we pass by reference. So we remove this crazy code and we go to compile. And we get this very confusing link error. Notice this is not a compilation error. This is happening in the linker after we've compiled. And it's saying it can't find calculate average. The reason for that error is we added const here, but we didn't add const to the function prototype. So we add const to the function prototype, and the code compiles fine. And we can run it again, and we see we get the same results we got before, except now we've protected ourselves from actually changing our vector inside our calculate average function. To recap, in this lecture you learned that C++ still uses the pass by value mechanism when containers are passed into a function. You learned how you can change the function header to use the pass by reference mechanism instead, so we can change the container within the function. You learned that we can use the const keyword so that we're prohibited from changing the container when we're within the function, even if we've used the pass by reference mechanism. And you learned about move semantics, which you should prefer to the pass by reference mechanism whenever it's possible. In this lecture, we'll learn how to pass in objects for user-defined classes into our functions and to use those objects within the functions. I've already written the code that we're using, though we'll modify it a little bit over the course of this lecture. So I have a function prototype for a rollit function where I pass in a die and the function rolls the die. I also have what I'll call a helper function that just prints the die state for a die that gets passed in. So down here in my main function, I'm creating a D20, and I will print the die state of the D20 before I call rollit. Then I'll call rollit, and then I'll print the die state of this variable in the main function after I've called rollit. Within rollit, I roll the die, and then I print out what number I rolled on this die, the parameter. And finally, printing the state of the die is just printing out the sides and printing out the top side. So our focus will be on the rollit function here. So let's go ahead and run and see how this all works. So before I call the rollit function, I have 20 sides on my D20 and the top side is 1. I rolled an 11, and after the call to rollit, the state of my D20 in the main function is 20 sides and the top side is 1. What that tells us is the rollit function uses the pass by value mechanism. It's making a copy of the die and passing in the copy rather than passing in a reference to or the actual die itself. Now you might be asking yourself, how can it make a copy of the die? I didn't write any code in the die class that says copy this die into a new die. Well, it turns out that by default, C++ gives us something called a copy constructor. A constructor that will copy an object into a new object. And it just copies over the values of all the fields or members of that original object. That works fine here because our die just consists of a couple of ints for our fields, but more complicated objects, particularly those that have pointers to other objects or strings or references to other objects, those are more problematic using the default copy constructor, because the default copy constructor does something called a shallow copy. So I know we're going to talk about strings in the next lesson, but let's say we have a string of characters in the original object. When the default copy constructor copies that string over, it just copies over a reference to the same location in memory. So if the original object changes one of those characters in the string, the new copied object also gets that change. So that's called a shallow copy. There are cases where you're going to want to actually have a deep copy, where when you're making the copy, you actually create a new string and copy the old string into the new string. So there's a distinction between shallow copies and deep copies, and the default copy constructor does a shallow copy. We don't care in this particular case, but you may find yourself with more complicated classes that you need to implement your own copy constructor instead of just using the default. But here, the default copy constructor works fine, except that that doesn't actually change our original die. So we know how to fix this. We can make this parameter use the pass by reference mechanism instead. We'll need to change the function prototype as well. And now when we run our code, you can see our original D20 is 20 and 1. We rolled an 11 again, oh well. And then after our call to roll it, the num side is 20 still, but our top side is 11. So as usual, passing an object by reference makes it so that we can actually change the object inside that function. Let's do one more thing. Let's actually say we don't want to change the die in rollit, which is silly, but I want to show you that if we put that const keyword again, the compiler says, no, you can't change the parameter because it's marked as const. It's not super smart. The compiler is not super smart because we know that roll does change the state of the die, and we know that get topside doesn't. So it would be nice if we could get the top side. That's not actually changing the die, but that's okay. We don't want this to be const anyway. But I wanted to show you that the const keyword works the same way for the objects of classes that we've defined. So let me get rid of that before I give you the code, and back up at the top as well. We'll run the code one more time to make sure I didn't break anything, and I didn't. Hey, we got an 11 again. Okay, so one more thing before we stop. With vectors, I talked about using move semantics rather than using the pass by reference mechanism. It is in fact the case that you can have your custom classes use move semantics as well. What you need to do is you need to write something called a move constructor. And that's certainly possible and reasonable and something you may even need to explore as you continue building your C++ knowledge. But because we don't need move semantics for our custom classes in any of the lessons in the courses in the specialization, I'm not going to cover that material, but you can explore that on your own if you ever need move semantics for the classes that you write. To recap, in this lecture you learned that the pass-by-value mechanism is still the default that C++ uses for objects of user-defined types as parameters. We learned that we can use pass-by-reference instead to modify the object inside the function, and we also learned how to use the const keyword to keep that object from being changed within the function even if it's pass-by-reference. And none of this should come as a surprise because the C++ containers are also objects, so user-defined classes are treated exactly the same way as the C++ containers are. In this lecture, we'll refactor our solution to one of the problems we solved in the iteration lesson. The problem is we want to print a box comprised of asterisks of a user-provided width and height. The constraints on the problem are both the width and height need to be between 3 and 20 inclusive, and we need to use functions as much as possible in our solution. This is our nesting in boxes code from the iteration lesson from the previous course, though I have added the function prototype that we developed last time and the body of the function as well. So we're going to start by using this function instead of doing this to get the valid width. So let's change our code a little bit. We'll take our variable declaration and put it here and set it equal to get valid input with, remember, 4 arguments. So here's our prompt string and a comma. Here's our error string, and we won't grab that new line with it because the function includes a new line after it prints the error string, and the upper bound and the lower bound. And then we can get rid of all of this stuff. And now we'll test it and make sure that works fine. Error checking works fine. And then we enter height and we get a 5 by 3 box. Now that we know this works fine, we'll say get valid width and height. And we'll do the same thing to get the height. We can get rid of this variable declaration up here. And of course, we want to change the prompts as well. And now we can get rid of all this code. So let's test this. And we get a 5 by 3 box. Now it looks like I need to add a new line here to separate our input from our output. So I'll just do that right here. And we'll run it again. 5 by 3 and we get that new line. So a couple of things here. As you can see, using this function multiple times makes it so that we have less code in our program, which is great. And You'll notice I didn't retest the error checking when I called the function to get the height because we already know that function is working properly. So that's one of the great things about functions, right? Is we can reuse them as many times as we want. Let's add another function that will handle lots of our printing for us, printing a repeated character a particular number of times. So up here, I'll add another function prototype. This one will be void, and I'll call it print character, and we'll pass in 2 arguments, so the function needs 2 parameters. We need to know the character we're going to print, and we need to know how many times we should print that character. So there's our function prototype. I'll grab that. And down here at the end, I'll build the function body for it. And before I do that, I'll add a comment. Prints the given character num times. And maybe I'll fix a little spelling stuff there. The compiler doesn't care about spelling, but comments are for humans, and some humans care about spelling. So the character to print, how many times to print it. You should definitely know how to implement the body of this function. We'll use a for loop. And I will say, I regularly use int I equals 0 as my declaration of my loop control variable and my initialization of my loop control variable. There are other ways you can do this, right? You could use a braced initializer to set I to 0. You could even do this, and the default would be a value of 0. So there are lots of ways to set I to 0. I just happen to use this syntax when I do that. And I less than num times, and I plus plus. The body of our for loop, all we're going to do is print out that character. We have lots of places in the body of the main function to do this. For example, printing the top row, we used what looks an awful lot like a for loop, printing out the asterisk width number of times, because we started I at 1 and we said I less than or equal to width. So let's just say print character. The character we want to print is an asterisk, and we want to print it width times. We'll test our code and make sure this works. So we'll do a 5x3 box. And as you can see, the top row is printed fine. So now that we know we can do that, we'll print the bottom row the same way. And I'll run it and test. And everything's working fine. Now, as you've noticed, each time I make a small change, I test it to make sure my code still works. That's a really good approach to use, both as you refactor code, which is what we're doing here. We're changing the structure of the code without changing its behavior, but also even when you just are doing pure development. Add a little bit of code and test it, add a little bit of code and test it, and so on. And that helps when you have a bug. Notice I said when, not if. When you have a bug, it's easier to find the bug because it's likely, not positive, but likely that it's in the new code that you just added. Okay, we still have some more repeated printing of characters because we have here in the middle of the box, we print spaces a certain number of times. And we look carefully and we remind ourselves that we were printing spaces width -2 times. So we'll change our asterisk to a space, and we'll change this to width -2. We test again, 5x3, and we get a 5x3 box. Now we could leave it like this, But I want to add one more function. I want to add a function that prints the box interior, the middle of the box right here. I want to do this in a function as well. And I'll show you why I want to do that after we've done it. So up here, we need one more function prototype. Print box interior. And we're going to need two parameters here. We're going to need to know the width and the height of the box. So I'll say width and height as my parameter. And of course I can't have a space in the function name. And I'm going to copy this prototype down to the end. And I'll add a body. And I'll add a comment. Prints the interior of the box. And of course we have a box width and a box height. The code we need for this is already implemented right here. And because I didn't change the names at all, I'm still using width and height, we should be able to run just fine. You're excited, you're ready to run, and so you control F5, and you say 5 by 3, and you're sad because you only get the top and the bottom of the box. A reminder, just writing the function is not sufficient. We have to actually call it as well. Providing the width and the height for the box. And now, when I run it, I get a 5 by 3 box again. Now you may be wondering why I decided to write this function even though I only call it once. And the big reason is we'd really like our main function to give us a high-level view of how we're solving this problem. And by doing it this way, it's pretty clear. In our main function, we have these high-level chunks of functionality included in the main function, but we're letting our separate functions do the heavy lifting to implement the actual functionality. So we know we're getting valid width and height, and then we print the top row, and then we print the middle, and then we print the bottom row. So our main function gives us a high level of what's going on, and then our other functions handle most of the real work. To recap, in this lecture, we refactored our solution to a problem from the iteration lesson, and we improved that solution by using functions. What will you learn in this lesson? You'll learn how to design an Unreal Engine class. You'll learn how to implement fields, a getter and a setter. You'll learn how to implement several functions, and you'll learn how to use the class in an Unreal game. In this lecture, we'll design an Unreal Engine class. And the class we're going to design is a fish class, and this fish will be a ranged weapon. You could build some really interesting games with fish as melee weapons, but that's not what we're going to do. We're going to make it a ranged weapon. An important piece of state for the fish will be the damage that's inflicted by the fish. The two important behaviors we need for the fish are we need to be able to shoot the fish, and we also need to be able to respond to other actors in the game overlapping with the fish. As far as identity goes, we'll get identity when the fish pawn is added to the game. Here's our UML diagram for our fish pawn class. Let's talk about the fields first. The first field is for the damage that's inflicted by the fish. The second field, our force magnitude, will be used when we apply an impulse force to the fish to shoot it. We'll have a half collision height and a half collision width to support clamping of the fish in the screen for going horizontally, and the half collision height will come in useful when we actually include the fish in a game to decide when it's left the screen vertically. We have a move amount per second field so that when we move the fish left and right, we can move it in a frame rate independent way. We're going to save a pointer to the static mesh component for efficiency because we need access to that component at various times as we use the fish. And we're going to include a was shot field that's a Boolean. So we're going to need to make sure that when we respond to shooting the fish, we only do that if the fish hasn't been shot yet. Because if we keep letting the player add an impulse force to the fish by shooting it again while it's already moving, the fish will just go faster and faster. So those are the fields that we have, and that's certainly a longer list than just saying the state of the fish is the damage inflicted by the fish. There's clearly lots more stuff that we need to actually implement the fish functionality. For our functions, which are called methods in the Visual Studio class diagrams, we'll have begin play, where we'll do some work. We'll have get damage, which is the getter for the damage. We'll have move horizontally, so that we can move the fish horizontally. We'll implement on overlap begin, so that we can respond to the fish overlapping with other actors. We have the setter, called set damage. We have shoot, so that we can shoot the fish. And we have the tick function, where we'll consume movement input and move the fish appropriately. So this UML diagram captures the fields and the functions that we'll implement or modify if we get them by default in Unreal for our fish pond class. To recap, in this lecture we designed an Unreal Engine class for a fish. And this is just one abstraction of a fish. I'm going to use the fish in a shooting game. But if we were building a fish cooking game or a fish eating game or something like that, we'd probably want different pieces of state in our fish to make it fit within that game. In this lecture, we'll implement our fields, our getter, and our setter. As you can see in this UML diagram, I've circled, well, I've put an orange square around the parts we're going to implement, so let's go do that now. I've created an Unreal project and added a fish pond script, so let's go ahead and do the fields first. Now I'm not going to do them in alphabetical order as is shown in the UML diagram. I'm going to group them more functionally, so I'm going to start with my fields for movement. I'm here in the fish pond header file, so I'll add a private section. And the first thing I'll add is my move amount per second. And I don't believe this would be changed as the game is played, so I'll make it a const, and I'll set it to float, and I'll call it move amount per second. Because I've played around with this a little bit in the final lecture in this lesson, I know I want it to be around 100 for the game I'm going to include the fish in, but of course you could change this number to tune it to be the correct speed for your particular fish game. So I'm going to make it 100. And also for movement, I want to clamp the fish in the screen. So I'm going to have a half collision width and a half collision height. And in the past, you've seen me assign a value here and perhaps even make it a constant. But I'm going to show you a different way to capture the half collision width and height at runtime. So I can't make these constants, but this will make it nicer than hard coding those widths and heights. And I guess I should add a comment here that says movement support. The next thing I want to do is I want to add shooting support. So I'll need a force magnitude that I'm going to apply when I add an impulse force to the fish to shoot it. So I'll call this force magnitude, and I'll say 300. And again, you tune that number as you need to. And we also need to know whether the fish has been shot. And I'll set that to false. Next, I'm going to add damage support. So I'll just apply integer damage, and I'm going to make this 100. So this will be a one-shot kill fish. If an object that it hits has 100 health and this inflicts 100 damage, it will kill that object right away. Okay, the last field I need is a uStatic mesh component pointer, as we've seen me use multiple times in the past for a variety of different reasons. We also want to implement our getter and our setter, so we need to put the function prototypes or the function headers here in our header file. So I'll do that at the bottom of the file. And of course we want them to be public, so they are, because they're below public here. And we'll do our getter first, so we want to get the damage, and the damage is an int. And I'll add a comment, gets the damage the fish inflicts, and I'll return damage, and we'll do the setter, which will have a return type of void, and this setter will set the damage the fish inflicts. And of course I forgot my parameter. We need to provide some information, specifically the damage the fish will inflict. So I've done that here, and now I'm going to complete my documentation. Like so. I'm going to grab these and put them in my implementation or source file. Include bodies for them. Tell the compiler that they're part of the fishpond class. And actually implement the bodies. So to return the damage the fish inflicts, we just need to return that field or member. And to set the damage, we just need to set that field equal to fish damage. So when I compile successfully. And that's great. It would be nice to test these getters and setters, but we'll defer that testing until we actually have the fish in an actual game. To recap, in this lecture we implemented our fields, our getter, and our setter. In this lecture, we'll implement our begin play, tick, and shoot functions. Here they are on the UML diagram, so let's go get to work. There's a lot of new code for this lecture, so I've already typed it in, and we'll talk about it instead of having you watch me type it all in as we go. So I'm in the fishpond header file. Here are the fields we declared before. I changed the waseshot variable to use a braced initializer. And as we scroll down, I've added the onOverlap begin function That will be called when the fish overlaps with something in whatever game the fish is included in. We already looked at the getter and setter. We have move horizontally, so the player will be able to move the fish horizontally, and the player will be able to shoot the fish. Now, as I say that, you should recall that I typically use a structure where I have a pawn that's controlled by a player controller, and the player controller responds to all the player's input and then calls functions in the pawn. And I'm continuing with that approach here, so I've added a player controller as well. We'll look at the player controller before we finish the lecture, but we'll focus on the fish pawn first. In the implementation or source file for the fish pawn, in begin play, recall that I said that in the past you've seen me initialize half collision width and half collision height with numbers that I got from looking at the static mesh. This is a different way to do that, where you can access that information at runtime. So I have an F vector for the origin of the pawn. I have an F vector for what's called the box extent for the pawn. So this is the extents of the pawn, the dimensions of the pawn. And then I call the getActorBounds function with true, the origin, and the box extent. And you can go read the documentation to see what each of those is, but we really care about box extent because box extent gives us half the depth, which we don't care about in X, half the width, and half the height in the Y and Z field. So we can just set half collision width to box extent.y and half collision height to box extent.z, and that gives us the half collision width and half collision height at runtime instead of having us hard code them. You've seen us saving the static mesh component for efficiency in numerous previous lectures, and I've set up the delegate for collisions with something else here, just like you've seen me do in the past as well. I did actually move this code inside this if statement to make sure that the static mesh component isn't null when we do that. In tick, you've also seen me consume the pending movement input in a pawn. This time I'm making sure that I'm taking that pending movement input that I made sure in a different function, which I'll show you, is between -1 and 1, and I multiply it by move amount per second, and I multiply it by delta time. And that makes sure that our response to player input is frame rate independent. So this is better than using move amount per frame because this will make sure it's the appropriate amount based on how much time passed for the previous frame. So I do this standard stuff, except I only do it in Y. We're only going to move our fish horizontally. I've left this on overlap begin blank. I've included the structure for it. I've included what's often called a stub for setting this all up so it will get called on an overlap. But the behavior that will occur when an overlap occurs will be game dependent. So I've put it in here, and whoever puts this into a game and then starts using it will add whatever behavior is appropriate in this function. We've already seen our getters and setters, and moving the fish pawn horizontally, we clamp the move scale to be between -1 and 1. And then we add that movement input, and then we consume it in the tick function as I showed above. And finally, shooting the fish, we're going to add an impulse force to our static mesh to shoot the fish. And we've seen that before as we were adding an impulse force to Ted to make him go collect the next pickup. But I'm checking to see if the fish wasn't shot before I do this. Because if the fish was shot, we don't want the player to be able to spam the space key. We'll use the space key to shoot the fish, and if they press the space key after they've shot the fish, it would add more impulse force to the fish, so we could make the fish go faster and faster by spamming the space key. So this flag will make sure that we only add an impulse to the fish if was shot is false. And then when we add this to a game, we'll actually see where we change was shot back to false again. And again, that will be game dependent. So you might change was shot back to false after a certain period of time and bring this ranged weapon back to the player. You might do it after the fish leaves the screen. There are different possibilities for when you'll reset was shot to false. So we leave that up to whoever is using this class in a game to handle that particular toggling of the was shot flag. And that's it for the implementation of the fish pond method. I'll show you in the player controller that we set up the input component, we move horizontally and we shoot the fish. And then in the implementation, we set up that movement key binding as you've seen before, and we set up that shoot key binding as you've seen before. Moving the fish horizontally is just as in the keyboard processing lecture from the Unreal Input lesson in the previous course. And shooting the fish looks very similar as well. Over in the editor, I've taken these C++ classes, and of course I added a custom game mode as well to set the player controller and pawn. And I turned those classes into blueprints. And when I run the game and get focus in the viewport, I can move left and right, and I can use A and left, and it stays clamped at 1 for that movement. And finally, I can shoot the fish by pressing the spacebar. So that's the implementation of the functions in the fish pond class. To recap, in this lecture we implemented our begin play, tick, and shoot functions. And we realized we need a player controller to handle player input using our typical approach. It's important to note that when we're designing and implementing Unreal Engine classes, we need to understand how our C++ code interacts with the Unreal Engine. In this lecture, we'll use our fish class in a game. I've moved our fish pond and fish player controller into a game, and I'll show you how the game works first, and then I'll talk about the changes that I needed to make to the fish pond as I included it in the game. So I run the game, and I can move my fish back and forth, and I can shoot a teddy bear, and he died, and then I went back to my original position, and I got him too, but I might just shoot for the heck of it, and I've missed, but I got him, and so on. So I get to use my ranged weapon, and when it kills a teddy bear or goes outside the screen, it comes back to its starting location, and then I can keep playing. So let's take a look at the changes I made to the fish pond. Here in the header file, I added a function called reset to start state. And it's a private function. Nobody outside the class can call it, but I'm going to use it internally because there are times when I need to make the fish go back to its start state. In the implementation file, you can see on begin play, I do all the things I did before, and I call that reset to start state function, which we'll look at soon. On tick, I do the things I did before, but I also check to see if I've gone above the top of the screen. So if the Z component of the actor, the pawn, is above screen constant's top, which I added, plus half collision height, that means that the fish is above the top of the screen, is totally above the top of the screen. And if that's the case, I also reset to start state. I added code here in the onOverlapBegin function to see if I've just overlapped with the teddy bear. And if the other actor isn't a null pointer, and if the other actor has the tag teddy bear, because I tagged my teddy bear actors with that gameplay tag, then I reset to start state. As you saw, when I hit a teddy bear, I went back to my start state. These are the same as before. And finally, reset to start state does a number of different things. First of all, I declare a location variable of all zeros, and then I change the Z component to be the bottom plus half collision height. So that puts me right at the very bottom of the screen, and I set my location to that location. Remember in the previous lecture, I talked about the was shot flag, and I said when you integrate this fish into a game, you're going to need to handle was shot. When does it toggle back to false? And here's where it toggles back to false. If I'm resetting to my start state for the fish, then I'm going to say I haven't been shot again, right? It's the start state where I haven't been shot. Finally, I need to make sure I stop the pawn. And I'll tell you, I didn't realize I needed this in the first place. So let me show you what happens if you don't do this. So when I run my game, I just keep moving even when I go back down to the bottom. And by the way, you may not have realized this, but I can steer my fish as I drive around. He is steerable even after he's shot. So I need to make sure I stop the pawn as well. And we saw how to do this in the Ted the Collector game. When we were designing our fish pawn, we didn't realize that we needed this reset to start state function. That was a game-specific thing that we needed to do in this particular game. And that's okay. It's okay to discover as you use classes that you've designed within games that you don't have the design complete. That's a natural part of the coding process, that the implementation feeds changes to the design and so on. That doesn't mean you did anything wrong. It's the nature of this process of development. Okay, I did want to talk a little bit about the teddy bears and how they're working as well. So in the teddy bears have health. They have 100 health, and they have half collision height as well. And I also included on overlap begin. So in the body of the teddy bear, I save half its collision height. I find the static mesh. I set up that begin overlap thing. On every frame, I'm having the teddy bear move down. So I'm not using physics on this teddy bear because I don't want the teddy bear to accelerate due to gravity. That happens too fast for the gameplay I want. They just steadily fall down the screen. But I do need half collision height so that when the teddy bear falls out the bottom of the screen, I get rid of it. I don't want to keep updating this object as it falls below the screen. I want to destroy it as soon as it's left the screen. In my onOverlapBegin function, I check to see if I've just overlapped with a fish. Now you could argue that I could have handled the processing I do here inside the fish on overlap, or I could handle resetting the fish to its start state from in here on overlap. But doing overlap processing in both participants in the overlap is reasonable in this case because each of them can be responsible for their own response to the overlap. So we get the other actor, the fish, and we typecast it to a fish pawn pointer. We make sure it's not null because we need to reduce our health based on the damage the fish inflicts. It turns out that we don't use the fish's setter in this particular game, but we certainly use the getter here. And then finally, if the health is less than or equal to 0, we destroy the teddy bear. So if I come back to the fish header file and I say, well, fish only inflict 50 damage, not 100. When I run the game, each teddy bear is going to require 2 shots to kill it. Whoa, that didn't work very well. Let me try again. Oh, that's too bad. I need one sort of centered. There we go. And there's the second shot for that teddy bear. Like so. So Changing the damage inflicted by the fish actually does have an impact. Now I need to hit a teddy bear twice with the fish to actually kill it. Make this damage 100 again because I like the one-shot kills. Testing our code one more time. And we're back to one-shot kills with our fish. So that's how we can integrate, with some changes, the fish that we designed into an actual game. To recap, in this lecture, we learned that we may need to change our design when we use our Unreal Engine class in practice, like adding our move to start function in this particular game. We also learned that we may need to implement game-specific functionality in functions we already have in our class, like in the onOverlapBegin function. What will you learn about in this lesson? You'll learn about the data type that we're going to use to store characters. You'll learn some string basics. You'll learn a number of different ways that we can process strings, and you'll learn how to do Unreal text output in a HUD in your Unreal games. One of the things we might want to store in our C++ programs is characters. And in this lecture, we're going to talk about the char data type. And people say that word a number of different ways. You might hear them say char or care or car. I just call it the char data type. The char data type is stored in 1 byte, although only 7 of those bits are actually used. And it's used to store what's called an ASCII character. There are other data types for storing characters in C++, in particular wchar for wide character, so that we could store Unicode characters instead of ASCII characters, but we're just going to stick with the char data type in the courses in this specialization. I will say that there are a variety of operations that we can perform on the char data type, and we'll learn about those as we actually need them. So let's go take a look. Okay, let's start by declaring a char variable, and we do that in the typical way. We put the data type first, and then we put the name of the variable, and I'm going to call this one menu choice, and I'm going to initialize menu choice to a particular value. So I'll use the braced initializer, and I'll say I want menu choice to be Z. When I try to compile, I get this error that Z is an undeclared identifier because the compiler thinks the Z is a variable name. To actually provide a character literal, we need to put single quotes around our character. So just as we put double quotes around string literals, we put single quotes around character literals. Let's go ahead and use the debugger to see how the value of menu choice changes as we run our code. So I'll start debugging. As you can see, before I execute line 11, the value of the menu choice variable is this garbage character. When I execute line 11, you'll see that the value changes to Z, our character literal, just as expected. Now you'll also notice that there's a number next to Z. And if you Google ASCII table and pick one of the resulting images, you'll see something like this. And if we actually zoom in on the value 122, you can see that that's the character Z. So Z is character 122 in the ASCII table. What that tells us, though, is that we can also treat characters as numbers. So I can go here and I can change menu choice, and I can set it equal to a number rather than a character literal. And if I run my code again, you can see that menu choice starts as that garbage character, and then it changes to Z, and then it changes to X, which is at 120 in the ASCII table. Now, it may not be clear to you now why it would be useful to treat a character as a number, and particularly to do math with characters and numbers, but when you go to solve the junior codebreaker problem as the programming assignment for this lesson, you'll see that this is a really useful characteristic of the char data type. To recap, in this lecture you learned that you can use a variable of the char data type to store a single ASCII character. In this lecture, we'll start exploring the very useful string data type. The big ideas are strings are sequences of characters, and strings are also objects, so we'll get functions that we can call on those string objects. If you've programmed in C, you're very familiar with something called null-terminated strings, and these are not those strings. C++ strings are much more robust than the null-terminated strings we get in C. Let's go take a look. Even though this first line of code declaring our string variable has a comment above it saying prompt for and read in a string, I'm going to just show you how we could initialize this string variable first, and then I'll get rid of that code and we'll actually prompt for and read in a string. So we can use a braced initializer just like we've used lots of times to initialize variables. And this time I give it a string literal. So I could say I'm a string. And then the next line of code down here says to print the string, so I'll actually do that. Although I'll lie and say it's the input string, which it will be soon. And then we just provide the name of the variable and our usual end of line. So if I run my code now, as you can see, it says input string, I'm a string. There's some code I haven't shown you yet that prints it out one character at a time, and we'll get there. But as you can see, the string was initialized properly. Now let's go ahead and actually prompt for and read it in. And I should have said when we declare the string variable, we declare it this way. So the name of the data type is string, and it's in the standard namespace. I will say that we will discover as we start trying to do string processing that we're going to have to pound include the string library, but we don't have to do that at this point. Okay, let's prompt for and read in the string. That's pretty straightforward, so let's go ahead and run the code again. And I'll say, for those about to rock, we salute you. And as you can see, it read in that string properly. Let's go ahead and take a look at that other code that I haven't shown you yet. So I have this for loop here that prints out the string one character at a time. And you'll notice here that I'm calling the size function that's provided by the string class that tells us how many characters are in the string. And that's really useful. So I'm going to use that here to start at the 0th element in the string and work my way up to the last element in the string. So as you can see, I'm indexing into the string to access specific characters, just like we've indexed into arrays to access specific elements of the array. So this is the code that generates that output that we've been looking at. I will caution you that using size t, which is an unsigned integral type for I, works perfectly fine if we're working our way forward through the string, because we're guaranteed our indices will keep increasing and stay positive. If you do a backwards for loop using size t, it will end up not working the way you expect, because when you get to 0 and you subtract 1, you'll wrap around to the maximum positive value for the integral type, and you'll never end. right? If you did like I less than or equal to 0, as we've seen in backwards for loops. So if you're going to have to go backwards, which you will if you do all the exercises in this particular lesson, if you go backwards, you're going to want to use int, not size t. But if you're going forwards, using size t works fine. As I've already said, we're just indexing into the string like we've indexed into arrays. So extracting and printing the first character in the string is pretty straightforward. I'll declare a char variable to hold this, and I'll call it first char. And I'll set it equal to input 0. And then I'll print that out. Like that. And we'll run our code one more time. And I'll just do some random string. And as you can see, the first char here at the very bottom is L, as expected, as we index into the string using a particular index to access a specific character. To recap, in this lecture we learned that strings are sequences of characters, and strings are very useful for reading in and processing user input, which we're exploring right now, and input from files, which we'll explore in the next course in the specialization. In this lecture, you'll learn how to search a string for a particular character. Let's go do that now. I've already declared a string variable called data, and I've given it this value. And it's pretty common to see strings that contain data that look like this, especially with a comma that separates the values in the string. And not surprisingly, these are called comma-separated value strings. Before we're done with this lesson, we'll actually do full processing of a comma-separated value, or CSV, string, but our first step will be finding the commas in the string. So we'll explore that piece in this lecture. So our goal here is to find this comma, specifically find the index of this comma in the string. And first I'm going to show you how we can do that manually, and then I'll show you how to do it using a built-in C++ string function, which is of course how you typically do it in practice. Okay, let's find it manually first. I've set an integer variable called comma location to -1. And because we know indexes start at 0, if we ever have -1 as the location of a character in our string, then we know that we didn't actually find that character. And I'll demonstrate that as we go through this code. I'm going to set an index to 0 because I'm going to do a while loop here. And I'm going to have a Boolean expression that first makes sure we don't go past the end of the string while we're looking for a comma, and second, that just stops the while loop if we actually find the comma. So while I is less than, remember we have that size function we can call to find out the size of our string, and data I is not equal to the comma we're looking for. So if either one of those is false, we'll terminate our while loop and continue on with our code. But as long as they're both true, we haven't looked at the entire string and we haven't found the comma yet, all we'll do is we'll increment I to move along to the next character in the string. Let's run this the way it is. And it says manual comma location is -1 and string function comma location is -1. And that's totally incorrect because I forgot to set comma location equal to I. So now when I run the code again, we see that I found the comma at location 3. Don't worry about that other output that's coming from down here. We haven't gotten there yet. So the comma is located at 0, 1, 2, 3. So we found the comma properly. Notice that if I look for a space instead, for example, there is no space in that string. If I run the code, it says the manual comma location is at 7. And that's totally incorrect, right? There aren't even 7 characters in this string. This is 4, 5, and 6. So there are 7 characters in the string, but there's not an element at index 7 of the string. And so what we would want to do here is we'd have to say if comma location is less than data size, we would print out this message and then else, and then we'd say something else like comma not found. I know we're actually looking for a space, not a comma right now, but this is the structure you would use to indicate whether or not you found the comma, and if you did find the comma, where you actually found it. One more time. And of course I put a comma there, not a semicolon, so let's try that again. Okay, so the comma was not found. Of course it is if we actually look for a comma. Running it again, and there you go. Now, it's really common to try to look for a character in a string. So of course, the string class actually provides a function for us to use to do that. So let's go look at the string documentation. I'm looking at the string documentation on C++.com, and as I scroll down, we're going to look for a function that looks like it might do what we want, and you sort of have to read either the names or the descriptions or both to find what we need. And I know that it's down here in string operations, and find certainly looks like a useful function for us to use. So if we take a look at this, and I'll look at the C++11 documentation, it returns a size t to us, so we'll pass in the character or string that we're looking for, and it will return to us an unsigned integral type, just like we've talked about, and it will return to us the location of the character or string we're looking for. Back in our code, we'll set comma location equal to data find, and we're going to pass in the character for the comma, and we can actually just call it this way. The second argument is optional, so we can just run our code, and it found the comma at location 3. Now we have a similar issue to the one we faced above, because if I look for space, which isn't in our data string, and I run our code, I get -1 as the return value. And again, because we know that -1 is an invalid index, the find function returns -1 as a clear indicator that it didn't find the character that we were looking for in the string. So again, we'd add an if statement, except this time we would say if comma location not equal to -1, we'll say that, and then we'll add this else that we had above here as well. So now, comma not found, even though it was a space in the second part, and we'll add the comma back in, and both the manual way and the string function way find the comma in the correct location. There is no doubt that you should always use the find function when you're looking for something in a string. I just wanted to show you this while loop approach as a way to walk the string looking for the comma. To recap, in this lecture you learned how to search a string for a particular character, And even though I showed you how to do that manually, you should always just use the built-in C++ functions to do whatever you're trying to do whenever that's possible. In this lecture, you'll learn how to convert strings to numbers. I've already added a bunch of code here. What we're going to do is we're going to read in a string for a floating point number, and then we'll echo that string in our output, and then we're going to convert that string to a floating point number, and we'll output the value of that floating point number. And then we're going to do the same thing with an integer. I'll show you when I run the code as it stands. I've echoed the floating point string, but I haven't done a conversion yet, so it's always 0 no matter what I enter, and the same with the integer. Now you might wonder why I don't just declare this float data variable and use cin to actually just read into the float data variable like we've done before when we input numbers into our programs. The reason I'm showing you how to do this is because we're on a journey to processing a comma-separated value string, and when we read in our string like we looked at in the previous lecture, we're going to have numbers mixed with commas. So we need to be able to figure out how to take a string and convert that string to a number. Obviously, we are not the first people in the history of programming to need to do this particular task, so there must be something in C++ that will help us do it, and of course there is. Here we are in our string documentation, and although you could scroll down here on the right and not find anything that seems to be helpful, if you look on the left as we scroll down, in this string area here, there are a variety of functions listed here. And I've got to confess you have to sort of know what you're looking for, but stof will actually convert a string to a float. And of course, you could just Google, right? You could say C++ convert strings to numbers, and you'd end up in this same place, probably following a few links along the way. But we can just use the stof function to convert our string to a float. So we'll pass in a string with the representation of a floating point number, and we don't need to worry about that second parameter. We don't need to provide that, and we'll get a float back. So back here in our code, I can just say float data is equal to stof my float string data, with of course 2 colons here, and we get a compilation error that says the compiler can't find stof. As I said when I started talking about strings a couple of lectures ago, there will be times when we actually need to include the string, and this is one of those times. So we'll include string, and now I can actually run my code, and I'll enter floating point number, and as you can see, the conversion worked fine. Why do we actually need to convert the string to a number? Well, it's entirely likely that after we've extracted the separate values from a comma-separated value string, if those values are numbers, we may want to do math with them, and so we need them to be numbers, not strings. So that's the other motivation for turning a string into a number, so that we can actually do math with it. Similarly, there is in fact an s2i function that will convert a string to an integer. So floating point number, integer, and that's all we need to do to convert strings to numbers. To recap, in this lecture you learned how to convert strings to numbers using the string to float and string to integer functions. Last time, we learned how to convert strings to numbers. This time, we'll learn how to process a comma-separated value or CSV string. So why would we want to process CSV strings? This format is really common in textual data. For example, you can export CSV strings from Excel. What ideas will we use to actually do our CSV string processing? Everything we've learned about strings so far, and a little more. Let's go get to work. The problem we're going to solve is we'll have the user enter a latitude and longitude as a comma-separated value string, and then we'll extract the latitude and longitude from that string and print out the result. I've declared variables to hold the latitude and longitude. I've included code to ask the user to enter latitude and longitude, and we tell them no spaces, comma separated, so that we have an appropriate format for us to process, and then we read that in. So the work we're going to do is we're going to find the comma location, we're going to extract the latitude, extract the longitude, and then print those values. If I run the code right now, we can enter anything, it doesn't even have to be comma separated, and we get zeros for the lat and long. We've already learned how to find the comma location in a string, so I can easily add that code. And remember, we can just use the find function to look for our comma. Now what we should do here, because find could return a -1 if there's no comma in the string provided by the user, to be really robust, we should check for -1 and print an error message, but we're going to assume in this lecture that the user has just provided a comma-separated value string in the appropriate format. Okay, so now we know where the comma is, and we want to extract the latitude. What that means is we need to take this lat-long string and take a piece of it that we can pass into the s2f function to actually turn that into a float. So our question is, how do we get a piece of a string? Let's go take a look at the string documentation. If we scroll down and look at the string operations area again, we can see that we have a function called substr, which is short for substring. So if we click on that, we can see that we can call the substring function on our current lat-long string, and we can pass in a starting location and a length, and it will return to us a string object that's a substring of the original string. So what do we need to do here? I'll do this in 2 steps, although we could do it in 1. First, I'll declare a new variable called latString, and I'll set it to the lat-long string, a substring of that string, starting at 0, and how many characters do we need to copy? Well, it turns out that having zero-based indexing really helps us here, because the length is comma location. Let's add a little bit of code that will show how that's working. So I'm going to actually echo, just as a demonstration here, I'm going to echo the lat-long string. I won't even put a label on it, but I will put a new line. And I'm going to want to echo the comma location as well. So when I run my code, now I'm going to want to actually do a comma separated string. So I'll say 1.1 comma 2.2. And as you can see, the comma location is 3. And if we start at location 0 of our lat-long string, we want to include 3 characters in our substring. We want the 1, we want the point, and we want the 1. So this zero-based indexing really helps us because comma location tells us how many characters there are before the comma. That means that now we can just set latitude equal to standard S2F. And IntelliSense tried to help me there because I haven't pound included string. So let's go back and do that. And now we can beat IntelliSense into submission, and we'll convert lat string to a float. When I run this code, I will do the same lat and long, and you can see that latitude has been converted to 1.1. Longitude is still 0 because we haven't processed the part of the string after the comma. So let's do that next. And I will again do it in 2 steps just to demonstrate, but you could certainly take this code and put it right here, and then you don't have the lat string variable at all. But I'll do it in 2 steps again. And I still need a substring of the lat long string. So the first question is, where do we start? We don't want to start at 0 because the latitude is the stuff that comes first. We don't want to start at comma location because comma location is where the comma is. So we want to start at comma location plus 1. And it turns out that if we don't provide that second argument, the length of the substring, then the function will just start at the location we provide and go to the end of the string, which is exactly what we want in this case because the longitude takes up the rest of the string after the comma. Now when we run our code, you can see that we've extracted both the latitude and the longitude from our comma-separated value string correctly. To recap, in this lecture we learned how to process a CSV string. In this lecture, we'll learn to output text to the player in a HUD in an Unreal game. And this is really useful if we want to share information like score or number of kills or something else with the player. So let's go see how we can do that. I've added another C++ class to our project, and I've called it Game HUD. So over in Visual Studio, as you can see, I've derived this class from the HUD class because it's going to be our HUD. I have some private members or fields. I'm using left offset and top offset to place the display of the text I'm going to display in the HUD in the upper left hand corner. You can do it lots of other places if you want, but I want it in the upper left hand corner, so I've declared them as constants. I also have a kill label because I'm going to label the kills count instead of just displaying a number. Fstring is a data type in Unreal, and we'll look at the documentation soon to see why I declared this constant to be of that type. And I'm going to keep track of the number of kills in an integer variable here in the HUD. I have a pointer to a U font for the font that I use to actually draw text in the HUD, and I'll show you how we get that all hooked together as part of this lecture. And I've marked it as a U property because I need to access it from within blueprints. I have a draw HUD function that is part of the HUD class, so I'm just including that here. And I've included an add kill function because when a teddy bear gets killed, it's going to need to call this function to increase the kill count in the HUD itself and of course in the display as well. And we'll talk about that a little more as we go through the code. In the implementation, drawing the HUD, I call the draw text function to actually draw text to the HUD, And the first argument is why I'm using fstring. So let's go take a look at the drawText function documentation first. And if I scroll down, you can see that the first parameter here, the first argument I need to pass in, is an fstring. So what is an fstring? An fstring is a dynamically sizable string in Unreal. So we've been talking earlier in this lesson about the strings that we deal with within C++, and fstring in Unreal is a comparable data type to the strings that we've been talking about in C++. We can construct them, we can append to them, we can search them. The typical things that we can do with a standard string in C++, we can do with an fstring. So that's why I made an fstring constant in the header file for my HUD, so that I can take that fstring and concatenate another fstring to it for the number of kills. And the way I get this integer variable converted to an fstring is I use the fromInt function in the fstring class. And that will take this integer and turn it into an fstring, which I can then concatenate with the kill label. The other things that I provide when I call drawText is I provide the color I want for the text. I provide the horizontal location and the vertical location for the upper left corner of the text I'm going to draw. 0, 0 is the upper left corner for the screen from drawText's perspective. So I have a coordinate system on the screen that increases going to the right and increases going down. And finally, the last argument is the font that I want to use to actually draw the text, which is why we need to store the font here in our GameHUD object. Before we go add the functionality to increase the kills count as teddy bears are killed, we're going to go back and finish building the HUD, and the HUD will then just say kills 0, and then we'll add that last piece so that that kills count increases. But we're done in the C++ code portion now. Now we need to go back to the editor and do some work in the editor. The first thing I need to do, which I haven't done in previous Unreal projects, is I actually need to create a blueprint from my game mode. I can't add a HUD to a C++ class, but I can add a HUD to a blueprint derived from a C++ class. So that's what I'm going to do. So I'll right click this and I'll create a blueprint class based on it. I'll make sure I put it in blueprints, and I'll name it accordingly and create the class. I'm going to save this and close it. And now I'll go to Project Settings, Maps and Modes, and instead of the fish shooter game mode base that we've been using, we'll use the blueprint that I just created. So I've selected that instead. Now we'll go to Blueprints, edit the game mode, navigate to HUD, say Create, and select the GameHUD class that I showed you in Visual Studio. We're creating a HUD blueprint right now, and it created a blueprints folder for me here that it thinks I want to use, but I'm going to put all my blueprints where I put all the other blueprints, and I'll call this Blueprint GameHUD. I'll close this, and as you can see, I have that new GameHUD that I just created, and I have the blueprint that I created a few moments ago for the game mode. So let's go ahead and save everything. Next, I'll open up this blueprint, and you'll see that there is no font associated with my HUD blueprint at this point. And I want to populate this HUD font. So I'll click the drop down and say I want to create a new font. And now I need to decide where to save it. I'm just going to save it in my content folder, and I'll call mine Game HUD Font. Now we've associated the Game HUD font with the Game HUD. So I'll compile and save. And the next thing I need to do is edit the Game HUD font. So I double-clicked it to edit it, and now we need to add a font. And here's where we have to do a slight workaround. So I click Add Font, and I can choose a font file from this computer. On Windows, in the Windows folder, there's actually a fonts folder right here, in between NUS and Game Bar Presence Writer. There actually is that folder. I confirmed that that folder exists. For some reason, it doesn't show up here in this browser. So I'm going to cancel out of here, and I'm going to go use Windows Explorer to copy a font from the Windows Fonts folder into the project itself. So I'll be right back after I've done that. Okay, I've copied that over. So now I'm going to choose again, and this time I'll stay here in my content folder. And as you can see, here's the font I added. So I'll just double click that, and it's going to save the font face as an Unreal asset. So I'll say OK, and I'll say save, and I'll close this, and I'll say save for the Game HUD font, and I'll close that. So now I've built my Game HUD font with a TrueType font from my Windows Fonts folder, and as you can see, I have a little preview for that as well. The other thing I'll point out actually is over here in my font details, I have a legacy font size of 9, which is really small. So I'm going to make it something like 32 instead. And you can modify this however you want. And you can even scale fonts when you are using them in your HUD, but I'll set it to 32, and that should be a good size. So I'll save. And that's all the setup we need to do in the editor. And when we run our game, you'll see that we have our unchanging kills displayed in the upper left-hand corner. And also, as you can see, the kills doesn't change as we play our game. Now that font is pretty big, and you could change it smaller. I just wanted to be very clear to you that we're displaying that text in the HUD, and I want you to see it as it changes. Speaking of as it changes, what we need to do is we need to, when we get a kill, we need to have somebody call the add kill function in our HUD. The question is, who should call it? Should it be the fish or should it be the teddy bear? And there's a clear answer here. With one-shot kills, it could be either one, we don't care. But if it takes 2 hits to kill a teddy bear, the teddy bear is the only one who knows that it's about to die. So we're going to have the teddy bear call the add kill function in the HUD. Let's take a look at how we do that. Here in the implementation file for the teddy bear, I've added a couple of pound includes, one for the game HUD and one for gameplay statics. And we only need to add a few lines of code. And you've probably already guessed that we're going to do this right before we destroy the teddy bear. So down in our onOverlapBegin function, if the health is less than or equal to 0, we're going to destroy the teddy bear, but before we do, we're going to get a reference to the HUD and add a kill. We're going to have a pointer to an aGameHUD object, and the way we get it is we call getPlayerController using uGameplayStatics, because each HUD is associated with a player controller. So we'll get the player controller, and it's really a pointer to the player controller. So we use the arrow notation to call the getHUD function, and this is a templated function, so we can tell it what class we want rather than casting to aGameHUD, and this will give us a pointer to our GameHUD object. And we check as usual to make sure we don't have a null pointer, but if we don't, then we just call, using our notation because this is a pointer, the addKill function in our aGameHUD object. When we do this, when we've added this code, which I just added, that's why kills weren't updating before, but once we've done this, I'll play the game. When I kill a teddy bear, the kills count increases because the teddy bear called the addKill function in the HUD. So now I can display to the player information using text, and many other forms as well in the HUD, but in this example, using text to display information to the player. To recap, in this lecture we learned how to add a HUD to an Unreal game. We learned how to output text to the player in that HUD, and I will say that it's unsatisfying, it's not a good object-oriented design to have the teddy bears know about the existence of a HUD. I mean, they're just teddy bears, right? Given what we currently know about C++ and Unreal, that's the best that we can do, but we'll learn how to implement a better object-oriented design using events in the next course in the specialization. What will you learn about in this lesson? You'll learn about C++ raw pointers, you'll learn about C++ smart pointers, and you'll learn about the smart pointers you should use in your Unreal games. In this lecture, you'll learn about C++ raw pointers. And although you should use C++ smart pointers, which we'll talk about in the next lecture, almost exclusively, you're almost definitely going to run into raw pointers if you work on legacy code. In addition, some of the ideas that apply to raw pointers also apply to smart pointers, so we'll look at those in this lecture as well. The reason we use pointers, whether they're raw or smart, is so that we can dynamically allocate memory as our program runs. Here's the big idea behind pointers. As you can see, our age variable, which is stored at memory location 40, just stores an age, in this case 17. So 17 is the value of that variable. Our score variable is a pointer to an integer located somewhere else. So the value of our score variable, which is a pointer, is actually a memory address. And that memory address is 44 in this particular picture. So the integer that holds the actual score is in memory location 44, and the score pointer variable points to that location in memory. That's why they're called pointers. Let's go see how this actually works in code. Let's start by looking at declaring pointer variables. On line 14 here, I'm declaring a pointer to an int. So this isn't an int, this is a pointer to an int. And I've called this pointer score, and I'm initializing the value of this score pointer to be null pointer. We've seen some of this before. We've seen the asterisk when we've declared pointers in some of our Unreal scripts, and we've also seen comparisons to null pointer when we were retrieving pointers to particular objects and we wanted to make sure that the pointers weren't null before we tried to access functions on those objects. So this syntax should feel familiar to you, although we've never actually initialized our pointers this way in our Unreal games. We've always been setting our pointer variables equal to the result from some function we were calling in the Unreal Engine. Just to show you that we can point to more than the fundamental data types, I'm pointing to a die here, and I'm calling this pointer D6 because it's going to point to a six-sided die. Now the pointer doesn't care. The pointer knows it's going to point to a die object, and it doesn't care how many sides it has, But this one I'm going to call D6, and I'll also initialize that one to a null pointer. And then finally I have a third pointer variable also pointing to a die object. This one will point to a D20, but I wanted to show you that I can declare the pointer variable and create the object it points to and set the pointer variable to point to that object all in one line of code. So I've got a pointer to a die, and I will construct a new die, and I will call the die constructor that passes in one argument, the number of sides for the die. So I'm passing in 20 here. So score will point to an integer, though it doesn't yet. It just is a null pointer. D6 will point to a die object, though it doesn't yet. It's a null pointer. And D20 will point to a die object, and it already does because I created a new die object and initialized this pointer to point to it with this syntax. The next thing we'll see is allocating memory. We don't need to do that for the D20 because we already allocated memory for the die. But score will allocate memory for an int, and D6 will allocate memory for a die object. And it doesn't just allocate memory, it also sets the pointer to point to the memory that was allocated, so it holds the address of the memory that it allocated for an integer or the object that it just created for a die. And of course this will be a six-sided die because we called the constructor version for the die that doesn't have any parameters, so it automatically creates a six-sided die for us. The next thing we'll do is a whole bunch of printing of addresses. So I print the address of score. So this is where the pointer gets stored in memory. And then I print the address that score points to. And that address is where the int actually is located in memory. Similarly, I do that for the address of D6, so the address of the pointer, and then the address of the die object D6 points to, and then the address of the D20, and then the address of the D20 object, the die object, that the D20 pointer points to. Now we will change and print the value of the fundamental type. To access the value that score points to, we need to use what's called the dereference operator, so it dereferences the pointer. In other words, here's the pointer, but here's what the pointer points to. So I can print out the value of the int that score points to by dereferencing the pointer with this asterisk. And I can also change the value of the int that score points to by dereferencing the pointer and then setting it to some value. And of course I can dereference the pointer to do math with the int and all kinds of other things. I'm just showing the assignment here. But the big idea is we dereference the pointer to actually get to the memory that the pointer points to sort of follow that pointer and end up at where it actually points to. I can also call functions on the D6, and we will look at the arrow notation that we've seen before in Unreal Engine scripts. First, I'll show you that another way to do it is we can dereference the D6 pointer, which means we're now holding an object, a die object in this case, and so we just use the dot notation to call functions on the die object. So remember, when I talked about the arrow notation, I said we're used to using the dot notation to call functions on an object, but because it's a pointer, we'll use the arrow notation instead. And that is by far the more common notation to use. So the arrow notation is here. So another way I can call a function on an object that a pointer points to is to put the name of the pointer variable and then the arrow and then the function I'm trying to call. And we've seen this numerous times in our previous work in Unreal Engine games, but this is another way to do the same thing. Hardly anyone does that. Most programmers will use the arrow notation, so that's what we'll continue to do when we're dereferencing a pointer and calling a function on the object that the pointer points to. And then I call functions on the D20 in a similar way. And the last thing that I need to do with raw pointers is I need to do two things with each pointer when I'm done with it. The first thing is I need to release the memory that I allocated for the thing the pointer points to so that we don't keep holding on to that memory. So it's good practice to release memory when we're done with it, and with raw pointers we have to do that ourselves. The runtime system won't handle it for us, we have to do it. So if we don't release memory when we're done with it, and particularly if we didn't release the memory that score points to, and then we allocated more memory for score to point to, that other piece that was allocated will actually stay in use by our program even though we're not using it anymore and we can't even get to it anymore. That's actually called a memory leak, and that's one of the big dangers of raw pointers. The other thing that we need to make sure we do after we've deallocated or deleted that memory or freed that memory or released that memory is we want to set score equal to null pointer, because we could, by mistake, later in our code, try to access the memory that score points to, but if we've already released that memory, then who knows what's at that memory address now. It could be garbage, it could be something else that was allocated in some other part of our program, and that would be a horrible thing as well. And that's called a dangling pointer, when a pointer points to something that has been released and it shouldn't try to access that memory anymore. So we want to do these two things every time we're done with a raw pointer. Let's actually run this code and see what it looks like. So as you can see at the top, we have a bunch of addresses. And so the address of the score pointer is this hex address. And then the address of the integer that the score actually points to is the second line. Here's the address of the D6 pointer, and here's the address of that D6 die object. Here's the address of the D20 pointer, and here's the address of the D20 die object. As you can see from the next line, the current score value is this big negative number. When we allocated memory for the integer, the runtime system went off and found a piece of memory for us that will hold an integer. And we have whatever garbage happened to be in that piece of memory as the value of the integer. You saw in my code that I then dereferenced the score pointer and set score equal to 100, so that next line shows that we've changed the pointed to value, the integer that we point to 100. The next two lines of code show that we created a D6 properly. So I'm dereferencing the pointer and calling functions, whether I'm using the dereference operator and then the dot notation or the arrow operator to do that. So the D6 has 6 sides and the top side is 1. Remember, that was our default for our die. And then finally, the D20 has 20 sides and the top side for the D20 is 1. And that's a whirlwind tour of raw pointers in C++. To recap, in this lecture we learned how to use C++ raw pointers, even though we should use C++ smart pointers as much as we possibly can. And we also learned that using C++ raw pointers can lead to some really bad bugs, including memory leaks and dangling pointers. Last time, we talked about raw pointers in C++ and how to use them. But we also learned that using raw pointers can lead to memory leaks and dangling pointers. In this lecture, we'll learn how to use smart pointers to avoid those problems. So what's a smart pointer? A smart pointer is a pointer that the runtime handles the memory for. It manages the memory for that pointer. What kind of smart pointers do we have available to us in C++? We have unique pointers, where only one pointer can point to a particular location in memory. We have shared pointers, where multiple pointers can share a particular piece in memory. They can both, or as many as you want, can all point to the same location in memory. And finally, there are weak pointers that are useful in some cases, but none of them will appear in any of the courses in the specialization. So that's the last you'll hear from me about weak pointers. For this lecture, I've converted the raw pointers code to use smart pointers instead, and we'll explore smart pointers a little more as well. So we'll start by looking at how we declare smart pointers to fundamental and user-defined data types. As you can see, the data type for my score pointer is now unique pointer to an int. And I'll show the use of shared pointers at the end of the code, but this is the way that we set up a unique pointer to an integer. We declare it as a unique pointer. It's a templated type, so we put the data type we're going to point to here. And the rest of this looks very similar. We have the same variable name. I'm saying it's a null pointer at this point. And so this line of code and this line of code look very similar to what we had before, except we're using unique pointers to an int and a die object. You may recall that the third line of code in the previous lecture called the constructor for a die object to build our D20. We're going to use a different syntax to do that for our unique pointer for the D20. So it's a unique pointer to a die object, and I've named it the same, but this time we call the makeUnique function for a die, and we pass in 20 as an argument to the constructor for making that unique object. So this line of code right here is creating our die object that will have 20 sides using the makeUnique function to do it. And although you'll see other ways that people will do this for our smart pointers, this is the accepted modern way to build objects that are pointed to by a unique pointer. As far as allocating memory goes for score in the D6, as you can see, I'm calling that makeUnique function again for an int and for a die. And because I haven't passed in any arguments for this making a unique die object, we'll end up with a standard 6-sided die just like we did in the previous lecture. Now I have a line of code that says can't do this. And of course I can do this. I can declare another variable called score2 that's a unique pointer to an int and initialize it to a null pointer. This is the thing I can't do. I can't set score2 equal to score. When I uncomment this code and build, you'll see a pretty cryptic error message that says operator equal for unique pointers. We're attempting to reference a deleted function. What does that mean? It means that we can't set one unique pointer to the value of another unique pointer because, wait for it, the pointers are supposed to be unique. We're only allowed to have one unique pointer pointing to a particular memory address. So this was just demonstrating that only one unique pointer can point to a particular memory address. All of this code printing the addresses of stuff is exactly the same. We are using the address of operator, which I didn't mention in the previous lecture. We're using the address of operator when we want to get at an address of a particular variable. And down here, we use exactly the same dereferencing syntax to access the integer that score points to. We use exactly the same dereference followed by dot notation or the arrow operator to get at functions on those objects that are pointed to. So lots of the syntax for the smart pointers is the same as for the raw pointers, but the underlying safety of smart pointers make it so that's really what you should use as much as possible. Using raw pointers is something that you might have to do if you're working with legacy code, but when you write your own code, you should use smart pointers as much as you can. We see the same notation on D20s. We don't have to actually release the memory on these unique pointers. So we can, if we call reset on a unique pointer, then it releases the memory we pointed to, and it automatically sets score to be a null pointer. So we don't have to do this part anymore. It automatically happens when we call the reset function, but we don't need to call the reset function either. The runtime system is smart enough to know when the score variable goes out of scope, for example, if it were within a function, or when we reach the end of the program, the runtime system will automatically release the memory. And that's one of the great benefits of using smart pointers, is we don't have to worry about releasing memory. So we avoid the memory leaks, we avoid the dangling pointers. We get to just use the pointer in a much more robust way than if we're using raw pointers. I did want to show you how shared pointers work as well. So here's what I'm doing down here. This time, I'm creating a D6 S1 on this line of code. I'm creating a D6 S1 variable that is a shared pointer to a die object, not a unique pointer, a shared pointer. And I'm going to just create a six-sided die immediately when I declare this variable. I'm also declaring another shared pointer to a die object called D6X2, and I'm initializing that one to null pointer, and then I'm setting D6S2 equal to D6S1. And this is the line of code that we looked at above for unique pointers that wouldn't compile, because we don't get the assignment operator for two unique pointers, because it's not allowed to set one unique pointer to another. But with shared pointers, we can set D6S2 to D6S1. And after this line of code, both of these pointers point to the same die object in memory. To demonstrate that with my output, I'm saying what address does D6S1 point to, what address does D6S2 point to, and then just to show that they actually point to the same object, though of course they do if these addresses are the same, I output the top side for D6S2, and then I roll D6S1, not D6S2, I roll D6S1, and then I show the top side for D6S2 again. So I'll run this code. We have all the stuff we had before. When I made a unique pointer to int, you'll notice I got 0 instead of garbage for my int. We still ought to make sure we explicitly set this to a value, so I set it to 100 like before. The rest of this stuff is working just like it did before. And then for the shared pointers, you can see that both D6S1 and D6S2 point to the same memory location. And unfortunately, before I rolled the top side was 1, and after I rolled the top side was 1. That was just the luck of the draw. I happened to roll my six-sided die and get a 1, so let's run it again. And as you can see, we actually get a better random number here to demonstrate what I wanted to show you. So the top side of D6S2 is 1 before the roll, and then after we roll D6S1, the top side of D6S2 is 2, because both D6S1 and D6S2 point to the same die object. And that's your whirlwind tour of smart pointers in C++. To recap, in this lecture you learned how to use the unique and shared smart pointers in your C++ code. Last time, we talked about smart pointers in C++ and how to use them. This time, we'll look at the smart pointer types provided by Unreal. We're not going to look at any code in this lecture, we're just going to look at the Unreal documentation for smart pointers. So an important thing to recognize before we even start talking about the different kinds of smart pointers that Unreal provides is the documentation tells us that the smart pointer classes cannot be used with the UObject system because Unreal objects use a separate memory tracking system that's optimized for game code. Our actors are derived from UObjects, and our pawns are derived from UObjects, and our player controllers are derived from UObjects. So the Unreal smart pointers are not for pointing to actors and pawns and player controllers, which we've been creating through lots of our Unreal games. These are for pointing to other objects for custom classes that we build that don't inherit from UObject. We haven't seen a need to do that yet in our Unreal games, but certainly it's a useful thing to do as you build larger, more complicated games, so it's a useful feature within Unreal. Basically, the Unreal Smart Pointer Library is a custom implementation of the smart pointers we've already been talking about, with one extra data type. But as you can see, we get a shared pointer called tsharedPointer that behaves the way that we've seen for C++ shared pointers. We get something called a shared reference, which is like a shared pointer but has the additional constraint that it can't be null. So we know shared pointers can be null in C++, and tshared pointers within Unreal can also be null, but tshared refs or shared references can't be null, which can be useful if you want to make sure that you can never be referring to a null object. We have weak pointers, which remember we said we weren't covering in C++, and we're not covering it here either. And then finally we have unique pointers that will behave just like the unique pointers that we've seen in C++. So Unreal provides a number of smart pointer types, and within Unreal Engine games, you should be using these smart pointer types, not the standard C++ pointer types. To recap, in this lecture, you learned about the smart pointer types that you can and should use in your Unreal games. This will be the shortest lesson introduction ever. In this lesson, you'll learn how to play sound effects in your Unreal games. In this lecture, you'll learn how to play sound effects in your Unreal games. And we're only covering the basics here. You can do lots of really cool stuff with sound effects in Unreal, and you should learn on your own how to do those things as you need them. We'll start by adding a sound asset to our project, and we're going to add a wave file. The Unreal documentation says that it supports a variety of different formats, but it's going to convert it to a wave file anyway, so you might as well just import a wave file. I'm actually going to create a new folder here in my content for audio, and then we import an audio asset. You can right-click and say import, and then you navigate through your file system to find the asset you want to add. So I'm going to do that, and then we'll come back. And as you can see, I've added a wave file named OW, and I'm going to save that. So I'll say save all and save selected. So now I've saved that wave file as an audio asset in my project. The next thing I want to do is create a sound cue. So the sound cue is a conceptual representation of the possible sound in the game. That sounds really weird. The reason the documentation talks about it that way is because we can set up our sound to mix a variety of different sounds and do other context-sensitive things based on what's happening in the game at the time we play the sound, and lots of interesting things. We're just going to play the sound. So I'll right-click here and say I want to create a sound cue, and I'm going to rename this Teddy Death Cue because we'll play this sound cue when the teddy bear dies. If I double-click it, I end up in a sound cue editor. And this looks a lot like the level blueprint editor that we used way back in the first course in the specialization to give us an orthographic camera. This is the blueprint's visual scripting environment, and we're going to use that to set up our sound cue. This output node here on the right will be the actual sound output, but we need something to play our sound. So I'm going to right click here in this area, and I'm going to add a wave player. If I select this node, you'll see over here on the left that it doesn't have a sound wave associated with that wave player yet, but I can easily pick the sound wave that I imported into the project. The last thing that I need to do here is I need to connect this wave player with the output. So I left click on this circle and I drag over and I drop on the circle here on the output node, and that connects the two together. And if I want to check to make sure that I've done this properly, then I can play the cue. Ow! And as you can see, we hear that sound. So we've set up our sound cue. I'll save that and we'll close the sound cue editor. The next thing we need to do is set up our teddy bear to actually play the sound cue when the teddy bear dies. We need to edit both the header file and the implementation file for the teddy bear. So let's do the header file first. I'm going to need to have access to the sound cue class. So I need another #include, and it's in sound cue.h. And the reason I need access to that class is because I'm going to add a property to my header file. So down here, I'm going to add a public field, but I'm going to mark it as a U property so I can populate it in the blueprints editor. I'm going to say we can edit this anywhere. I'm going to set it to blueprint read write. And I'll set up a category, and I'll call that category sound. And you've seen using the uProperty macro in previous lessons and in previous courses. The field I'm going to have, and this is why I need that #include, is a uSoundCue pointer, and I'll just call it audio cue. You can pick whatever name you want for that field. That's all the work we need to do in the header file, so let's save that, and we'll come over to the implementation file, and we'll find the place where the teddy bear dies, and I know that's in the onOverlapBegin function, so we'll go there. And here, where we're checking if health is less than or equal to 0, we'll also play the sound. The way we do that is we use uGameplayStatics. And there are actually a number of functions we can use to play a sound. We're going to use playSound2D. And we pass in 2 arguments. This is the first one, and the second argument is the name of the field that we're using to store our sound cue, and I called that audio cue. That's all the code we need to change, so I'll build, and now we have one more thing to do back in the editor. Here in the editor, we need to navigate to our blueprint for the teddy bear. And we'll open it up in the blueprint editor. And as you can see over here on the right, I now have a sound category where I'm supposed to fill in an audio cue, and I'll populate that with the Teddy death cue that we built. And I'll compile and save and close the blueprint editor. And when I run the game, when I kill a teddy bear, you'll see he says ow, which is exactly what we were hoping for.
Ow!
And that's all there is to playing a sound effect in your Unreal games. To recap, in this lecture you learned how to play sound effects in your Unreal games. Congratulations on completing this course. I hope you learned a lot, and I hope you had fun doing it as well. There's one more course in the Specialization, so if you want to keep exploring C++ and Unreal, you should take that course. But if you just want to go start building your own games, you should do that as well. No matter what you decide, thank you for joining me in this course. I love doing these courses, and I'm glad you joined me in the course. Cheers. Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the Computer Science Department at the University of Colorado at Colorado Springs, where I teach a variety of game development courses and some computer science courses as well. I'm also the program director for our Bachelor of Innovation in Game Design and Development. I have 5.5 years as an indie game developer in a company that I started with my 2 sons, and now I do my game development in my one-man shop, Burning Teddy. This is a 4-week course, and in week 1 you'll complete a quiz that's worth 25% of your grade. In weeks 2 and 3 you'll complete programming assignments that are each worth 25% of your grade, and then in the final week you'll complete a final exam that's also worth 25% of your grade. I've provided lots of exercises for you to do that don't count toward your grade, but they give you good experience engaging with the course material. So what will we cover in this course? We'll cover exceptions, which are things that happen when stuff goes badly wrong in your program. We'll cover file I/O, or file input and output, which is really useful for us as we include game configuration data in our game and we persist data between gameplay sessions. In week 2, we'll move on to inheritance, a hugely important idea in object-oriented programming. And then we'll look at polymorphism, a related and very powerful capability that we get when we use inheritance. We'll close out week 2 with a look at a teddy bear destruction game, which will use lots of all those ideas from week 2. In week 3, we'll move on to event handling, which lets us implement even better object-oriented designs. And we'll close out week 3 looking at how we can implement menus in our Unreal games. In the final week of the course, we'll look at a larger, though still small by commercial standards game called Feed the Teddies that uses lots of the ideas from this course and also uses ideas from the previous courses in the Specialization. Speaking of those previous courses, this is the 4th and final course in the Specialization, so it builds on the foundation that we've built in those previous 3 courses. That means that I have an expectation that you have good mastery of the material in those previous courses so we can keep building on that foundation. As always, if you run into trouble, there are forums in the class or fora in the class that you can post your questions to so that other people can help you. And as a secondary technique, you can also look on the web to see how to solve a particular problem you might be running into. Let's go get to work learning all these things in the last course in the Specialization. What will you learn in this lesson? You'll learn what exceptions are, and you'll learn how to handle exceptions. And as part of learning how to handle exceptions, you'll learn about try blocks and catch blocks. In this lecture, you'll learn what exceptions are. And the big idea is exceptions are objects that are thrown when something bad happens in our code. And I don't mean something bad like we asked the user for a number between 0 and 100 and they entered 101. I mean something bad like we asked the user for a number between 0 and 100 and they entered Bob. We'll learn in the next lecture how to actually handle exceptions, but in this lecture we'll just look at the documentation for exceptions and then we'll see how they work in code. If we look in the C++ documentation for exceptions, we can actually see that the exception class is the top of a class hierarchy of a bunch of other more detailed exceptions, and we'll learn about class hierarchies in the next module when we talk about inheritance and polymorphism. But the big idea is that this exception class gives us a consistent interface for handling errors by throwing exceptions. And we'll actually see a couple of these exceptions when we look at the example lecture code. Our code for this lecture starts by declaring an array container of ints of size 2 and initializing the elements in that array container to 0. We then run a for loop to print out each of those scores using the @ function that's provided by the array container. And then we get to throwing exceptions. So first, we'll throw an exception where the user enters Bob. So we declare a string, and then we ask the user to enter a value for the first element of the scores array. And then we read in the score string, and we convert that score string to an integer and put it into scores 0. And that will throw an exception for us if we enter Bob when we're prompted for a value for scores 0. The second exception we'll see is we'll try to index outside of the array using the @ function again, but this time we're going to provide an invalid index for our scores array. Remember, our scores array only has 2 elements, so those are at indexes 0 and 1. So 2 is outside the bounds of the array. And you should remember that this is one of the powerful features of the array container as compared to the basic array in C++, is that we can actually know if we try to index outside the array. Whereas if we're just using a basic array, we can index past the end of the array and look at all that memory pretending it's part of the array even though it's not. So let's run the code and see what happens. I will enter an invalid value for score 0 here. I'll type in Bob and hit enter, and as you can see, our code crashes. When we move on to actually handling this exception in the next lecture, we'll see that we really want to know what exception it is, and I'll show you how to do that now, and then we can use that information in the next lecture. So I'm going to set a breakpoint here on line 25, and I'm going to debug. I'm going to press F5 to debug. You can also click up here and say start debugging. And now when I enter Bob, I get to this line of code and the exception hasn't been thrown yet because I haven't tried to convert Bob to an integer yet. If I press F10 to step over this line of code though, I get an unhandled exception, and it even tells me that it's a standard exception and it's the invalid argument exception. I'll stop debugging. That makes sense, right? Passing in a string that's not an int is an invalid argument for the s2i function or the string to int function. Let's throw the second exception. If I run my code, not debug it, just run it, and I enter a valid value here, it gets past that line of code, but it crashes again on that second exception. If I set a breakpoint here and we debug our code, and I'll enter a valid int here, and I'll give the editor focus again, I'll step over that line of code and it succeeded. It turned 1 into an int just fine. But if I try to step over this line of code, you can see I get an out of range exception. So we can use the debugger to identify which exceptions are getting thrown as we run our code. Let me stop debugging. We won't handle those exceptions yet. We'll do that in the next lecture, but I wanted to show you in this lecture how the exceptions are getting thrown and how we can figure out which exceptions are getting thrown. To recap, in this lecture you learned that exceptions are objects that are thrown when something bad happens in our code, and we also learned that exceptions crash our console apps if we don't handle them, and it's also the case that exceptions crash our Unreal games if we don't handle them. In this lecture, you'll learn how we can handle exceptions. And this is an important thing to do because if we handle a particular exception, it won't crash our code. The way we do this is we put code that might throw an exception inside a try block. We're going to try that code and see if we can run it without it throwing an exception. And then we add one or more catch blocks to catch specific exceptions. Let's go see how that all works. This is the code we ended with in the previous lecture. So now we're going to actually catch these exceptions that are getting thrown. Our first step is to enclose any code that might throw an exception inside a try block. And although we could put a separate try block around each of these blocks of code, one try block for this and one try block for this, I'm going to put all of this code into a single try block instead so that I can show you how we can have multiple catch blocks to catch different exceptions. I'm going to get rid of these breakpoints because we don't need them. So I'll say try and then open curly braces, and down here at the bottom, close curly braces. Now you'll notice that I can't compile at this point, and if I do try to compile, you'll see that I have an error message that says my try block doesn't have any catch handlers. There are no catch blocks included to handle exceptions. And if we as programmers go to the effort to add a try block, then the compiler expects us to have at least one catch block associated with that try block. So let's go ahead and catch that first exception. You may or may not remember that that was an invalid argument exception. So the data type for the exception is invalid argument. And we do need to give it a name because what happens is we get an exception object here and we need to name that object. We're providing a data type and a name for this object. You can think of this as a parameter for the catch block for this exception. I'll just call it IA. And then we can do something here if we have an invalid argument. So I'll just print a message. We could, of course, do any number of different things here when this exception gets thrown, but I'm just going to print a message. Score must be an integer. Like so. So now, when we run the code, if the user enters Bob, the exception will get thrown on line 27 and will immediately jump down to the first catch block to see if the exception that was thrown matches the data type that we've provided here. And if it does, we'll go into the catch block and do whatever the body of the catch block says. I'm actually going to add one more output down here so you can see the full flow of control through the code. Past exception handling. Okay, so if I run my code and I enter Bob here, what happens is we say the score must be an integer, and then we move past this entire set of try and catch blocks, and we move past that chunk of code to any statements that might follow that chunk of code. I'll add a new line here as well. So we caught that invalid argument exception and we handled the exception. What we haven't done yet is if I enter a valid integer for that first exception, that exception doesn't get thrown, and we move on and we crash because we've now thrown an exception on this line of code, on line 30. We can have multiple catch blocks associated with a particular try block. So this one was an out of range exception. And again, I'll give it some arbitrary name for that parameter. And here, I'll say indexed out of array bounds. So now when I run my code, I'll show you that if I put Bob, we still get that score must be an integer because we caught that exception and handled it. And then we moved past the try catch blocks and printed the past exception handling message. And if I run it again, and I don't throw that invalid argument exception, I caught the other exception where we indexed out of array bounds. So we moved past that first catch block because the out of range exception didn't match the invalid argument exception type. So after determining that the first catch block didn't apply, we moved on to the next catch block in our line of catch blocks, and that one did apply. So we went into the body of that catch block, did what it was supposed to do, and then moved past the try catch code and printed that past exception handling message. Let's do one more thing for efficiency before we leave this lecture code. Under the covers, the way this works is when an exception is thrown, the runtime makes a copy of that exception immediately. If our catch blocks pass in that exception object by value, as they do right now, then the runtime will make a second copy of that exception object to pass into the catch block. So when we're catching exception objects, we should pass those in by reference rather than by value. We also actually know that we're not going to change the exception inside the catch block, so we can mark them as const as well. The pass by reference rather than pass by value is an efficiency thing, and the const keyword just indicates that we're not going to be changing this parameter. I'll show you that it all still works fine. So when I run the code, if I enter Bob here, I still catch that exception. And if I enter a valid value here, I still catch the indexing outside the array bounds. And that's how you can use try and catch blocks to handle the exceptions that are thrown while your code is executing. To recap, in this lecture you learned how we can handle exceptions using a try block and one or more catch blocks. In this lesson, you'll learn about file input and output, which is commonly called file I/O in C++. You'll learn how to do file I/O in your Unreal games as well. File I/O is great because it lets us save and retrieve data that persists beyond a single execution of our console app or our game. So what specifically will you learn in this lesson? You'll learn why we use files. You'll learn how to read from, write to, and append to a file. You'll learn about game configuration data files. You'll learn how to use those game configuration data files in Unreal games, and you'll learn about the Unreal Save Game class. In this lecture, we'll talk about why we use files. So here's our problem, or one of our problems. We want our data to persist after our program finishes running. So while our program is running, we have RAM allocated to our code, so we store values and variables and so on. But once our program finishes running, all that data goes away. So we need a way to save that data after our program is done running. It may also be the case that we have a large amount of data that we need to save. The solution, at least the solution we'll cover in this course, is files. In practice, people also use databases to save and persist data across executions of programs, but we won't cover databases in this course. So what can we do with files? We can read from a file, and that might be reading from a file that our code generated, or it might be reading from a file that was generated from some other code like Google Sheets or Excel or something like that. We can also write to a file, so that means saving data from our program into that file, and we can append to a file, which means adding data from our program to an existing file. To recap, in this lecture you learned why we use files and what we can do with files. Last time, we talked about why we use files and what we can do with them. In this lecture, you'll learn how we can read from a file. So the problem we're trying to solve here is we want to read data from a file so we can use it within our program. The constraint that we'll impose on this is that we're only going to use text files in this course. Binary files are also particularly useful in practice, but you can learn about those on your own as you need them. Let's go see how we can read from a file. The big idea in this example is we have a file that contains data about students, and we want to read that student data in from that file. That's why you see a #include student.h here, and if I open up that header file for my student class, you'll see it just holds the student number, a percentage, and a letter grade for the student. And this is a char, so there are no pluses or minuses. It's just A, B, C, D, or F for the student. I have a constructor for the students where I pass in that student number, percentage, and letter grade. And then I have a getter for the student number. I don't have a setter for the student number because student numbers tend not to change while students are at university or college. But I do have getters and setters for the percentage and the grade because those things do tend to change for students. I also have a getStudentFromString function that I've written that will take in a CSV string and it will extract the student number and the percentage and the letter grade for that student, create a student object, and return that from the function. And then finally the file IO stuff. The first thing we see is that I'm using a class called ifstream, which happens to be in the fstream library, so you need to #include fstream when you use this class. And let's go take a look at the ifstream documentation. As you can see here, the ifstream is an input stream class to operate on files, and that's exactly what we're trying to do. So basically, an input stream is some stream of information that we can use for input. We've been using the keyboard as our default input stream when we use standard cin, but we can use other forms of input streams, including files. As you can see, there's a constructor for the ifstream object. And I'll look at the C++11 documentation, and we'll actually be using one of the initialization constructors where we pass in the file name so that when the ifstream object is constructed, it's associated with a particular file given the file name that we provide as an argument. And there is a default mode of in, which is just what we want when we're reading from a file. So I'm declaring a variable of type ifstream. I've given it the name input, and I'm passing in this argument to the constructor for the data.txt file. Before we do any processing with this file, we need to make sure that we opened the file successfully. There's a function called isOpen, and we can go back to the documentation and we can check to see if the file is open, and this just returns true if the file is open and false if the file isn't open. So if this returns false, the file didn't open for some reason. Not false is true, so we'll go in here and we'll say we didn't open the file for reading, and then we'll return 1 from our main function. We'll just fail our program because the rest of our program needs to read from the file. The next thing I want to do is actually read from the file. That's what this block of code does. I'm going to populate a vector with student objects, and I'll call that students. I have an input string, and the next thing we see is while not input end of file. Back in the documentation, if I scroll down some, we see this end of file function that checks to see whether the end of file bit is set. Basically, what will happen is this function returns true if we've reached the end of the file. We've reached the end of this input stream. If we haven't reached the end of the input stream, this will return false. So for this while loop, if end of file returns false, that means we still have more of the file to read, and not false is true. So we'll go into the body of the while loop and we'll read the input string from our input file stream. Notice that I'm using what's called the extraction operator here, just like we've used with standard cin to put information from the keyboard into a variable. We're using that same operator here that's in the ifstream class to let us use the same syntax to get input from that stream into a variable. So now that I've read a string from that stream, I'll call getStudentFromString with that input string, and then that function returns a student object that I'll push onto the back of my student's vector. Now I will say that I can use this operator because I know the file format doesn't have any spaces on each line. This only goes up to the first instance of a whitespace character, so if I have spaces in my line, I can't use this extraction operator. I need to use getLine instead, which we've seen in the strings lectures when we were talking about getting string input that included spaces. But my file format doesn't include spaces, and in fact, I should show you what that file format is, because the next thing we need to do is get the student from the string, and we need to know the file format before we can do that. And in fact, in general, we need to know the file format before we can process the contents of any file that we're opening up and trying to process. The data.txt file that I'm reading from is in the same folder as my file.io implementation file, and this is the file that has my main function in it. This is true for Visual Studio. It's not true for Xcode, and I've provided a reading for you so that if you're using Xcode, you can figure out where to put the files that you're going to read from as you do file input. This is the file itself, so it has a student number, a comma, a percentage, a comma, and a letter grade. And I have 1 line per student here. So this is a comma-separated value file like we've discussed numerous times, and each of these strings is a comma-separated value string. So let's go take a look at this function. I extract the student number by finding the first comma location and getting a substring from the beginning of the string to that comma location, and then converting that string to an integer. And I put that into my number variable. And then I substring my CSV string, find the next comma, extract the float, and finally I know that the letter grade is just after the last comma that I found that was after the percentage, so I can just grab that single character at comma location +1 and put it into my character grade. And finally I'll return a new student object where I call the constructor with number, percentage, and grade. I will say that this is the standard pattern that I use to process CSV strings, but you can actually avoid doing these substrings if you want to by using one of the other overloads of the find function where you tell it which character to start looking at. So you don't actually have to substring the string as you move along past the commas. That just happens to be the way that I choose to do it. Okay, back in our main function, after we get past this while loop, we're done with the file. We can explicitly close it if we choose to do so. The runtime will actually automatically close the file when the input variable goes out of scope, which will happen in this particular case when our main function ends. So you don't, strictly speaking, have to close the file if you don't want to. If you were writing a longer program where you finished with the file and then your program was going to run for a long time doing other things, you might want to release that file resource so that the operating system or people accessing the operating system can actually access that file. But you don't have to if you don't want to. I like to explicitly close it, so I've done that here, but you should know that's optional. And finally, we print out that vector of students that we've extracted from the file. The only unusual thing that you'll notice here is when I'm printing out the student number, sometimes student numbers have leading zeros in them, and I want all of the student numbers to be displayed with 9 characters, including leading zeros, if that student number actually has a leading zero. So this is how you can do this if you ever need to do this. I can set a fill character for 0, and I can set a width that the numbers get displayed at. And if the student number, that integer, is less than 9 characters long, it will fill the left side with zeros. Okay, so I'll finally run the code. And as you can see, I have student 1 with this information, student 2 with this information, and student 3 with that information. So we successfully read that data from our file and extracted the information we wanted from it and then displayed that information. And that's how you can read from files in C++. To recap, in this lecture you learned how to read from a file, and you also learned that we really need to know how the file is formatted for us to be able to read from it properly. Last time you learned how to read from a file, and this time you'll learn how to write to a file. The problem we're trying to solve here is we need to save data that our program has generated so that it persists or sticks around after our program has finished running. Let's go see how we can do that. Our starting point is the code that we finished with last time, but this time what we're going to do is we're going to write to an output file the list of student percentages and an average percentage. So the big idea is we're reading in all the student information and then we're filtering out the student ID numbers and letter grades to anonymize the data, and then we'll just output to a file the percentages and the average percentage, just so we can do something interesting in the code in addition to the file IO. So we'll come down to our main function. We'll still read in the data from data.text and fill up our vector of students and close that file, but we won't print the students anymore. Instead, we'll print each percentage and calculate the average. Before we do that, let's go ahead and open our output file. It turns out that this is remarkably similar to the way we did input, although our class will be OFStream, O for output, and I'll call it output, and I'll call that file percentages, and I'll make it a text file. It will automatically be a text file. I just am giving it that extension so it will be easily opened in Notepad++ or WordPad or whatever you use. And we're going to do that error check to make sure we opened our output file. So I'll just copy this down here. And this time, of course, I want to check output. And I'll say failed to open file for writing. But if we get past here, we've opened the output file. I'll even go down here and close it. Again, it's optional, just like it was for the input file stream. And we're not printing the students, we're printing percentages and average. And I'll want to keep track of the sum of all the percentages, initializing that to 0. So inside the for loop, instead of printing out to the console, I'll do two things. I'll print the percentage to the output file, and I'll add that student percentage to the sum. The good news is for output file streams, I can use the insertion operator, just like you see here I've been using for standard C out, but I will insert the student percentage into the stream, and I'll also add that student percentage to my running total of student percentages. That's all I need inside my for loop, but I did say I would print the average as well, so I'll output sum divided by however many students I have, which is students.size, and I'll print that to the output file as well. When I run my code, we don't see any output anymore, so we should go confirm that we actually printed to the output file. As you can see, I have percentages right here. This is my text file, and if I open that up, and as you can see, this is a horrible format because I forgot to add new lines when I was outputting to the stream, so let's go fix that now. And that's really straightforward. So I'll run it again, which, by the way, erases the existing file and starts it fresh when I start my output. And as you can see, now I have each student percentage on a single line, and then I have the average percentage on that last line. And that's how you do file output in C++. To recap, in this lecture you learned how to write data to a file. Last time, we learned how to write data to a file. This time, we'll learn how to append data to a file. So the problem we're trying to solve here is we need to save data from our program to a file that already exists. We could have taken the files we've been working with in the previous two lectures, and I could have appended another student to the student data file or something like that, but I wanted to do something different here. I'll show you how to append to a file, and here's the file that we're starting with. These are some incomplete lyrics to a song, and I want to append one more line to these lyrics, so I'm going to go back to my C++ code and do that. I'm still going to use an OF stream object for my output, and I'm still calling a constructor, but this time I'm providing the file name and a mode for interacting with that file. And APP doesn't mean application. People talk about apps all the time, but that's not what it means here. This means append. So we actually have a number of different file modes we can use. And here in the constructor documentation for OFStream, we can see that there are a number of different modes we can use. And we're using append here so that we're adding to the end of an existing file. I make sure I opened the output file fine. Remember, it's always important to make sure you opened a file before you start reading from it or writing to it. And then finally, I'll add one more line to the file, and then I'll close the file, remembering that that's optional, that the file will be closed when my output variable goes out of scope. So I'm going to run this code, And now if we go look at the file, and I need to reload it because it was changed, and you can see that we've added that additional line to the file. And that's how you append to a file in C++. To recap, in this lecture you learned how to append to a file. In this lecture, we'll talk about game configuration data files. The problem we're trying to solve here is we want game designers to be able to tune our game, but we don't want game designers to be touching our source code. That is a recipe for disaster. So the solution to this problem is to use game configuration data files. In other words, let the game designers generate a file that contains data about how the game should be configured, and then we consume that data or read it in so that we can actually use it in our game. There are a number of reasonable formats for those game configuration data files to have. One reasonable format is comma-separated value files. These are really easy to generate from spreadsheets. We can just export CSVs from most spreadsheet programs, but they are kind of difficult to actually read the raw data file. Another format that I've used is extensible markup language or XML files, and those are easy to read the raw file, but you really want to have an XML editor tool rather than having somebody just open up the XML file in Notepad++ or WordPad or something and try to edit the raw XML. Let's go take a look at a few of the game configuration data files that I have used and am using in my professional game development experience. This is the configuration data file for the game I'm currently working on called Balloons Extreme. And as you can see down here at the bottom, I have a number of different worksheets within my spreadsheet, and I'll have a medium level configuration data and a hard level configuration data sheet when I'm done as well. The big idea is that I just fill out the spreadsheet with tuning values and save it as a CSV. And in fact, I will save each of these sheets as a separate CSV that I process within my game. The game configuration data at this point just contains how many levels there are, and there are 2 for my development testing. I do have a separate sheet that describes or will describe each of the data values so that someone who is using this sheet knows what these numbers mean. The easy level configuration data has more information, like how many seconds each level will be, what the maximum number of balloons will be in the level, how much damage those balloons inflict on the player, and the playfield screen width and height percentages. So as we make the playfield wider, that makes it harder. I guess I should tell you the point of the game is that you drive this air shooting vehicle around and you're keeping balloons in the air by shooting bursts of air. So the wider the playfield is, the harder that is to do because there's more area you need to cover. And the less tall the playfield is, the harder it is because you have less time to shoot air at a balloon before it hits the floor, at which point, it destroys and damages you and so on. This other configuration data file I'm showing you is from a game called Battle Paddles, which Peak Game Studios almost finished before we shut down the company, and I am in the long-term process of converting this, but I already know what the configuration data looks like, and there are lots of pieces of configuration data. This is an XML file. So I have formatted this so that someone who wants to edit this XML file knows what each of these values means. This is a comment, and it tells the valid range. And so somebody could, in fact, manually edit this XML file. In practice, before we distribute the game, we will probably build a tool that makes it easier to edit this without actually having to go edit the raw XML. But there are many, many values in this file. So those are 2 examples of game configuration data files. One of those is CSV files that we can export from a spreadsheet, which lots of people are comfortable with manipulating. and the other one is this XML file, which is just another mechanism for capturing game configuration data that we can import and use in our game. I used to use XML files much more commonly, and I have started moving to comma-separated value files just because people are more familiar with manipulating spreadsheets. And for both of these games, we'll distribute the games with the game configuration data editable so that players can mess around with it and see what happens to gameplay when they play with the values in the game configuration data file. To recap, in this lecture you learned that we can use game configuration data files so that game designers can tune our games without actually touching our source code. Although I've used XML in the past, I'm moving toward using CSV files for all my game configuration data files in my current and future games. And I will say that if you don't want to let people manipulate those game configuration data files, you need to use something other than XML or CSVs. You'd probably want to use binary files so that most players would be incapable of messing around with the game configuration data. In the next two lectures, we'll explore how we can import configuration data from a file into our Unreal games using something called a data table. In this lecture, we'll see how to import that data into a data table, and we'll also see how to create a configuration data actor that will provide access to that data to the other classes in the game. In the next lecture, we'll see how those other classes in the game can actually consume that data. We're starting with our fish shooter game from the previous course, and the first thing we want to do is we want to import the data that we have in a CSV file into something called a data table. I'm going to add a folder here in content called data, and I'll go into this folder and I'll try to import a CSV file. And I'll show you what that CSV file looks like. And this is really important for the format of our CSV file. The top row is a set of column names for all the data that's included in each row. And the very first column name has to be name with a capital N. You have no choice there. You have to call it name. And then the rest of the column names are comma-separated values. And this CSV file only has one row of data in it. I've called the row config data, and I've included a fish move amount per second, a fish force magnitude, a teddy move amount per second, min spawn delay seconds, and max spawn delay seconds. And at this point, all of those values are declared as constants in the appropriate classes in my game, but we're going to make it so those classes actually use the data from the CSV file instead. So here's my CSV file. Back here in my data folder, I'm going to right click and say I want to import, and I can navigate to where I put that CSV file. I put it right there in the same folder as I have my Visual Studio solution file and my uProject file for the project. And if I try to open it, I definitely want to import as a data table, but I have to choose the data table row type. And if I click this drop down, I have a bunch of stuff that is by default available in our game, but none of them is actually the definition of the particular structure of data that I have in this CSV file. So I'm going to cancel out of this. What we need to do is we need to define a struct for each row of data in the CSV file. So I'll go to my C++ classes, and I'll just click one to fire up Visual Studio, and now I'll add that struct to my project. So I right click and I say add new item, and I'm going to pick a header file But this is really important. We don't want to put it in the default location that's provided here. Instead, we want to browse to where we have all our other source code. And that's where we're going to put our header file. And I'm going to call it configuration data struct. Now I'm going to go copy all the code for this particular header file, and then we'll be right back. Okay, so I've included the data table header file from the engine because if I'm going to use this struct for rows in a data table, I actually need to inherit from ftable row base. And we're going to talk about inheritance in the next module in this course. So we'll get there, I promise. But this is a rule in Unreal that we have to inherit from ftable row base for any struct that we're going to use for table rows in our data table. So I've called this struct fconfiguration data struct, and I've marked it as a ustruct, and I've said it's a blueprint type, and that makes it so that the data table can actually access this struct. We've seen stuff like this before, although this has a ustruct in the middle here. I have a constructor for the struct, and I have a set of values, and I've assigned default values for each of them. And then I have a bunch of U properties, and I have a U property for each of the columns in the table except for name. I don't have a U property for the column called name, but I have U properties for all the actual data that I have in each row in the table. All of these happen to be floats, and this should all look really familiar to you. So now I have this struct, and by the way, if you look down at the bottom, you can see I'm getting 9,709 errors, but I'm not really. I can build and the build succeeds, so that's just some weird thing going on there. Let's go back to the editor and try re-importing that CSV file again. Here I am in the data folder again, so if I try to import that CSV file again, I'm doing a data table, but this time you can see my configuration data struct appears as an option in the dropdown, so I can pick it, and I applied it. And now if I open up this data table, you'll actually see that I have the column names along the top, and then I have one row of data, and these are all the values that were in the CSV. So we can save that data table, because the data table now holds the rows of data that I have in my CSV file. I only have one row of data, but it holds that row of data in the CSV file. Now we want an actor that we can place on the map that will give us access to that data in the data table. I'll add a C++ class. And as I said, it's an actor. And I'll call this configuration data actor. And again, I've copied over codes to fill in the template that was provided when I created this class. I've included data table again, and I've included the header file for that struct that I defined. I'm going to save a configuration data row for efficiency here in this actor. I don't want to have to find the row in the data table every time a consumer of this class wants to access a piece of data that's available in the data table. So I'm going to just look up the row of data once and save it in a field here. I have a U property here so that I can just use the blueprint editor to populate this field with the data table that you saw me create moments ago. And then everything else is the same, except I've added a getter for the fish move amount per second. In the implementation file, I've set tick to false because I don't have to tick this actor every frame. And here in the begin play function, I'm going to retrieve the configuration data. I'm going to get that row from the data table. So I'm going to call the find row function, which is a templated function, so I can tell it what data struct I want it to find as the row, and that's the struct I defined. I give it a row name, and the name of that one row with data was called config data. And I have to hand in a context string, which I don't really care about, but I have to pass it in as an argument. So I declared it here, and I'll pass it in here. So I'll find that row of data, and I'll put it into my configuration data row. I didn't make any changes to tick, but I did implement the body of the get fish move amount per second getter. And all I need to do is take that configuration data row and access the fish move amount per second and just return that. And that returns that piece of data to whoever asked for the fish move amount per second. I'll build again. And back in the editor, I'll take this configuration data actor and I'm going to turn it into a blueprint. And I'll make sure I put it in my blueprints folder, and I'll call it BP configuration data actor. I'll create the class. And as you can see, I have this U property over here that I can populate with the data table. So let's go get that. And I can just drag that over here, compile and save. And now my configuration data actor has access to that data table that imported all the data from the CSV file. Before I forget, I'm going to add this actor to the scene. Doesn't really matter where he is, but I'll set him at 0, 300, -100. No real reason for me to line it up with the teddy bear spawner, but that's what I did anyway. And I'll save my map. To recap, in this lecture you saw how we can import data from a game configuration data file into an Unreal data table. And even though we didn't really talk about it, the reason that I created a configuration data actor is that we should have a single class that hides from the rest of the classes in our game where that data comes from. So those other classes don't have to care that it came from a file versus just constants or something else, and they can just consume the data from the configuration data actor without knowing or caring where that data came from. Last time, we saw how we could import data from a game configuration data file into a data table, and we also saw how to build an actor that would provide access to that data. This time, we'll see how the other classes in our game can consume that data. So the next thing we need to do is set it up so that the classes that need access to this configuration data can actually get it. And one way that we've already learned how to do that is we can create a gameplay tag and we can tag the configuration data actor so that consumers of that class can find that actor by its tag. So I'll go to Edit, Project Settings. I'll search on gameplay tags. I'll add a new gameplay tag called configuration data actor, and you can make this tag anything you want. I just felt like that was descriptive for tagging the configuration data actor, so I'll add that new tag. Not quite done yet because we now have to open up that blueprint and search for tags and give it that exact tag, configuration data actor. We'll compile and save the blueprint. So now we've tagged that actor so consumers of the class can find it. let's go see how one of them can do that. And we'll do the fish pond because the only piece of data exposed by the configuration data actor at this point is the fish move amount per second. So here in the fish pond, I'm going to comment out this constant because I'm not going to use it anymore. And for efficiency, I'm going to save a reference to that configuration data actor. I don't want to have to look up that actor every time I need the fish move amount per second. So I'm going to just look up that actor once, because remember, finding actors by the tag is a slow process. So let's just do that once. Before I can declare this field, I'm going to have to pound include the configuration data actor header file. And down here, I'll store a pointer to the configuration data actor like so. That means that I want to set this field in the implementation file for FishPond, so let's go do that. And I'll do that in the begin play function. And I'll just copy that chunk of code and then come back and talk about it. So here's the code to store the configuration data, and I realized that I prefer calling the configuration data actor configuration data, so I've come back to the header file and I've changed that name. I also had to pound include Kismet uGameplay statics because I use that right here. So we've gotten all the actors with tag in previous courses, so this is standard stuff. I'm just getting a TRA of pointers to actors that have the tag configuration data actor. I'm making sure that I got at least one, and if I did, I take that first element in the TRA and I cast it to an A configuration data actor pointer, and I put it into my configuration data field. The only other thing I need to do in the fish pond is in my tick function, I no longer have a constant called move amount per second, so instead I'm going to call the getter get fish move amount per second to actually get that value from that configuration data actor. I'll go ahead and compile again. And back in the editor, when I run the game, I'm moving at 100 units per second for the fish. Now, that's what it used to look like. So you may not actually believe that this is getting the data from the CSV file. So let me prove that to you. Let's come back to the CSV file, and I'll change the fish move amount per second to 300 instead of 100. I'll save the file, and here's a really important step. I need to come back to my data table, and you'll see that the fish move amount per second is still only 100, so I need to click this re-import button to re-import the data table. And as you can see, the fish move amount per second changed to 300, so I'll save that, and I'll run the game again. And now the fish is moving much faster. Those are all the big ideas for importing the CSV file, putting it into a data table, setting up an actor that provides access to the data in that table, and then calling a getter on that actor to actually get the data from a consumer of the class. Doing this for the rest of the data in the data table is remarkably similar to what we did for the fish move amount per second. So I'm not going to record me doing all that, but the final code that I provide as a lecture resource will include all those values for all the consumers of the class that need it. Specifically, the fish pond will access the fish move amount per second and fish force magnitude data. The fish force magnitude tells how much force we apply to shoot the fish. The teddy bear pond will access the teddy move amount per second to move at the appropriate speed. And the teddy bear spawner will access the min spawn delay seconds and the max spawn delay seconds to determine the spawning rate of new teddy bears. And if you download the lecture code, you can change the values in the CSV file and watch how the game behaves differently as a result of those changes. I did actually discover a problem as I was finishing up the code when I was refactoring the teddy bear spawner. So in the teddy bear spawner, in the begin play function, I'm saving that configuration data information and I'm starting the spawn timer. And when I start the spawn timer, I'm getting the min spawn delay seconds and the max spawn delay seconds from that configuration data actor. The problem is that because the teddy bear spawner blueprint was placed in the map before the configuration data actor blueprint was placed in the map, the configuration data actor had not yet run its begin play function, which, as you'll recall, actually gets that row of data. So my getter functions for getting the min spawn delay seconds and the max spawn delay seconds in this actor was crashing because I hadn't hooked it up to the data table yet. That was actually an easy fix. All I did was I removed the teddy bear spawner blueprint from the map and then added it back in. And apparently, the way begin play works is the begin play functions are executed in the order in which the actors were placed in the map. So that's important to remember. If you use this technique in your games, you'll want to make sure that you've placed the configuration data actor first in your map before you place anything that might use that configuration data actor. And that lets us initialize the configuration data actor before anybody's actually trying to use it. To recap, in this lecture, you learned how other classes in our game can consume data from our configuration data actor. The game configuration data files that we've been talking about over the last few lectures are really designed to be read-only data that controls how the game runs. We'd also like to be able to read and write data from our game. So the problem that we're trying to solve is we want to persist data between gameplay sessions. Stuff like player progress or inventory contents or cumulative time played or lots of other things. We want to save information about the current game state that we can use later when we start up the game again. The solution to this problem in Unreal is the Save Game class. So what is the Save Game class? It's a class that lets us preserve information across multiple gameplay sessions. So how does Save Game work? When we want to save data, we copy data from the game into a save game object, and then we tell that save game object to save itself to a particular named slot. When we want to retrieve that data, we load into a save game object from that saved data, providing a slot name, and then we copy that data from the save game object into our game so we can use it. Let's go see how this actually works. As usual, we're starting with our fish shooter game, and I've already added all the code that we're going to talk about today, but I do want to show you how to add a save game class. To add a save game class, we do our usual right-click and add a new C++ class, but if you scroll down here, you can't find save game as one of the parent classes that you can pick. That's because it's less commonly used. But if we want to see all the classes we can choose as a parent class, you have to click this checkbox right here, and then you can see all of them. And then you can scroll down to Save Game, and there it is right there. So don't be alarmed if you're doing this and you don't find Save Game in the commonly chosen parent classes. You can still find it by clicking that checkbox. let's go take a look at the save game class that I've already created called Fish Shooter Save Game. This is the header file for that class, and as you can see, we're inheriting from uSaveGame, just as we need to do for a save game class. The only thing I've added to this class is a property. So this numKills field or member is the only piece of data that I'm going to save from the game and load into the game. But of course, you can have as many pieces of information as you want to save and load to save the game data between multiple gameplay sessions. Here's the body of my Fish Shooter Save Game class, and as you can see, it's just the default code that gets generated when I add a class. The place where we actually use this class is the game HUD, because remember, the game HUD is keeping track of how many kills we have in the game. In the header file for the game HUD, I've pound included my new save game class, and I've added a field for a pointer to that class so I don't have to retrieve it every time I need access to it. And I've added a constructor for the game HUD, which we didn't have before, but there's stuff that we need to do when the game HUD is created. So I've added this constructor, and those are the only changes to the header file for the game HUD. In the source file or implementation file, I've added some pound includes here, and here's the constructor that I wrote. The first thing I do in the constructor is I try to load the saved number of kills. Remember, we're saving this information and I want to load it up if it's available. This is my pointer to my save game class, and I'm calling uGameplayStatics load game from slot. And I need to provide two arguments when I call this function. I need to provide the name of the slot, because we can have multiple save game slots. We don't have to just have one. And I provide a user index. And I'm just going to use 0 for the user index. When this is returned, I need to cast it to my class name, rather than using the style of casting that I've shown you before, where I would say Fish Shooter Save Game asterisk inside parentheses here. I'm showing you that there is in fact a templated cast function in Unreal Engine that will also do that typecast for us. And I'm using that different syntax here just to extend your knowledge of the capabilities provided in Unreal Engine. I will say in C++ we actually have static cast and dynamic cast templated functions as well. And those are also reasonable and sometimes even preferable ways to cast from one object to another. In any case, I've tried to load the game from the slot and put it into this field, and then I check to see if save game instance is not a null pointer. If it's not a null pointer, that means we successfully loaded the game from the slot. So I'll just set kills in the HUD to whatever the value of numKills was that was saved. However, we might have save game instance as a null pointer if there isn't a game saved in the Fish Shooter save slot yet, and that would certainly happen the first time you run the game. So in that case, I initialize kills to 0 and I create a save game object. So I've now created an object and cast it to the appropriate type and put it into my field. So no matter what, when I get to line 30, save game instance holds a valid pointer to my save game object, and the kills field here in the HUD has been set appropriately. I did add some extra code here, and as you can see it says development use only. And this resets the saved numKills to 0, and I say comment out when not needed. So the big idea is I was playing around with this and making sure it worked, but I wanted you to be able to see a starting point of numKills of 0. So I needed a way to reset it to 0. So this was just a couple of lines of utility code that I could use to set everything back to 0. It doesn't delete the game that's saved into the Fish Shooter save game slot, but it does set it back to 0. So this is all about loading the saved game from the save game slot. And by the way, I'm loading the game from the slot synchronously, but if in fact you are going to load a large amount of saved game data, there's an asynchronous function to do this as well, and you can just start it loading and then get called back when it's done. And that will be helpful if you're loading a bunch of data because you won't make your game lag while you're loading the data. The place I'm going to save information is when I add a kill to the kill counter. So down here, when we add a kill, we increase the value of the kills field here in the HUD. And I also want to save the number of kills. So I set that field in my save game object, and then I say save game to slot. I provide a pointer to the save game object I want to save. I provide the slot name, and I provide the user index. So this is where I'm writing back to disk, saving the game because the number of kills changed. And again, there's an asynchronous version of this function available if you're saving a whole bunch of information and you don't want to lag your game. You can just call the asynchronous version and then you'll get a callback when it's done saving the game to the slot. And that will help you prevent making your game drop frames. But we don't have to worry about that here. We're just saving one value and it happens pretty quickly. So that's it for the code we need to write to actually make this work. So let's go see how it looks when we run our game. The first time we run our game, you'll see I have kills of 0. And let me kill a teddy bear. Oh, I'll kill a couple of them. And now I'll stop. So I've stopped running the game. That's the end of my gameplay session. But when I run my game again, you can see it read in that saved game, and now I have 2 kills, and that's great. And I'll get one more kill. Ow! And stop again, and that's the end of a second gameplay session. And when I run again, you can see kills is initialized to 3, which was the number of kills that were saved in the save game. To recap, in this lecture you saw how we can use a save game object to persist data with read-write access across multiple gameplay sessions. What will you learn in this lesson? You'll learn what inheritance is, you'll learn how inheritance works, and you'll learn how to implement inheritance in C++. In this lecture, we'll talk about what inheritance is and why it's useful. So what is inheritance? Inheritance is a way for us to structure our code so multiple classes can share common fields or member variables and functions. And this is really useful. It makes our code much more compact because we don't have to duplicate code across multiple classes. And it also makes our code easier to maintain. So when we decide we need to change some of that common code or fields, then we can just change it in one place instead of in all the places we copied it. Even though multiple classes share these commonalities, each class can also implement class-specific data and operations to meet the needs of that class. Let's take a look at an example. This is a unified modeling language, or UML diagram, of 2 classes, a car class and a dragster class. We'll start by talking about the car class, and all cars have an engine, or with electric cars they have a motor, but they have something that provides propulsive force to the car. And all cars, at this point anyway, have wheels as well. So those fields for a car will be common to all cars. We have a number of functions for the car. We have a destructor for the car, and we talked about destructors back in the console app classes lesson in the previous course. And here, when we implement inheritance, we definitely want to implement destructors in our classes. We also have a constructor for a car, so we can actually create a car object. And then we have a variety of functions that would apply to all cars. We want to be able to accelerate the car, we want to be able to turn the car, and we want to be able to get the current velocity of the car. A dragster is a specialized form of car. So a dragster has all those characteristics that a car has, both the fields or member variables and the behaviors or functions, but it also has some specialized stuff. It has whether or not a parachute has been deployed, because dragsters regularly have parachutes to slow them down, and it has a deploy parachute function that lets us deploy the parachute on the dragster. All cars don't have parachutes, so it wouldn't make sense to include that field and function related to parachutes in the car class, but it does make sense to include it in the dragster class. We also have a constructor and a destructor for dragsters, and as I said, that's important when we're implementing what are called class hierarchies, a hierarchy of classes where car is at the top of this hierarchy and dragster is at the bottom of this admittedly small hierarchy. It's always the case that classes that are higher up in the hierarchy are more general, and classes that are further down the class hierarchy are more specialized. The way we show inheritance in a UML diagram is with this arrow, with the unfilled triangle at one end, and the unfilled triangle points to the parent class. So regularly we talk about these two classes as car would be the parent class and dragster would be the child class. You'll hear people talk about car as the base class and dragster as the derived class, and you might even hear people talk about car as the superclass and dragster as the subclass. In any case, I'll usually call them parent and child, but this arrow is the way we show that parent-child relationship. To recap, in this lecture you learned that inheritance is a way for us to structure our code so multiple classes can share common fields and functions while still implementing class-specific fields and functions as necessary. You also learned that the higher up we are in the class hierarchy, the more general the classes are. Alternatively, you can think the lower down we are in the class hierarchy, the more specialized those classes are. In this lecture, we'll implement inheritance in a C++ console app. This is the class hierarchy for the inheritance we're going to implement. At the top of the class hierarchy, we have a family member class that implements a constructor, a destructor, getters and setters for height and weight, and a have fun function. We have a gamer child class that implements a constructor, a destructor, and its own version of the have fun function. And we have a geek child class that only implements the constructor and destructor. Let's go see how we can implement this class hierarchy in our code. We'll start with our implementation of the family member class, the top of our class hierarchy for this example. Our family member class has a couple of private fields or member variables called height and weight. We have a constructor where we pass in the height and weight and use that to create our family member object. I have a destructor for family member. Remember back in our console apps lesson from the previous course, I said that when we got to inheritance, it would be important for us to implement destructors. Well, here we are in inheritance, and it is important for us to implement destructors. And we'll talk about the need for this virtual keyword in front of the destructor when we talk about polymorphism in the next lesson. We have a getter and a setter for height, a getter and a setter for weight, and a function called have fun that makes the family member have fun. we have marked this function as virtual because we know that one of our subclasses or child classes is going to want to replace whatever functionality we have in our have fun function here with custom have fun behavior in the child class. Implementing a function with the same function signature in the child class is called overriding the function if we've marked this function here in the base class or the parent class with the virtual keyword. If we don't mark it with the virtual keyword, then the child class function with the same function signature actually hides this one. But in general, we're going to find that we want to mark our functions that might have overridden behavior with the virtual keyword so that we can actually use the overriding mechanism. In the implementation file, you can see our constructor is as expected. We use that member initializer list to initialize our height field to the height parameter and our weight field to the weight parameter. Our destructor doesn't do anything, though it will when we start talking about polymorphism. The getters and setters are just as you would expect. And for a family member, the default having fun behavior is I'm writing code, because that's what most family members should do to have fun. So this is our family member class, and it's going to serve as the root of our class hierarchy. But as I showed you in the UML diagram, we're going to have two child classes that use family member as a parent class. We'll look at gamer first. Notice we have to pound include the header file for family member because we're inheriting from family member. You've seen this before. This is the new syntax that says family member is my parent class. Specifically, this part says family member is my parent class, and this base class access specifier controls our access to the protected, which we haven't talked about yet, and private member variables and functions of our parent class. If we use public for our base class, then everything stays the way it was in our base class. Public member variables and functions stay public, protected member variables and functions stay protected, and private member variables and functions stay private. If we put protected here, then public member variables and functions in our base class become protected, and protected member variables and functions stay protected. And finally, if we put private here, public and protected member variables and functions become private instead. There are lots of cases where you might want to use protected and private, but throughout the examples in this course, we're always going to use public as our base class access specifier. You should think about this as in our gamer object, we have a family member sub-object. And putting this base class access specifier here determines how we access the member variables and functions in that sub-object. We have our gamer constructor, we have a gamer destructor, and we're overriding have fun. And we say we're overriding have fun by including the override keyword. This function is still a virtual function because the function in the base class is a virtual function. You can mark it as virtual as well if you want to be particularly clear about the fact that it stays a virtual function. This is a matter of taste. Seeing the word override already tells you it's a virtual function, and understanding how C++ works would tell you that this will be virtual as well. If you want to just be really explicit about it, you can just put the virtual keyword there as well. Whether or not we mark this function with the virtual keyword, if we were to derive another class from gamer, that other class could also override the have fun function. In our gamer implementation file, you can see that our constructor here is actually calling the family member constructor. It's calling the constructor for our parent class. And In general, you're going to want to do that because you want to have your parent class sub-object that's contained in our gamer object get initialized in an appropriate way. And that's what the constructor for family member does. So the first thing we want to do is call that constructor to initialize our sub-object. If we had other things that we wanted to do in the constructor, which we'll see in the next lecture, then we would then put it in the body of this constructor, but we don't have anything else we need to do in the gamer constructor, so we'll just leave that body empty. We have a destructor that does nothing, and here's where we override the behavior of have fun, because the gamer object wants to say, I'm playing a game, rather than I'm writing code. And I will freely admit, I know from personal experience that you might like to both write code and play games, but for this example, we'll say a gamer doesn't like to write code, they like to play games to have fun. Notice we don't put virtual here in our implementation, and we don't put override in our implementation. Those go in the header file, not here in our implementation file. The last class we have to look at for this example is geek. So the header file for geek says, I am a child of family member, and I'm using that public base class access specifier. I have my own constructor and I have my own destructor. I'm not overriding the have fun function. And in my implementation file, I call the constructor for my parent class, and then there's nothing else I need to do in this particular example in my constructor, and my destructor does nothing. So how does this all work? Here in our main function, I'm going to create 3 different family members. I'm creating a family member object and putting it into a family member variable. I'm creating a gamer object and putting it into a gamer variable, and I'm creating a geek object and I'm putting it into the geek variable. And then finally, I tell each of those variables to have fun: the family member, the gamer, and the geek. When I run my code, you can see that our base class, or our parent class, the top of the class hierarchy, the family member says I'm writing code. The gamer, remember, overrode the have fun function, so the gamer object prints I'm playing a game. And finally, the geek object, which didn't override the have fun function, just inherits that function from the parent class. So when we call have fun on a geek object, it doesn't have an override of that function, so it goes and finds the function in the base class sub-object and executes that function. And that's why it says the same thing as the family member object says when we tell the family member to have fun. To recap, in this lecture you learned how to implement inheritance in a C++ console app, and you also learned how a child class can override a function it inherits from its parent. In this lecture, we'll implement another example of inheritance in C++. Here's the class hierarchy we're going to implement, and this is sort of a canonical inheritance example that computer scientists use. The root of our class hierarchy, or the top of our class hierarchy, is a bank account class that has fields to keep track of the balance in the account and vectors for the deposits made to and the withdrawals made from that bank account. We have a constructor and a destructor, getters for those 3 fields, a way to make a deposit, a way to make a withdrawal, a function that prints information about the account, and a set balance function that we'll talk about in more detail when we're looking at the code. We have a checking account child class that inherits all that stuff from the bank account, but also stores a vector of the checks that have been cashed. It implements a constructor and a destructor, a getter for that vector of the checks, a way to cache a check, and it overrides the print function to print information about the checking account. Finally, we have a savings account child class that inherits everything from its parent bank account class, but also has a field for an interest rate, implements a constructor and destructor, provides a mechanism to accrue interest, and also overrides the print function. Let's go look at the code. Again, we'll start with the top of our class hierarchy. So this is our bank account class. As you can see, I have some private fields or member variables. I have a balance, I have a vector of deposit amounts, and I have a vector of withdrawal amounts. I have a constructor that starts our bank account object with an initial deposit. I have a destructor for our bank account. We have a getter for the balance in our bank account, but I don't have a setter for the balance. We don't want to let a consumer of the class directly change the balance. We want them to change the balance by either making deposits or making withdrawals. We can get a vector of the deposit amounts and we can get a vector of the withdrawal amounts. We can make a deposit by providing an amount to deposit. We can make a withdrawal by providing an amount for the withdrawal. And we can print the account class and balance. And this is just a utility function that I've provided so that we can get some reasonable output when we run the code. Notice I've marked the print function as virtual, so my child classes can override the print function to print class-specific information about the child class rather than the parent class. I do have a protected function called setBalance. And I'll show you why I've done that soon, but a member function or a member variable that's protected is only accessible to the bank account class and child classes of the bank account class. No other class can access this setBalance function, only bank account and child classes of bank account. In the implementation of bank account, in my constructor, I'm going to call my makeDeposit function with the initial deposit because, as we'll see soon, I do some work in the makeDeposit function to validate the deposit that's being made, and there's no reason to duplicate that code. Opening the bank account with a particular initial deposit is just making a deposit to the bank account. My destructor still doesn't do anything. Remember, we'll do stuff in our destructors when we get to polymorphism. I can get the balance, that's pretty straightforward. And I can get to the deposits and withdrawals. So here's that makeDeposit function. We want to make sure that the deposit is greater than 0. If it is, we'll increase balance by the amount and we'll add that amount to our deposits vector. If the amount is less than or equal to 0, we'll print a message that says deposits have to be larger than 0. Our makeWithdrawal function does a little more error checking because we have to check both that the amount of the withdrawal is less than or equal to the current balance in the account and that the amount is greater than 0. If the amount were less than 0, we'd be providing a negative amount, and we'll see here we subtract the amount from balance. So if we could provide a negative amount, we could call makeWithdrawal with negative amounts and increase the balance in our bank account. And that's obviously not the way this should work. So if I have a valid amount, I deduct that amount from the balance and I push the amount onto my withdrawals vector. And because I want specific error messages based on how the amount validation failed, if the amount is greater than balance, I want to say there's not enough money. And if the amount is less than 0, I want to say withdrawals have to be larger than 0. That's just providing specific error messages based on what the error actually is for the invalid amount. Printing the bank account, I'm just going to say it's a bank account and I'll print the balance. And here's that protected function that can only be called by this class and child classes of this class. And when I say child classes, they don't have to be direct children. They could be further down the class hierarchy. But if you can reach bank account from wherever that class is, then they can call this protected function. As long as we haven't set a base class access specifier somewhere in the middle to be private, but we're not going to do that in this class. Okay, we're validating the amount for setting the balance, because even though we trust our children, we want to make sure they're not doing anything silly. So we want to make sure that setting the balance is setting it to an amount that's greater than or equal to 0. If it is, we'll just set the balance to that amount. If it's not, we provide an error message that says balance amounts have to be larger than 0. Okay, so this is our base class. This is the root of our class hierarchy. Let's look at our checking account next. Remember, our checking account is a child of bank account, and I'm just going to keep using the public base class access specifier. We have an extra field here that we don't have in our parent class, and that's a list of check amounts. Now I will admit that we'd probably actually have a check object that had a check number and the amount and who it was made out to and all those things, but I'm just keeping this example simple to let us focus on inheritance. So we do have an extra field or a member variable in this child class, the vector of checks. I have a constructor, I have a destructor, and then I have some new functionality that wasn't in our base class. I want to be able to get the vector of checks, and I want to be able to cache a check, and I want to be able to override print. And we'll see how I override print when we look at the implementation file. This is as you'd expect. I'm just calling the parent constructor here within the child class constructor. The destructor doesn't do anything. This returns the vector of checks. Caching a check, we validate the check amount. Here's where I'm using that protected function. So what I'm doing here is I'm getting the current balance and I'm subtracting the amount that this check is for, and then I'm setting balance to that new balance. And I push the amount onto my vector of checks. Some specific error messages in case the check amount isn't valid. And here I've overridden the print function in my parent class so that I can say checking account and call getBalance. Now there is another way to give the checking account object access to the balance in bank account. I could come up to bank account, and instead of having this balance be private, I could make it protected. And if I do that, here in my checking account, we'll just look at cashing a check. Instead of this, I can say balance minus equal amount. And this will compile fine, and it will work properly, and so on. However, there is a philosophy that says that even child classes shouldn't be allowed to manipulate directly the member variables in the parent class. And as you can see in our setBalance function, we actually do some validation here to make sure that the balance isn't getting screwed up, because the bank account class is responsible for the data integrity contained in itself as an object. If we do this, then our parent class doesn't have that control over the data integrity of its fields or member variables. So although this works okay, it's generally better to provide protected setters in the parent class that the child classes can call to manipulate those member variables in the parent class. I'll actually show you that if I make this private again, I can no longer compile because the error message says I can't access a private member in bank account. Even from within the child class, that field is private to the bank account sub-object that's contained in my checking account object. So we'll get rid of this code and go back to using our protected setBalance function. And finally, let's look at savings account. So our savings account also is a child class of bank account, also with a public base class access specifier. We have an additional field for the interest rate. Our constructor looks a little different because now it has two parameters, the initial deposit and the interest rate for the account. We have a destructor, we have a new function that lets us accrue interest, and we're overriding the print function as well. So if we look at our implementation file, we can see that the savings account constructor calls our parent constructor and actually does some work in the body of the constructor. So here's an example of a child class constructor initializing the base class subobject and then doing some additional work, specifically validating the interest rate. And if the interest rate is valid, we set the interest rate field to the interest rate parameter. And if not, we provide an error message. Accruing interest, we get the current balance, and then we take that current balance and we add current balance times interest rate to it. And this is our new balance. So we call that protected set balance function to set our balance in our bank account subobject. Overriding print so I can say savings account. And finally, here in our main function, I'm creating a bank account object, a checking account object, and a savings account object. I'm telling each of them to print itself. Then I'm depositing $20 into each account. And remember, bank account implements the make deposit function, and checking account and savings account inherit that function. We print them again. And there are some class-specific things we do here. So we know our checking account class exposes a cash check function, so we call that. And our savings account class exposes an accrue interest function, so we do that on our savings account. And then we print each account one more time. When I run my code, as you can see, the first three lines are calls to the print function on our bank account object, our checking account object, and our savings account object. So they each have a different message they print, and then they print the balance in those accounts. For the next group of output, we made a deposit of $20 to each of those objects. So now they each have $20 more. And then finally, the bank account stayed at $220. The checking account, we cashed a $20 check, and the savings account, we accrued interest. To recap, in this lecture, you got more practice with inheritance in C++. You learned about the protected access specifier, and you also learned that it's really best practice to have child classes work through a setter to change fields in the parent class rather than accessing an inherited field or member variable directly. In this lecture, we'll talk about how inheritance works in our Unreal Engine games. So most of the time, when we're creating a new C++ class in our game, we pick one of the pre-existing Unreal Engine classes as a parent. So some examples include actors and pawns and player controllers and HUDs. We've seen lots of different parents that we've selected as parents when we create new C++ classes. What does that have to do with inheritance? What we know about inheritance is that our custom classes then inherit the member variables and the functions that are in the Unreal Engine class that we selected as a parent. We also know that we can override those parent functions that have been marked as virtual, so we can implement our custom behavior in the C++ classes that we've created while still inheriting the member variables and functions from our parent. To recap, what we've learned is inheritance in polymorphism, which we'll talk about soon, makes it so that our custom classes work just the way we want them to, as long as we code them properly in our Unreal Engine games. In this lecture, we'll talk about abstract classes. What is an abstract class? It's a class that can't be instantiated, but it can be the parent of other classes in a class hierarchy. We know we have an abstract class if we have one or more pure virtual functions in the class. So what's a pure virtual function? It's a function that we define in our header file, but we don't provide an implementation of the function in our implementation or source file. And of course that means we need to define the function using a particular syntax. Let's look at an example where this feature might be helpful. In this class hierarchy, we have the talker class as the root of the class hierarchy, and we have a happy talker and a sad talker. And each of those child classes will print either a happy message or a sad message. What that means, though, is that the talker class can't really provide a reasonable body for the say something function. It shouldn't say something happy because it'll be wrong half the time, and it shouldn't say something sad because that will be wrong half the time. What we really want is we want the talker class to not have to implement the body of that function, but to say any class that can actually be instantiated below me in the class hierarchy needs to implement their version of the say something function. So we're going to enforce the requirement that those classes have a say something function without actually implementing the body of that function in the parent class. Let's go see how this particular class hierarchy looks when we implement it in code. We'll start by looking at an implementation that doesn't use a pure virtual function, so this isn't an abstract class yet, but I'll show you why we really want this to be an abstract class. So here in my talker header file, I just have a virtual function called saySomething, and then in my implementation file, I implement the body of that function, but it's an empty body. In my happy talker header file, I'm overriding that saySomething function, and in my implementation, the saySomething function says I'm so happy. In my sad talker header file, I'm overriding that saySomething function, and of course both sad talker and happy talker are child classes of the talker class. And then in the implementation file, I'm saying I'm so sad. In my main function, all I'm doing is creating a happy talker object, a sad talker object, and telling them both to say something. When I run my code, that's what happens. The happy talker says it's happy, and the sad talker says that it's sad. The thing that we don't like about this implementation is this, because we know in the talker class that the talker class has no reasonable body of the function to implement. That's why I left it empty, and we know it will never even get called, or should never even get called. So we want to get rid of this, because it's extra code that we know we don't want to use. Unfortunately, if we do that, we get an error message down here from the linker that says that it couldn't find a symbol for the talker saySomething function because we never implemented the body of the function. So we can't just get rid of it. We can, however, get rid of it and come over to the header file and turn this virtual function that we have into a pure virtual function, which means that we're defining what the function needs to look like, but we're not implementing a body for it. The syntax for turning this into a pure virtual function is pretty straightforward. All we have to say is equal 0, and that turns it into a pure virtual function. I can successfully compile now, and running the code has the exact same behavior as before. So that's a win right away. We don't have to implement the body of this function, leading to extra code that we know will never be used, but there's actually another win as well. Let's say that my happy talker class, which says it's a child class of talker, doesn't actually implement saySomething. So I will comment that out there, and I'll comment it out here. When I try to compile, I get an error message here in my main function that says I can't instantiate an abstract class. That's why it's showing up right here as I try to instantiate an abstract class. So remember I said that abstract classes can't be instantiated. But you could certainly be asking yourself, why does the compiler think that Happy Talker is an abstract class? We didn't include a pure virtual function in Happy Talker, so why does it think that class is abstract? Well, the reason is because our parent class has a pure virtual function and we didn't override it. That means that that pure virtual function still hasn't been implemented. And if we have a function that is supposed to be provided, but it hasn't been implemented yet, then Happy Talker also is an abstract class. We only get a non-abstract class once we reach a class that has implemented everything that is required in the class hierarchy. And in this particular case, Talker requires all its child classes or all its non-abstract child classes to actually implement the say something function. So this is another really powerful feature of abstract classes, is once we specify here that all the non-abstract classes below us in the class hierarchy have to implement this function, we're enforcing a requirement for behavior in our children, as we often try to do in real life. We're enforcing a required behavior in our children, and if our children don't specify or meet that behavior, then they don't get to be instantiated. So that is really helpful, because as we move our way down the class hierarchy, if we forget to implement a function that's required, then the compiler will help us by giving us an error message and reminding us that we actually have to implement that. So I'll uncomment this again because I want to give you clean code that actually works. And we'll run it one more time. And it behaves as expected. So that's how we can implement abstract classes in our code. To recap, in this lecture we learned we can use abstract classes to specify functions that are required in our child classes without having to implement the body of those functions in our abstract class. And I will say that using abstract classes as appropriate leads to much better object-oriented designs. What will you learn in this lesson? You'll learn what polymorphism is, you'll learn how polymorphism works, and you'll learn how to implement polymorphism in C++. In this lecture, we'll talk about what polymorphism is and why it's so useful. So what is polymorphism? With polymorphism, a particular function call behaves differently, takes different forms based on the object on which it's called. And that feels really abstract, and concrete examples will really help us understand why polymorphism is so useful. So we'll see polymorphism in action with the have fun functions for family members and the print functions for bank accounts. To recap, polymorphism lets different objects in a class hierarchy respond to function calls in class-specific ways. One important point is polymorphism only works in C++ on pointers to objects or references to objects. So we don't get polymorphism when we just have variables holding objects. We need to use pointers or references to objects to get polymorphism. And we'll see how that works in the next few lectures. In this lecture, we'll see how polymorphism works on our family field hierarchy. And just as a reminder, here's what that class hierarchy looks like. So let's go start exploring how polymorphism works. Our family member, gamer, and geek classes are almost the same as they were in the inheritance lecture. I'll show you the difference when we start talking about the importance of virtual destructors. But for now, the destructors still do nothing. So the difference in this example is an actual demonstration of polymorphism here in the main function. Remember, we only get polymorphism through pointers and references to objects. So I'm building a vector of unique pointers to family members. And I'm calling that family members. And the important idea here is I've set the type for the unique pointers to be pointers to family member. And because of the is-a relationship between gamers, geeks, and family members, a gamer is a family member and a geek is a family member. So I can add a pointer to a gamer to this vector of pointers to family members, and it works fine because a gamer is a family member. So I've got a vector of pointers to family members, and I'm pushing a unique pointer to a family member object, a unique pointer to a gamer object, and a unique pointer to a geek object into that vector. So at this point, the vector has three different kinds of objects. It's important to understand that the static type for all of the elements in the vector is family member. So statically, with compile time information, each of these elements is a family member. So that's the static type of each of those pointers to objects. However, as you can see here, I'm actually adding a pointer to a family member, a pointer to a gamer, and a pointer to a geek. So the dynamic type of each of these pointers is dependent on the object that I created. They all have to be in the family member class hierarchy for this to work, but the dynamic type of each element is not necessarily the same as the static type. The dynamic type of this pointer to an object is of course the same as the static type, but the dynamic type of this pointer is actually a pointer to a gamer object, and the dynamic type of this pointer is actually a pointer to a geek object. So the distinction between static types and dynamic types are an important component of understanding how polymorphism works. Now I'm just going to walk my way through the vector using the standard for loop and have each of those elements have fun. And of course, because each element is a pointer, I'll use arrow notation to call the function on that object. And when I run the code, you'll see that the family member says I'm writing code, the gamer says I'm playing a game, and the geek says I'm writing code. And that's polymorphism at work. Each of these elements in the vector is a family member, but the behavior of calling the have fun function on each element is dependent on the dynamic type of the object that's pointed to for that particular element. That's the big idea. The power of polymorphism is that we can do this, and depending on the dynamic type of the object the pointer points to, we can get the appropriate behavior from that pointed to object. Let's talk about virtual destructors. So I've changed the destructor in the family member class to not be virtual. I removed that virtual keyword. And now we'll go to the destructor and say I'm destroying a family member object. We'll go to the destructor in gamer and it will say destroying gamer object. And we'll go to the destructor in geek and say I'm destroying the geek object. What you might expect, because of the dynamic types of each of these elements in the vector, is you might expect one destructor message from each type of object. When I run the code, that's not what I get. I get destroying family member object for all of them. And the problem is that I need to say that the destructor is actually virtual at the top of my class hierarchy. As soon as I do that, I get the appropriate messages. Now you might wonder what's going on here. So the destroying family member object is destroying the family member. The next message is I'm destroying the gamer object, but automatically the runtime is also going to go destroy that family member sub-object that's in the gamer object. So that's why we're getting two messages for the gamer object. But the good news is we're actually calling the destructor for the gamer object, and then it goes and calls the destructor for that family member sub-object. And we see the same behavior for the geek object. We're actually calling the destructor for the geek object because we marked that destructor as virtual in family member, and then it destroys the components of the geek object that are specific to the geek, and then destroys the family member sub-object in that geek object. So that's why marking our destructors as virtual at the root of our class hierarchy is really important. As I've mentioned before, it doesn't hurt to mark the gamer destructor as virtual and the geek destructor as virtual as well. So I like to do that just to be very clear that the destructors are virtual all the way down the class hierarchy. To recap, in this lecture we saw how polymorphism works on our family member class hierarchy, and we also saw the importance of virtual destructors. But remember, we only need to include destructors in our code if we need to do special cleanup when our object gets destroyed. Otherwise, we can just use the default destructor that C++ provides to us. In this lecture, we'll see how polymorphism works on our bank account class hierarchy. As a reminder, here's what that class hierarchy looks like, so let's go take a look at the code. The bank account, checking account, and savings account classes are identical to the classes I showed you in the inheritance lesson, but we're going to demonstrate polymorphism here with these bank account classes. Here in the main function, I have a vector of shared pointers to bank accounts, and then I'm adding a shared pointer to a bank account, a checking account, and a savings account. And remember, I can do that because a checking account is a bank account and a savings account is a bank account. I do a for loop to tell each account to print itself, and we're going to see polymorphism here because the appropriate print function will be executed based on the dynamic type of accounts I. Then I deposit $20 into each account and I print those accounts again, and we'll come back to this class specific stuff momentarily. There's a big chunk of code there that does something new for us, and then we print each account one more time. So I'm going to run the code, and you can see the first chunk of output is that polymorphic execution of the print function based on the dynamic type of the element in the vector. Then I add $20 to each of them, and then the second group of output shows that each of them has an additional $20 in it. And then the final chunk of output shows some class-specific behavior for the checking account and savings account. And that's something new that I wanted to show you. We know we have a vector of bank accounts, but it might be the case that we want to use a child class function on an element of that vector. We can't automatically do it. Remember, the static type is determined by the compiler at compile time. The static type for every element is a bank account, but the dynamic type might be a type of one of the child classes that has special behavior that we want to access. So what I do here is I'm doing a for loop, and then I'm using a new operation here called type ID, and that will return to me something called a type info object. What I'm doing here is I'm saying, what is the type ID for the current element of the vector, but I'm dereferencing the pointer. So I'm getting the type ID of the actual object that's pointed to by this pointer. It might be a bank account, it might be a checking account, or it might be a savings account. But by dereferencing the pointer here, I can retrieve the type info for the actual dynamic type of the object. I can then compare it to the type info for checking account, and if those are the same, then the dynamic type of the current element in the vector is a checking account. Next, I do something called a dynamic pointer cast. This is a typecast. And I take this element and I typecast it into a pointer to a checking account. And I need to do that so that I can then call the cast check function on that pointer. Because if I don't cast it to a checking account, the static type is still bank account, so I can't call a cast check function on a pointer to a bank account object because bank account doesn't expose a cast check function. This is the documentation for dynamic pointer cast, and this is for shared pointers. We can use the dynamic pointer cast function on shared pointers. And I'm a big fan, as you already know, of smart pointers, so I wanted to use a smart pointer here, and I wanted to use the dynamic pointer cast, the appropriate function to use for a shared pointer. As you can see here, there's also a dynamic cast, not dynamic pointer cast, but dynamic cast function that actually will convert pointers and references to classes up, down, and sideways along the inheritance hierarchy. And we're trying to do a conversion down the hierarchy, right? We're trying to go from bank account to checking account. We could use dynamic cast as well, but I wanted to use the appropriate function for shared pointers. You'll see dynamic cast all the time when people want to do dynamic casts, particularly when they're interacting with raw pointers, not smart pointers. Similarly, if the dynamic type of the current element in the vector isn't a checking account, I then check to see if it's a savings account. And if it is, I do a dynamic pointer cast of that element to a savings account so that I can accrue interest on the object that's pointed to by that element in the vector. So that's how I can get class-specific operations done on particular elements in the vector as appropriate. We'll run the code one more time. And that's why in that bottom group of output, we didn't try to do anything to the first element in the vector. But for the checking account, you can see when we discovered that that element was a pointer to a checking account object, we cashed a $20 check against that object. And when we discovered that the third element was a pointer to a savings account, we accrued interest in that savings account object. To recap, in this lecture you learned how polymorphism works on our bank account class hierarchy, and you also learned that we can't call unique child class functions on elements of a collection of the parent class unless we do typecasting, and we saw how we can do that. This is a different kind of lesson from what you're used to, because in this lesson we'll go through a small game that uses many of the inheritance ideas that you've learned about in this module. Let's go see how the game works first. First I'll show you the full game, and then I'll show you how each component of the game works. So when I run the game, I have a launcher and I can shoot brains. This is a zombie launcher, and the yellow teddy bears randomly drop good or bad loot, and the green teddy bears never drop loot. And as you can see, I have purple teddy bears that will sometimes drop good loot and sometimes won't. So that's the game, and I just keep playing, and my score gets adjusted based on what happens in the game. So let me put in a piece of good loot into the game. And as you can see, when I shoot good loot, it just disappears, and I scored 50 points for shooting good loot. I'll get rid of the good loot, and I'll add a piece of bad loot. And I'll run the game. And when I shoot the bad loot disappears, and I score 10. And by the way, if a teddy bear runs into the bad loot, you'll see the teddy bear gets destroyed and I lose 50 points. So that's why the loot is bad, because it kills teddy bears, which means I can't shoot those teddy bears to get points. I'll replace this bad loot with good loot. And if a teddy bear runs into good loot, I score points as though I'd shot the teddy bear, but I still have an opportunity to shoot the teddy bear even more. This green teddy bear that I added is a no loot teddy bear actor, so he never drops loot. I just shoot him, and I get 20 points for shooting the green teddy bears. The purple teddy bears randomly decide, with a 50-50 chance, that they'll either drop good loot or they don't drop anything. So we'll see if I get lucky on this one when I shoot him. And I did not. He did not drop any loot. So that's a random good loot teddy bear. He randomly decides whether to drop nothing or to drop good loot. The final teddy bear is a random good bad loot teddy bear. So he will drop either good loot or bad loot. He always drops something, and half the time it's good loot and half the time it's bad loot. And there you go, he dropped good loot. Oh, I got some other ones here, so let me see if I can get him to drop a bad loot. And there you go, he dropped bad loot as well. And as you can see, that bad loot kept killing teddy bears. So those are the components of the game and the full game in action. So starting in the next lecture, we'll actually talk about the code that implements the game. And now we'll look at the class hierarchies that we're going to explore throughout the rest of the lesson. The first class hierarchy we have is for loot. The root of this class hierarchy is a loot actor, and this is conceptually an abstract class. We'll talk about that more as we talk about the implementation in the next lecture. And it has a conceptually pure virtual function called process teddy bear collision, because the loot actor doesn't know how teddy bear collision should be processed, but it does know that child classes should provide an implementation for that function. Then we have a good loot actor child class and a bad loot actor child class. The other class hierarchy that we'll explore is a more complicated class hierarchy, and it's for all the teddy bears that we include in the game. The root of this class hierarchy is our teddy bear class, and it is conceptually an abstract class because it has a conceptually pure virtual process projectile collision function that concrete classes that can be instantiated below this class in the class hierarchy, needs to implement the body for. Then we have our no loot teddy bear that doesn't drop any loot at all. And on the right you can see that we have another conceptually abstract class called a loot teddy bear actor. And this serves as the parent class for two child classes. The teddy bear that randomly drops good loot, so sometimes drops nothing and sometimes drops good loot, and the teddy bear that randomly drops either good loot or bad loot, always dropping some loot just half the time it's good and half the time it's bad. To recap, in this lecture you saw how our teddy bear destruction game works, and you also got your first look at the class hierarchies that we're going to explore throughout the remainder of the lesson. In this lecture, we'll look at the implementations of the classes in the loot class hierarchy. As a reminder, here's what that class hierarchy looks like, so let's go take a look at some code. As you can see, I have lots of classes in this particular game. Let's take a look at the 3 classes that form the loot class hierarchy. The root of that class hierarchy is the loot actor. I've marked this as abstract here using the uClass macro to let the engine know that I intend this class to be abstract, even though Unreal Engine doesn't really support abstract classes. I have a field for the loot destroy points. You may have noticed when I demonstrated the game that I do earn points when I destroy loot, so this field holds that information. And I've put this field here in the parent class of the good loot actor and the bad loot actor because this is a shared member variable. We have the typical constructor, begin play, and tick functions. I have an onOverlap begin function because I'm going to want to do something when an other actor overlaps the loot. And then I have some protected functions. I'll process a teddy bear collision, and this is the function that I really want to be a pure virtual function. Here in the parent class, I have no idea how we should process a collision with a specialized form of good or bad loot, but I want to make sure that both of those child classes actually implement a process teddy bear collision function. Unreal Engine doesn't support pure virtual functions, but we can mark it as pure virtual with the pure virtual macro, and then we need to provide the name of the function, including the class name. And here, if I returned something, I'd have to actually put return something. For example, if this returned an int rather than having a void return type, we'd put something like return 0 here. But because we have void as the return type, we don't have to put anything here. So what does this buy us, since we can't actually do a pure virtual function? Well, as you know from our discussion of abstract classes, the compiler will tell us if we have a child class that doesn't implement a pure virtual function. That's not how Unreal Engine works. If we have a child class that doesn't implement the pure virtual function that we've marked here, the game will crash. So we discover at runtime that we didn't do everything we should have, rather than discovering at compile time. It's better than not finding out at all, but it would be much nicer if the compiler could actually just tell us when we didn't implement something we needed to implement. We also have a set loot destroy points protected function. The process teddy bear collision function is protected, so only objects of this class or child classes of this class can call this function. And the same applies to set loot destroy points, because the good loot has a certain number of points and the bad loot has a certain number of points, and we want them to set those points here in the parent class. But as we've also discussed, we don't want them to actually modify the member variable directly. We'd rather have them work through a setter. We also have a function that will add the loot destroy points to the HUD. And finally, a function that adds points to the HUD. And we'll see how both of those functions are used as we look at the 2 child classes. Here in the implementation file, we don't do anything exciting in the constructor. In begin play, we find the static mesh component so we can set up the delegate for when we begin an overlap with another actor. We don't do anything special in tip, but in onOverlap begin, we make sure the other actor isn't a null pointer, and we check for a projectile, because both pieces of loot respond the same way when a projectile hits the loot. we add points to the HUD, we destroy the projectile, and we destroy ourselves. If we've just started overlapping with the teddy bear, then we call the process teddy bear collision function with a pointer to the teddy bear object. So this is where the good loot actor and the bad loot actor can behave differently when they have a collision with a teddy bear. This is actually a standard design pattern where we have processing here, and then we plug in some specialized behavior. This is called the template method pattern as a design pattern in object-oriented programming. Setting loot destroy points just sets our member variable to the parameter that's passed in. Adding loot destroy points to the HUD just calls add points to the HUD, passing in loot destroy points. And finally, adding points to the HUD. We've seen interactions with the HUD in the previous course, but this just adds the points that are provided as a parameter to the HUD. We'll look at the good loot actor first. We're going to do something in begin play, and we're implementing what would have been the pure virtual function, but we still want to implement it to provide good loot specific behavior. In the implementation file, begin play is where we set the loot destroy points. So good loot is worth 50 points when a projectile hits it. And when we collide with the teddy bear, we add the loot destroy points to the HUD. So we earn those points either by shooting the good loot with the projectile or by running a teddy bear into it, and we destroy the loot. Remember, the teddy bear doesn't get destroyed here. The teddy bear kept moving toward the left side of the screen so that the player also gets the opportunity to shoot the teddy bear for more points. Finally, the bad loot actor also does something in begin play and implements the process teddy bear collision function. In the begin play function, we set our loot destroy points for 10. The player doesn't earn as many points for destroying bad loot because they want to destroy bad loot so that it doesn't keep killing teddy bears on them. And speaking of killing teddy bears, when bad loot overlaps with a teddy bear, we add penalty points to the HUD. So that's why I have an add points to the HUD function, because I'm not adding the loot destroy points to the HUD. I'm adding a penalty for letting a teddy bear run into the bad loot. So the appropriate action for the player to take is to shoot the bad loot as quickly as they can, because they'll earn the loot destroy points for doing so, and they won't take this penalty every time a teddy bear runs into that bad loot. And we destroy the teddy bear that ran into the bad loot, but we don't destroy the bad loot. So it's going to stick around killing teddy bears until we actually shoot it with a projectile. To recap, in this lecture you saw how we could simulate an abstract class with a simulated pure virtual function in Unreal, and you also saw how we could implement that simulated pure virtual function in our concrete or classes that can be instantiated child classes in the class hierarchy. In this lecture, we'll look at the implementations of the teddy bear actor and no loot teddy bear actor classes. Here's a reminder of what our class hierarchy looks like, and we'll be looking at the implementations of the two classes that I've enclosed in that orange box. So let's go take a look. We'll start with our teddy bear actor class, and this is the root of the entire teddy bear class hierarchy. Again, we've marked it as an abstract class. We have fields for the move amount per second, half the collision width for the teddy, and the number of points that the teddy bear is worth. Standard constructor, begin play, and tick functions. We have an on-overlap begin function because we want to take some action when the teddy bear overlaps with something. We have another, what we would like to be a pure virtual function, even though it isn't really in Unreal, and this one's to have a teddy bear process a projectile collision. What should each teddy bear do when they collide with a projectile? We can get half the collision width of the teddy bear, we can set the teddy bear points, and we can add teddy bear points to the HUD. In our implementation file, we don't do anything special in the constructor. On begin play, we save half collision width, and we also get the static mesh component so we can set up our delegate for when we start an overlap with some other actor. On tick, we move left every frame by the move amount per second times delta time, and we destroy the teddy bear if it goes past the left side of the screen, because we don't want to keep them in the game once they've left the game world. When the teddy bear overlaps some other actor, we check to see if it's overlapping with a projectile, and if it is, we call the process projectile collision function, which we haven't implemented in this class, but all our child classes that aren't also abstract classes will implement this function. Getting half the collision width is pretty straightforward. Setting the teddy bear points is pretty straightforward. And adding the teddy bear points to the HUD is also pretty straightforward. The no loot teddy bear actor, remember this teddy bear just gets destroyed and we get points for doing that as long as it's not destroyed by bad loot, but it doesn't drop any loot, so that's why I've called it the no loot teddy bear actor. We're going to do something in begin play, and we've implemented the process projectile collision function. And in begin play, we set our teddy bear points to 20, so a no loot teddy bear is worth 20 points when we destroy it. And if a no loot teddy bear collides with a projectile, we add the teddy bear points to the HUD because we just earned points for shooting this teddy bear, and we destroy the teddy bear. To recap, in this lecture you saw another example of simulating an abstract class and simulating a pure virtual function in Unreal and implementing the bodies of that pure virtual function and other functions in one child class of the teddy bear actor class. In this lecture, we'll look at the implementations of our loot teddy bear actor, our random good loot teddy bear actor, and our random good bad loot teddy bear actor classes. As a reminder, here's the class hierarchy for the teddy bears, and we're going to be talking about the three classes that I've enclosed in this orange box, so let's go take a look. Our loot teddy bear actor will be the parent class for the two different kinds of teddy bears that drop loot in different ways. But our loot teddy bear actor is a child class of the teddy bear actor class that we looked at last time. We have a loot drop offset because teddy bears will actually drop loot behind themselves when they're getting destroyed. We have two different U properties here for our good loot blueprint and our bad loot blueprint, and we've populated these properties in the blueprint editor. We have a begin play function and a drop loot function, and both of these are protected functions. Our begin play function doesn't do anything, but the drop loot function most definitely does. This function has two parameters, an actor location and the loot that we want to drop, because at least some of our child classes will be dropping bad loot and both of our child classes will be dropping good loot. So we need to know what kind of loot to drop, so we just pass that in as an argument when we call this function. We start by setting our drop location to the actor location, and then we add to the Y component of that drop location half the collision width of the teddy bear. So we're moving to the right because we're adding to Y. So half the collision width plus that loot drop offset so that it ends up slightly behind us when we get destroyed. And then we spawn an actor just as we've done many times in the past. The loot teddy bear actor is another abstract class, at least conceptually, because we did not implement our process projectile collision, what we wanted to be a pure virtual function, in this class. So if we were doing pure C++, this would absolutely be enforced by the compiler as another abstract class because it doesn't implement what we're treating as a pure virtual function, that process projectile collision function. Our random good loot teddy bear actor is a child class of the loot teddy bear actor we just looked at. We take action in the begin play function, and we've implemented process projectile collision. The action we take in begin play is we set teddy bear points, so this random good loot teddy bear is worth 50 points if we shoot it with a projectile. If we collide with a projectile, we're going to randomly drop good loot. So we get a number between 0 and 1, and if that number is less than 0.5, then we're going to call the drop loot function that we just looked at in the loot teddy bear actor class, and we'll provide our current location, and we'll drop good loot. And remember, this good loot member variable is inherited from our loot teddy bear actor. Remember, we had those properties for good loot and bad loot. We also add teddy bear points to the HUD because we were just shot by a projectile. So the player earns the points for destroying this teddy bear with a projectile, and we destroy ourselves. Our random good bad loot teddy bear actor will either drop good loot or will drop bad loot. So the implementation of this class looks very similar to our random good loot teddy bear actor. Here in the header file, we have a begin play function and a process projectile collision function. And here in the implementation file, we set teddy bear points to 100 on begin play. Processing a collision with a projectile will get a random number between 0 and 1. And if that number is less than 0.5, we'll drop good loot. And if that number is greater than or equal to 0.5, we'll drop bad loot. So that gives us a 50-50 chance of good loot or bad loot. We then add the teddy bear points to the HUD because the player earned points for destroying this teddy bear with a projectile, and we destroy the teddy bear. To recap, in this lecture we saw another use of a simulated abstract class in our class hierarchies, and we finished our discussion of the class hierarchies in the teddy bear destruction game. What will you learn in this lesson? You'll learn how pointers to functions or function pointers work in C++. You'll learn how to use single delegates, multicast delegates, and events in Unreal. And you'll learn why you should use an event manager and how to do that in your Unreal games. In this lecture, you'll learn how to use pointers to functions, which are commonly called function pointers. The big idea is we can declare a variable to hold a pointer to a function, assign a function to that variable, and then use the pointer to call the function. We know from our past work that we can use pointers to point to data, variables, in memory, and functions are also stored in memory. The executable code is also stored in memory. So we can also use pointers to point to the memory address of the executable code. Let's go see how this works. At the top of our code, we have function prototypes for two functions that say hi and say bye, and two functions that find the smaller of two numbers and find the larger of two numbers. And the implementations of those functions at the bottom of this file are as you'd expect. So here's the new stuff. We're going to declare pointers to those two different kinds of functions. The syntax for declaring a pointer to a function is we put the return type, and then between parentheses, we put the asterisk and the name of our variable that's going to point to a function. And then we have another set of parentheses where we put the data types for the parameters for that function. And here I'm initializing that pointer to a null pointer because that's always a good practice when we declare a pointer variable. So this top declaration of our pointer variable is going to point to a function that returns void and has no parameters. And of course, that's these two functions here. And our second declaration will point to a function that returns an integer. It's a pointer. We're going to call it the find function. And this one has two parameters, two integer parameters. And then we initialize that to null pointer as well. Just to show you that a pointer variable that we've declared as a pointer to a function in this way can only point to a function that has this return type and this empty parameter list, I'll try to set my say function pointer equal to find smaller. And the compiler tells me I can't assign a function that returns an int and has two int parameters to a pointer to a function that is supposed to have void as a return type and no parameters. So just as we can't assign a float to a pointer to int, we can't assign a function with a function signature that doesn't match the pointer that we've declared as a pointer to a function. Okay, so let's actually do some good stuff, not just look at compilation errors. I can assign the address of say hi to this pointer to a function that returns void and has no parameters. And then I can call the function that's pointed to. So I put the name of my pointer to a function variable, and then I put any parameters that I have between these parentheses. I'll set find function to the address of find smaller, and then I'll print out that the smaller number is, and then I call the function by putting my pointer to function variable name, and then I put 1 and 2. So I imagine you can figure out what the answer should be. And then I'm going to reassign variables. So now say function is going to hold the address of the say by function, and I'll call that function. And then I'll reassign the find function to hold the address of find larger, and then I'll call that function again here. So the cool thing about this is I always call say function with this syntax, and I always call find function with this syntax. But the function that I'm currently pointing to is the one that gets called with parameters if I've provided parameters. So we can change the function that gets called by changing the function that the pointer to function variable holds. It's also the case that we don't actually have to put the address of operator here on the right hand side of the assignment statement. Notice that I've been putting the address of operator up above, but we don't have to. That's a matter of personal preference. I like to put the address of operator just to demonstrate that I'm in fact putting an address into this pointer to a function, but the compiler is smart enough to know that it really is assigning the address of this function to this variable. So that's personal preference. I'm going to use address of, but you don't have to. The compiler can figure it out. And then I call this say function again. So you should think about what you think the output will look like when I run the code. The first line of output, the say function pointer to a function was pointing to the say hi function, which says hi. And the find function pointer to a function was pointing to the find smaller. So the smaller number of 1 and 2 is 1. And then I reassigned both those pointers so that the say function pointed to the say by function, and the find function pointer to function pointed to the find larger function. So then I get by as the output from calling the function pointed to by say function, and I get the larger number when I call the function pointed to by the find function, pointer to function. And then finally, when I showed you we don't need the address of operator, I was reassigning again the say function pointer to a function to point to the say hi function, so when I execute that function, I get the hi message again. And I will show you those function implementations. Say hi says hi, say bye says bye, find smaller finds the smaller number, and find larger finds the larger number. So that's how we can use pointers to functions in our C++ code. To recap, in this lecture you learned how to use a variable to hold a pointer to a function, and you learned how to call the function using that pointer. In this lecture, you'll learn about callback functions. The big idea is we pass in a pointer to a function as an argument to a different function, and later on, that different function can call back the function that we passed in. The pointer to function that we pass in is called the callback function, and the function that does the calling back is called a higher order function. Let's go see how this works. In this example, we have three functions. We have a less than function that will return true if first number is less than second number and will return false otherwise. We have a greater than function that will return true if first number is greater than second number and false otherwise. And then the interesting function is the find extreme function, which returns an int. So we pass in a reference to a vector of int called values, and here's the new stuff. We also pass in a pointer to a function that we're going to call compare, that's the parameter name, and this function returns a bool and has two int parameters. And you shouldn't be surprised to recognize that function signature as the function signature for the less than function and the greater than function. So down here in my main function, I create a vector of values and I set a min value variable to the results of calling the find extreme function with that vector of ints and the address of my less than function. And then I set a max value variable to the results of calling find extreme with the vector and the address of the greater than function. So this part here is me passing in a callback function into the higher order function called find extreme. So let's look at the implementations of our function bodies. Less than is straightforward. It just returns whether first number is less than second number. Greater than is very similar. And of course, this is the interesting function for this example. Remember the values and a pointer to a function that returns a bool with two int parameters, and that parameter is called compare. We're going to just assume at least one value is provided. So I'll set an extreme value variable equal to the first element of my values vector. And then I'll iterate over the rest of the vector. And here's the interesting part. I'll call the function that's pointed to by the compare parameter, and I'll pass in the current value I'm looking at in the vector and the extreme value. It might be the smallest, it might be the largest, we don't know, but the extreme value that we've found so far. And if the function that's pointed to by the compare pointer to function parameter returns true, then we just found a new extreme based on whatever that comparison does. And if we just found a new extreme, we set extreme value equal to the current element of the vector that we're looking at, because we just found a new extreme value. And then when we're all done, we return that extreme value. So this code here doesn't have to have any idea how compare works. This function just uses a pointer to whatever function was passed in as an argument when the find extreme function was called to do whatever comparison is required and keep track of the current extreme value. When I run my code, you'll see that the first time I called find extreme, with a pointer to the less than function, I found the minimum value. And then the second time when I called find extreme with a pointer to the greater than function as an argument, I got the maximum value. And just to show you that that's actually true back at the vector, you can see that 1 is my minimum value and max is my maximum value. To recap, in this lecture you learned how we can pass a callback function into a higher order function. You learned how we can call back that function from the higher order function. And you should know that using callback functions lets us implement a standard object-oriented pattern called the observer pattern. In other words, the callback function says, I would like to observe when something happens, and the higher order function, when it calls back that function, says, hey, it happened. I'm glad you wanted to observe it. Now you can. That's really the core idea behind event handling. In this lecture, you'll learn about single delegates in Unreal. For our purposes, single delegates are analogous to the higher order functions we learned about in the previous lecture, where we pass in the address of the callback function and the higher order function can call back that function at some other time. The terminology and the way we do it is slightly different in Unreal, but the big idea is the same. In the interests of full disclosure, our single delegates are actually more like what are called function objects or functors in C++, but the way we're using them, you can just think of them like the higher order functions we've already learned about. Before we look at the code for our example, I wanted to show you here in the Unreal Engine documentation, if you search on delegates, you'll get to the documentation that explains how to do the things that we're going to do today. The big idea is that the delegate is essentially a higher order function that we can bind a pointer to a callback function to, and when we decide to execute the delegate, which is essentially executing the higher order function, it will call the callback function that has been bound to that delegate. In this lecture, we're going to explore single delegates, and in the next lecture, we'll explore multicast delegates, including events. We have some options when we declare a delegate. We can declare delegates for functions that return a value. We can declare delegates for functions that are const. We can have up to 4 payload variables, which we're not going to deal with in the examples that I provide. And we can have up to 8 function parameters for that pointer to function that we're going to bind to the delegate. And I will let you explore the rest of this documentation on your own so we can just get to our code example. First, I'll show you how the code works. So I have a talker actor and a listener actor, and if I run the code, the talker actor every 3 seconds sends a message with a number in it, and these log messages you're seeing appear are the listener receiving that message with the appropriate number in it. So the listener has provided a callback function to our talker delegate, and when our talker delegate is executed, it calls that function back. We'll look at the talker actor first. So here's how we declare a delegate. We use the macro declare delegate, and I happen to be declaring a delegate that has 1 parameter. So I include _1 param in my macro name. Over here on the right, I provide 2 things. I provide the name of my new delegate. So this is defining a type. I'm defining a type called fMessageDelegate. and I say what is the type of that one parameter for the delegate. And I happen to be passing an F string when I execute this higher order function to call whatever callback function has been bound to this delegate. I'm keeping track of the message number so that I can increase that each time I send a message. I have a timer that goes off every 3 seconds to execute my delegate. This is the function that will actually execute that delegate. And this variable right here is my field or member variable that holds the actual delegate. This is the delegate that will bind a callback function to and execute when we decide we want to execute it. We have the constructor begin, play, and tick as usual. In my implementation file, I'm just starting the talker timer on begin play, and that does the usual starting a timer thing. So here in my talk function, I'm taking that message delegate object, which remember is essentially a higher order function, and I'm telling it to execute if bound. And then I provide that single F string argument that my delegate type requires and that my callback function is expecting me to provide when I execute the callback function. There's actually an execute function that I can call instead of execute if bound, but that's a bad idea. We should only execute message delegate if in fact there has been a call function bound to the message delegate. So we'll use execute if bound when we're executing single delegates that we're using in our code. So this is the talking side, right? This is the message delegate calling a callback function with this particular argument. In my listener actor, I'm going to keep a reference to the talker actor, and I'm going to add 2 additional functions beyond the usual functions. This receive message function is my callback function, and as you can see, it's got a return type of void, and it expects 1 F string argument. So this matches the required function signature for me to bind this function to my delegate. And I'm overriding the end play function so that when this listener actor gets removed from the level or the map, it will unbind itself from the delegate. We don't want to remove this and have my delegate still holding on to a reference to it in memory. That's like our dangling pointer problem that we've talked about previously. So we want to unbind our receive message function from that delegate when we get removed from the level. And finally, in the implementation for our listener actor, on begin play, we get a pointer to the talker actor object that's in the map and save it right here if we find it. And then on that pointer to a talker object, we access the message delegate field that we declared to be public in my talker actor, and we call the bind uObject function on that delegate. There are a number of different ways we can bind a function to a delegate, and you can read the documentation to see that variety of ways we can do that, but I'm going to use the bind uObject function to bind this listener object with this address of my receive message function to that delegate. So this is me providing the callback function to that delegate. When I receive a message, I just print out the message I received. And then finally on end play, first I check to make sure I have a pointer to that talker actor object before I try to access a field in the object I think I'm pointing to. And as long as this isn't a null pointer, I access the message delegate field for that talker actor object, and then I unbind myself from that delegate. If this idea of binding a function to a delegate looks eerily familiar to you, you should realize that we've been doing this ever since we started handling Unreal Input. As a reminder, we've called the bind access function on an input component to bind a particular function. In this case, the address of the fish player controller's move horizontally function to a particular axis. And we've called the bind action function on the input component to bind a particular function, in this case, the fish player controller shoot fish function, to a particular action. So we've actually been providing addresses of functions to bind them ever since we started processing Unreal Input. To recap, in this lecture you learned how to use a single delegate in Unreal, and you also saw that the big ideas are analogous to our higher order function and callback functions in pure C++. One of the big limitations of the single delegates we learned about in the previous lecture is that a single delegate can only call back a single callback function, the most recent callback function that was bound to that delegate. There are certainly lots of situations where we'd like a delegate to be able to broadcast to as many callback functions as we need for whatever we're trying to accomplish. In this lecture, you'll learn how we can use multicast delegates and events to accomplish that. This is our project from the delegates lecture from last time. And single delegates work great if we have only one talker and only one listener. But if I add another listener actor to my map and put it in an appropriate place, and when I run the game, you can see that only one of those listeners is getting called when the delegate is executing. And that's because one of them binds itself to that delegate on begin play, and then the other one binds itself to that delegate on begin play, and that last binding is the only one that has an effect. So if we have multiple listeners that need their callback function called when the delegate is executed, using a single delegate won't work for us. The answer is to use a multicast delegate instead of a single delegate. And as you can see, we have documentation here that tells us how to do that. And you can read that documentation. I'll show you in the example how we can actually use a multicast delegate so that multiple callback functions get called when the delegate is executed. Let's go take a look at the code that actually does that. First, I'll show you that the changes that I've made to the code actually solve our problem, and then I'll show you those actual changes. So if I run my game, every 3 seconds, you'll see that both listeners are having their callback functions called when the delegate is executed. First, I've changed the way I've declared my delegate. So instead of using declare delegate one param as my macro, which just defines a single delegate type, I'm declaring a multicast delegate one param. I've left the type name of that delegate the same, and it still only has an f-string parameter, but it's a different kind of delegate. It's a multicast delegate, not a single delegate. The rest of my talker actor header file is the same. My implementation file changes slightly, so when it's actually time to execute my delegate, I don't use execute if bound, I use broadcast. And the broadcast function will call back all of the callback functions that have been added to this delegate. Not just one, like we saw when we bound a callback function to a single delegate. This will broadcast to every callback function that has been added to this delegate. In my listener actor, I've added an additional field here for a delegate handle, and we'll see why I need that when it's time for me to remove this particular object from the broadcast list of callback functions. The rest of this header file is the same as it was before, but the implementation file changes a little bit. In begin play, I still find the talker actor, but this time, instead of calling bind UObject, I call add UObject, because I'm just adding myself to the list of objects that have a callback function that should be called back when the delegate is broadcast. And I also save the results of calling that function into that delegate handle field I showed you moments ago. The reason I need that is because when I want to remove myself, when this particular listener actor is being removed from the level or the map, I can't call unbind anymore with no parameters. Remember, the unbind function had no parameters. For a multicast delegate, I need to call the remove function instead, and the remove function has a single parameter, and that parameter is the delegate handle that I saved when I added this UObject to that delegate. So that's why I need to save that delegate handle, so when it's time for me to remove myself from that multicast delegate, I can provide that handle that was provided to me when I added myself to that multicast delegate. So back in the talker actor header file, this works fine for having multicast delegates. We might want to actually limit which classes can actually broadcast a particular delegate type that we're defining, fMessage delegate in this particular case. With multicast delegates, any class can broadcast an fMessage delegate, but we might want to be more limited. If we know that there's only one class in our game that should be able to broadcast a particular delegate, then we can limit the broadcast capability so that only that class can broadcast that delegate. The way we do it is, instead of using multicast delegate, we use event in our macro, and we need to change our list of items provided to the macro. The very first thing we put is the name of the class that is allowed to broadcast the delegate. So if I say a talker actor here, that's the name of the class that can broadcast our delegate. And only a talker actor objects can broadcast that delegate. So I'll compile again. And then back in the editor, when I run the game again, it's going to behave exactly the way it behaved before, but I wanted to show you that if in fact we want to limit who can broadcast a particular delegate, we can use one of the event macros that are available to us to do that. If we don't care, or if we have multiple objects that we want to be able to broadcast a particular delegate, which we'll see before we're done with this particular lesson, then we definitely want to use a multicast delegate. If we do care, and we only want objects of a particular class to be able to broadcast the delegate, then we use the event macro instead. To recap, in this lecture you learned how to use multicast delegates and events in Unreal, and you also learned that using multicast delegates and events lets us broadcast to multiple callback functions. In this lecture, you'll learn about C++ maps, another container type. Maps store key-value pairs where we look up a value using the key. You can think of this as being like a dictionary, where if we want to find the definition or definitions of a word, we use the word as the key to look it up in a dictionary, and then the value for that key is the definition or definitions for the word. Maps can be much more efficient than other container types like vectors when we want to look things up. If we're looking for a value in a vector, we may have to traverse the entire contents of the vector to find the value we're looking for or to discover that it's not there. Maps, on the other hand, can simply use the key to look for that value or to discover that the key is not in the map without traversing the entire container. In this lecture, we're going to use an unordered map, so we don't care about any natural ordering that the keys for the map may or may not have. I'm going to create a map of high scores with the key being a gamer tag, so a string, and the value being an integer, so the high score for whatever gamer tag that entry is for. Here's how we declare our variable. We say it's a standard unordered map, and we provide the data type for the key and the data type for values. I've given it the variable name high scores, and I'm initializing it to an empty map. One way we can add a key value pair to our unordered map is to use the insert function. When we use the insert function, we need to pass in a key value pair. One way we can do that is to call the standard makePair function, and it's a templated function, so we tell it the data type for our key and the data type for our value, and then we provide the actual key and value as arguments to the function when we call it. So these 3 lines of code are adding a score for Joe of 100, a score for Bob of 9001, and their unfortunately less adept brother Joe Bob has a high score of 1 in this particular game. We'll see in a coming lecture why using the makePair function can actually be a helpful way to add a key value pair to the map. If your map is simple like this, we can do the following. We can say high scores Harry equal 42. So for a simple unordered map with simple key value pairs, it's also reasonable to add a key value pair to the map by just using this syntax where this is the key and this is the value. Then we'll prompt for and get a gamer tag from the user. And now, given the gamer tag that the user provided, we'll look up in our unordered map using the gamer tag they provided as a key. And if there's a key value pair that corresponds to that key in the map, then we'll provide the high score for that gamer tag. And if not, we'll print an error message that says there's no high score for that gamer tag. One really effective way to find out if the map contains a particular key is to call the count function on the map and pass in the key that we want to check for, and the count function will return how many times the key appears in the map. There can actually only be 2 numbers. There can be 0 or there can be 1. Maps don't allow duplicate keys, so you can never have 2 or more key value pairs with the same key, but you might have 0 if there's no key value pair with that key, or you might have 1 if there is a key value pair for that key. So we can just get that count and then compare to 1, and if the count is 1, then we did find a key value pair in the map that has that key, so we can access the value. We can use @ like this. We can use the square brackets like you saw me do above. Either way works fine. And then if the count function returned 0, then we'll print no score for that gamer tag. I'll test with all the gamer tags that are in the map. So 100 for Joe, 9001 for Bob. Joe Bob only has 1. And remember, I added Harry. Harry has 42. But if I enter a different name like this, I get no high score for that particular gamer tag because there was no key value pair in the map. To recap, in this lecture you learned that maps hold key value pairs. We worked through an example using an unordered map, and you also learned how to use the count function to determine whether or not a map contains a particular key. In this lecture, we'll refactor our talker and listener game again to get an even better object-oriented design. The big idea is that we'll add an event manager utility class that will make it so that the talker and the listener don't need to know about each other, they'll just interact with the event manager. We'll gain other benefits as well. We won't care what order they're added to the map when the game starts, and we'll be able to spawn and remove both broadcasters and listeners as the game plays, and everything will work fine. I'll actually use the term invokers rather than broadcasters, but the ideas are the same. Let's go see how we can reap these benefits from adding an event manager. I started with our Unreal project from the previous lecture, and I've added two classes to the project. I've added a delegate declarations class that's just a U object, and I added an event manager actor that's an actor. And I turned the event manager actor into a blueprint, and I added it to our scene, and I added an event manager gameplay tag to the project and tagged this blueprint with that tag. Let's go take a look at the code. I added the delegate declarations class just as a container for delegate declarations. I know as we build larger and larger games, we may have multiple delegates in our games, and although it's reasonable, like we've seen previously, to have the talker actor actually declare the delegate that the talker actor will broadcast, I decided to just group all our delegates for the game in this class instead. And grouping one in this class is not very exciting, but as we have more delegates, as you'll see in the next module, it's nicer to just put them all together in one place. So I've started doing that now. I've declared a one parameter multicast delegate, and I've called it fMessageEvent like we called it before. And it has one parameter and fstring just like before. So this delegate declaration hasn't changed, except I turned it into a multicast delegate instead of an event, because I'm also going to find that I will regularly have multiple classes that I want to broadcast the same event. So my standard will be to make them all multicast delegates. I'll call them events when I'm talking about them because that's how I think about them, but they'll be multicast delegates. So any class can broadcast the fMessage event. My event manager actor, pound includes the talker actor, and pound includes the listener actor, and pound includes this header file as well. I have two fields in the event manager actor. The first one is a T-array of pointers to talker actors. So this is a T-array of the invokers of the event. And this makes it so that I can support having multiple talker actors in my map, and they can all invoke the message event. The other property I have, and here's why we talked about maps. This map is for message event listeners, and the key is a pointer to a listener actor. So again, I can have multiple listener actors in my map. I don't mean this map, I mean a level in the game. And each of them will have a unique key, of course, because they each have a unique address. So I'll have an entry in this listener's map for each listener actor. And then the value is another map that I will key by a pointer to the talker actor, and the value here will be an fDelegate handle. The reason I've structured it this way is so that listeners don't have to hold on to that F delegate handle. Remember, we needed to hold on to that to be able to remove ourselves as a listener from the delegate when we get removed from the map. I didn't want the listeners to have to care about that detail, so I'm going to maintain this map here. So when a listener says they want to be removed, we can effectively do that, removing them from each of the invokers using the delegate handles that we saved in this map. We have the standard constructor, begin, play, and tick. And here's the new stuff. I'm going to let a talker actor add themselves as an invoker of the message event. And I'm going to let a talker actor remove themselves as an invoker of the event in case that talker actor is getting removed from the level in the game. I'm going to let a listener actor add themselves as a listener, and I'm going to let a listener actor remove themselves as a listener when the listener actor is getting removed from that level in the game. So the event manager will let invokers add themselves as invokers, and the invokers don't have to know anything about who's listening for this particular event. Similarly, we'll let listeners add themselves as listeners, and the listeners don't have to know anything about who's going to invoke or broadcast the event. So this is a great way to decouple the classes that listen for events and the classes that broadcast events. We'll let the event manager do all the hooking up between invokers and listeners. In the body of our event manager actor, adding an invoker, the first thing we do is we add the invoker that's been passed in to the T array of message event invokers. The next thing we want to do is, because we don't know if there are listeners who have already added themselves as listeners, we want to go through the map of message event listeners and add each of them as a listener for this new invoker when this new invoker broadcasts the event. I'm using a range-based for loop to do this. So the element I'm looking at each time through the loop is called element. I'm going to execute this for loop across the map of message event listeners. This is new. We haven't actually talked about auto, but auto is just a way to say, I'm not going to tell you what type this element is. I'm going to let the compiler infer from this information, specifically from this, what each element will be as we go through the for loop. And this, of course, just says we want a reference to that particular type. You may wish I had told you about auto before. It certainly shortens this line of code, but I wanted us to spend a lot of time in the previous courses thinking about the actual data types that we were dealing with. So I didn't tell you about auto until now, but I think you're mature enough as C++ programmers and Unreal game developers to be able to handle letting the compiler just infer the data type. The next line of code, we take the element we're looking at, and we take the key for that element, and the key for that element is a pointer to an A-listener actor, and then we're going to call a function on that A-listener actor that says add to message event. So we're going to pass in a message event into the A-listener actor, and the A-listener actor will add the address of its callback function to the message event we pass in. To get the message event we pass in, we have a pointer to an invoker that we passed in as a parameter up here, and we call the getMessageEvent function on the aTalker actor to get the message event that is embedded in the invoker. I made the fMessageEvent field private in the talker actor just because that's the way it really ought to be, but I provided a getter so that we can get access to that fMessageEvent. So this is just adding a listener to the message event inside the invoker. And then the final line here is I take the element value, which remember is another map that maps pointers to A talker actors as keys and F delegate handles as values. And I add an element to that map using the invoker as my key and the delegate handle that I just got here as my value. And we're only doing that so that we can remove the listener later if we need to do that. So that's how we add an invoker. Big picture again, we add the invoker to the T array of invokers of the message event, and then we iterate over the map of message event listeners who have already added themselves as listeners, and we make sure they're listening for the event being broadcast from this new invoker that we just added. To remove an invoker, the first thing we do is we remove all listeners from the invoker. So we execute a for loop over all the message event listeners, and if the map that maps invokers to delegate handles contains this particular invoker, then we get the message event from the invoker, and then we remove this particular listener by accessing the value in the map, and that value, remember, is an F delegate handle. So this is how we remove the current listener we're working on from the event in the invoker, and then we remove that element from the map because the invoker is getting removed, so we don't need this element in the map anymore with this particular invoker as the key and the delegate handle we used when we added to this message event as the value. So this is removing that element from the map. Now that we've disconnected all the listeners from this invoker, we actually remove this invoker from the T array of invoker for the message event. To add a new listener, we do something similar to adding a new invoker. The first thing we do is we add the listener to the map of listeners, and then we iterate over all the invokers. And for each invoker, we hook up this new listener to the set of invokers who have already said they're invokers of the event. So this code right here does what we saw previously. We're hooking up this listener to the current invoker we're looking at as element. And then we add to the map of invoker pointers and F delegate handles the delegate handle we just got, with the current invoker we're looking at as the key and the delegate handle as the value. Remember, we do that so we can remove the listener later. And that's all we have to do to add the listener. So big picture, we add the listener to the map of listeners, and then for each of the existing invokers, we go through and we hook up this listener to that invoker's message event. Finally, removing a listener looks a lot like removing an invoker. We go through all the invokers. If the map in the listener contains the invoker that we're currently looking at as a key, then we remove this listener as a listener for the event for that particular invoker, and then we remove that element in our map of A talker actor pointers and F delegate handles because we just disconnected this listener from that invoker, so we don't need that element in the map anymore. And then finally, when we've done all that disconnecting, this says remove invoker, but let me fix that. We remove the listener. So that's all the stuff in the event manager. We can move a little more quickly now. In our talker actor, we need to pound include our delegate declarations so that we have a reference to that delegate that we defined over there. And here's where I have a field for that F message event. I've added that get message event function that we've been talking about. And it's really important that this returns a reference to an F message event because we need to make sure that we're not returning a copy of the F message event. We need to get a reference to the F message event to make sure that when we do this and we're hooking up a listener to this talker, that we make sure that we're doing it with the F message event field, not a copy of the F message event field. And end play, just as we saw in not the previous lecture, but the lecture before that. in my implementation for the talker actor. I do more work in begin play now because I need to add myself as an invoker to the event manager. So as I said, I tagged the event manager with this tag. So I do our standard go find a tagged actor. And if I find it, I cast that a actor pointer to a pointer to an a event manager actor. And then finally, I call the add invoker function that we looked at, passing myself in as the invoker. Down here, I haven't changed my talk function at all. I still broadcast the message event. And when I'm being removed from the level, I go find the event manager again, and I remove myself as an invoker. And that's it for the talker actor. For the listener actor, I pound include delegate declarations again. I have that add to message event function that we talked about. The receive message function we already saw previously. And the end play function we saw previously. So in my implementation file, when I begin play, I find the event manager and add myself as a listener. Here's that new add to message event function where I just call the add UObject function on our message event, passing myself in as the object and the address of my receive message function as the callback function, and I return the fdelegate handle that I get back from calling add UObject so that the event manager can add that to the map that contains talker actor pointers and fdelegate handles. I didn't change receive message at all. And here on end play, I find the event manager again and remove myself as a listener. And just to show you that the game works fine with this new event manager structure, and when I run my game, you can see that the listener actor is still receiving those messages and the talker actor is still broadcasting those messages. That's how the listener actor can receive them. But we connected those two together through the event manager rather than having the listener directly know that the talker actor was the one who was broadcasting that event and having the listener actor interact directly with the talker actor. To recap, in this lecture you learned how to add an event manager utility class to gain a number of benefits as we handle events in our games. And doing it this way gives us a really solid object-oriented design. In this lecture, we'll refactor our teddy bear destruction game to use events and an event manager instead of having multiple objects called the add points function in the game HUD. And this will decouple our loot actor, teddy bear actor, and launcher pawn from the game HUD. I've added a couple of classes to our teddy bear destruction game. I have a delegate declarations class, which is a U object, and I have an event manager actor, which is an actor. And as before, I turned the event manager actor C++ class into a blueprint, added a gameplay tag for event manager, tagged the blueprint with that tag, and as you can see, added it to my map here. So let's go take a look at our code. In our delegate declarations, I declared a multicast delegate, and this one I called an fPoints added event, and it has one parameter, an integer, the number of points that have been added. And as I mentioned previously, I can't actually use an event here. I need to use a multicast delegate because I have 3 different classes that are actually going to broadcast this event: the loot actor, the teddy bear actor, and the launcher pawn. So this is one of those places where using a multicast delegate instead of an event makes a lot of sense. One of the problems that we're faced with is in my event manager, we know when we added an event manager and a talker actor was the only invoker, that we used the address of the talker actor objects as both the elements in my T array of invokers and as a key in the map in the listeners to help us look up fdelegate handles for that particular listener, for that particular actor. And now we have 3 different classes that will broadcast this event. And although in C++ people regularly will use multiple inheritance to get characteristics of multiple parent classes into a particular child class, that's not a good idea here in Unreal. We're going to use a different approach that lets us have our different invoker classes be treated as invoker classes without muddying up our class hierarchy by making each of them inherit from both the Unreal Actor class and some other class that we define. And the thing that we're going to use is we're going to use something called an interface. And interfaces are commonly used for exactly this purpose in C#. They're not used in C++ for this purpose. People use multiple inheritance, but in Unreal in C++, we can actually use interfaces so that we still have single inheritance. We have nice class hierarchies where each child only has a single parent class. So over here in my project files, I've actually added an interface, and I'll show you how I did that. Over here in the editor, I said I wanted to create a new C++ class, and I scrolled all the way down and I picked Unreal Interface as the parent class for my interface. I'm not going to do it again. I already have that interface, but that's how I added the interface to my Unreal project. And I'll show you the points added invoker interface implementation file. Doesn't have anything in it other than the #include. It does say add default functionality here for any iPoints added invoker interface functions that are not pure virtual, but I only have one function in this interface, and I've made it pure virtual because I don't know a good default implementation for the function that I've included. So here's what the interface looks like. I've #included my delegate declarations, and the class is marked as UInterface, and this comment was automatically provided when Unreal created this script for me, so we'll just leave it alone because it says to leave it alone. This is the name of my actual interface, and I added the comment in interface for, with a typo, invokers of the points added event. And this comment was automatically generated. It says add interface functions to this class. This is the class that will be inherited to implement the interface. So we want to get the points added event for this invoker. Just like we implemented a get message event function in our talker actor class so that we could get the message event that was inside that talker actor so that we could add listeners to it. But we're going to make it so the multiple classes that invoke this event need to provide a get points added event that returns a reference to the fpoints added event field that will be in those classes. And I've marked it as pure virtual. And here's the name of that pure virtual function. And this is horrendously ugly code. I will freely admit that's horrendously ugly code because we're returning a reference, but references can't be null in C++. And that's what I'd like to return here as my default function that should never get executed, but I can't return a null reference. So I had to do that horribly ugly code, and you can read about it here if you want to. This should never get executed because I marked it as pure virtual. So I feel guilty, but that's what I had to do to get this to compile. And I know, because I marked it as pure virtual, that that horribly ugly code should never get executed. So this is how I define an interface. And notice, of course, that I made this not just a virtual function, but a pure virtual function. And that will make sure that any of my classes that inherit this interface will have to implement the getPointsAddedEvent function. And now if we look at my event manager, you can see I've #included the pointsAddedInvoker interface, not a specific class, but the interface itself. And GameHUD will be my listener. and I have a T-array of pointers to objects that implement that interface, and that's my invokers T-array. And I have a T-map where I have a pointer to my listener as the key, and the value is another map with a pointer to the object that implements the interface, and the fdelegate handle I got back when I added a U object to the points added event in that particular object. And that's my set of listeners. And then really, the rest of this looks the same as we looked at when we added an event manager, except that we're always dealing with pointers to the interface. In the implementation file, this all really looks just like we've already looked at. The only thing that I want to mention is right here, we can safely call the getPointsAddedEvent function on a pointer to an object that implements the interface, because we know that that object has to implement that pure virtual function. And other than the use of the pointers to objects implementing the interface rather than pointers to actors, the rest of the event manager looks just like we've already seen. In our loot actor, we pound include the delegate header file, and we pound include the interface file. So here's where we see the use of that interface. Our loot actor used to just inherit from a actor, but now it inherits from this class, and it also inherits from the interface. So our loot actor inherits all the stuff that it inherited before, but now because we've said it inherits from, or we regularly use the terminology that this class implements the interface, because we've said it implements this interface, that means that it's going to provide a getPointsAddedEvent function. It has to, because we marked that as a pure virtual function. So we have a field for the pointsAddedEvent. We're going to override the endPlay function, so when the loot actor gets removed from the level, we can remove it as an invoker for the pointsAddedEvent. And this will happen all the time. In the adding event manager, we actually never removed talkers or listeners from our level. But in the teddy bear destruction game, loot and teddy bears get destroyed all the time. So this function will get called each time a loot actor gets destroyed. Here's where we're overriding that getPointsAddedEvent, and the rest of this class looks the same. In our implementation file, you'll notice that I commented out our reference to the GameHUD header file because this actor no longer needs to know about the GameHUD. This actor is just going to work through the event manager actor. So I've added a pound include for that header file. And in addition to the stuff we did before, we're adding ourselves as an invoker to the event manager. When we get removed from the level, we remove ourselves as an invoker from the event manager. Here's our implementation of that overridden function where we just return our field. And here's our other difference. So instead of what we used to do, which was get a reference to the HUD and then call the HUD's add points function, instead we're just broadcasting a points added event. And whoever's listening for that event, it will be the game HUD. Whoever is listening for that event will just hear that event and process it. Our teddy bear actor header file looks remarkably similar, where we have some more pound includes. And we say we're going to implement that interface as well as inherit from a actor. Provide event support. Handle when the teddy bear gets removed from the level, and override that pure virtual function from the interface. In the implementation file, again, I don't care about the game HUD anymore, but I do care about the event manager. I add myself as an invoker in begin play. When it's time to add points, I broadcast the event instead of getting a reference to the HUD and calling that add points function. Remove myself when I get removed from the level, and implement the override for the get points added event function from the interface. There's no need for us to look at the launcher pawn because it does the same things in the header and the implementation file. So the last thing we should look at is the game HUD, which needs a reference to the delegate. I've added begin play to the game HUD because that's where I'm going to tell the event manager that I'm a listener for the event. I've added an add 2 points added event function just like we saw when we were adding an event manager. And even though the game HUD shouldn't be removed from the level, we're going to implement our end play function anyway just for completeness. And as I said, in begin play we add ourselves as a listener. In our add 2 points added event function, we do what we've seen before. For listeners, we return the fdelegate handle that we get when we add ourselves as a U object to a particular event. And we remove ourselves as a listener when we are removed from the level, even though that shouldn't happen for our game HUD. I should have pointed out that we're providing the address of our add points function here, and of course our add points function doesn't have to change at all. It just gets called when the event is broadcast instead of being called directly by the launcher pawn and the teddy bear actor and the loot actor. And of course I'll show you that the game still works fine after that refactoring. I can still destroy teddy bears and loot, and my score goes up. And my launcher actually deducts points when I collide with teddy bears as well. To recap, in this lecture you learned how to refactor our teddy bear destruction game to use events and an event manager, and you also learned how to use interfaces in Unreal. What will you learn in this lesson? You'll learn about building user interfaces using Unreal Motion Graphics or UMG and Slate widgets. You'll learn about menu buttons in Unreal, and you'll use that knowledge to build a simple menu system that lets us play or quit a game. And then finally, we'll learn how to add a pause menu to our game. In this lecture, you'll learn how to implement menu buttons in Unreal. So let's get right to work doing that. To start with, I have a custom game mode and a custom player controller. So let's go take a look at that code. Before we even start looking at the classes I modified and the class I added for the player controller, we need to actually change some dependencies in the project. Over here in the Solution Explorer, you can see under Source, Menu Buttons, I have a build file that's actually a C# file that I need to modify to change the dependencies that my project uses, specifically to let me use UMG and Slate. So we'll open up that file, and the first thing I need to do is I need to add something to the public dependency module names. What I need to add is UMG between double quotes. The other thing that I need to do is down here you can see it says uncomment if you're using Slate UI, which we are using in this project. So all I have to do is uncomment that line of code. None of our code will work if we don't modify this build file. So we need to make sure that that's the first thing we do whenever we're going to use UMG and Slate. I'll save that. So now we can start looking at the game mode base and the player controller. In the game mode base header file, I've added a #include for user widgets because the Slate widgets we're going to use are the user widget class. I've made sure that we call begin play when the game starts in my game mode, and I've added a U property for our menu widget class, so I can just populate that in the blueprints editor rather than doing it here in my C++ code. In the implementation file of my game mode, I call super begin play as always, and then I make sure that the menu widget class field has been populated in the blueprints editor. I don't want to do anything else if this is null at this point. And then what I do, as long as it's not null, is I'm going to create a widget. This is a templated function, so I provide the class I'm going to create. I get my world, and this is the widget I want to create, the menu widget that I populated as a U property. And then I store that in a pointer to a U user widget. If that worked fine, so that's not a null pointer, then I take that widget that I just created and I add it to the viewport, and that will display the widget in my game. In my player controller header file, I've added a begin play override because there's stuff I want to do when the game starts, and I've also added a speak function that will print a message to the log. It's critical that I mark this as a U function and say that it's blueprint callable, because in this particular example I'm going through, we're going to call this function from a blueprint. In the implementation file for the player controller, in the begin play function, I do two things. I set input mode to game and UI to make sure that the player can interact with both the game and the user interface. There is no game in this particular example, but this is a pretty reasonable input mode to set it to. And the next line of code makes it so the mouse cursor is visible to the player. And we want that to happen because as the player navigates to interact with a single menu button in this example, they should be able to see the mouse. The speak function just logs a hi message to the log. So that's all the code we've added to set up interactions with the user interface. Now we need to go actually build that user interface. To do that, we'll go to our content folder, and I've created a folder called menus. I only have one menu that I'm going to create in this particular example, but as we build more complicated menu systems, we'll of course end up with multiple menus. My approach will be to set up a directory or a folder for each of those menus. The only contents of this folder right now is two textures that I imported for the button that I'm going to include in my menu. And I've included a texture for an unhighlighted button and a texture for a highlighted button so that the button will highlight when we hover over it and unhighlight when we move off the button. That's just a nice user interface thing to do. What I need to do is I need to right click in this folder and add a new user interface widget blueprint. And I'm going to call that menu widget since I only have one. And I'll double click it to open it up. And this is where I can lay out my widget for the menu. The only thing I'm going to add to my widget is a button, which does the typical things you'd expect from a menu button. Because I know that the size of the button image I'm going to use is 256 by 128, I'll change the size of the button. And I can use anchors to make sure that my buttons are always in the same place no matter how the resolution changes. So I'm going to pick the middle place here, and for position X I'm going to do -128. This is the upper left corner of the button, and for position Y I'll do -64. And that will center my button in the screen. The next thing I want to do is to change the appearance of the button so that it uses the textures that I showed you. So I can expand style, and for normal I can expand that and I can pick my speak menu texture button. And now that's what it will look like normally. I'll minimize that section, and for hovered, I'll add the highlighted texture and minimize that. And I will tell you from experience, this looks ugly if I only do those two things, because when I actually press the button to click it, I'll end up with a big gray box instead of an image. So I'm going to change the pressed image to also be the highlighted image, because the only way we're pressing the button is if we're already over it. And that will make it so I don't get that ugly gray box around it when I actually press. So at this point, we've got a button that will highlight when we hover over it and won't do anything if we click it. But let's compile and save. And I still need to do a little bit of setup work. So in Edit, Project Settings, under Maps and Modes, I want to use the menu buttons game mode base that we were talking about. I did turn it into a blueprint, and I turned the player controller into a blueprint as well. So we'll pick that as our default game mode. And under the selected game mode, instead of adding the player controller in code as you've seen me do many times in the past, I'll just set it up right here. I'll pick the BP menu buttons player controller as my player controller. We're still not quite done. We're almost done, but we're not quite done, because we need to still populate the property, the menu widget class, here. And we're going to pick the menu widget that I just created. So if we don't populate it here, remember that if statement that checks if it's null would say, hey, it's null, and it won't do anything. So I'll change that. I'll compile and save my game mode. And now when I run my game, we see my menu button, and it hovers when I go over it, but I can click it and nothing happens at all. To actually build in functionality for our menu, we need to go back to that menu widget, and I'll select this button, and I'll scroll all the way down here, and you'll see that there are some events that I can decide that I want to implement functionality for. And I do want to implement functionality for when this button is clicked. So I'm going to press the plus next to onClicked, and here I am in a Blueprints event graph where I can program what happens when the button is clicked. So I'll right mouse button and drag this over to give myself a little more room. The first thing I'm going to do is I'm going to get player controller. And we only have one player controller, so player index 0 is great. You've actually seen me do blueprint programming in an event graph way back when I edited the level blueprint to give us an orthographic camera. We're going to find it a little more straightforward to do our programming for menu functionality here in the Blueprints editor. The assumption is, perhaps, that the people who are developing our menu system may not be strong programmers like the programmers who are actually implementing our full game. So implementing menu functionality with blueprints is a little easier for perhaps the people who are going to actually do this. Okay, the first thing I want to do is take this player controller, just like I did when I was editing the level blueprint, except this time I want to cast to my menu buttons player controller blueprint. And the reason I want to do that is because this is a generic player controller, and this is my custom player controller that actually has a speak function. So I want to be able to call my speak function, which means I need to cast to the blueprint that implements that function. We want this to happen when the button is clicked, so I'll connect those two nodes, and I'll straighten things out a little bit, which, by the way, you can do by right-clicking and straighten connection, and you can straighten all your pin connections, and that'll take care of it for you. So right here, I'm holding a reference to a menu buttons player controller, so I can now do something. Specifically, I can search on my speak function and tell it to speak. And again, as I said, we can clean up all the pin connections like so. And that just makes the event graph look nicer. I will say that this is exactly why we needed to mark that U function as blueprint callable. We'll compile and save, and I'll pull up the output log, and when I run my game now, if I click the button, you can see that the player controller speak function gets called, and we see that logged message there. And of course, I can click it as many times as I want, and the player controller keeps speaking. So that's how we can add a very simple widget for a menu that lets us interact with the menu button using UMG and Slate. To recap, in this lecture you learned how to implement menu buttons in Unreal. You learned how we can make the menu button highlight when we hover over it, and you learned how to program the behavior of a menu button using a Blueprints event graph and C++ code. In this lecture, we'll add a simple menu system to our teddy bear destruction game. And I really do mean a simple menu system because our main menu will let the player either play the game or quit the game. Let's go take a look. The only work I've done so far in this project is to import the textures for a play button, both unhighlighted and highlighted, and a quit button, both unhighlighted and highlighted. So let's go build our main menu. I'll right click here and say I want a widget blueprint, and I'll call this menu widget, and then I'll double click it to open it up. I know I'm going to want two buttons in my main menu, so I'll drag a button over and I'm going to anchor it in the middle, and I'm going to change its size to 256 by 128 because I know what image I'm going to use for it. And since I started talking about the image, let's go ahead and add my play button, and you'll notice I have all kinds of materials here for the art that I've included. That's not what I want though. I want my textures, so I want the play menu button right here. And I'm going to also do the hovered. And remember, I also want to do the pressed so I don't get that weird box when I actually click on it. So I've set that all up, but I'm going to want to place this in a more reasonable location. So X, I will set as -128, which will center it horizontally. Let's set Y to -256, and we'll see how that spacing works out. Before I add another button, I might as well change the name of this one. So over here in details, I'll call this the play button. I'll add another button for quit and do the same sorts of things. 256 by 128. My pressed image, I'll just go do that right now. That's the highlighted button. My hovered image will also be the highlighted button. And then the normal will just be unhighlighted. I better move this around as well. So position X will be 0. Let me anchor it first. Position X will be 0. That's not right, -128. And I think I'll leave it right there. That looks pretty good as a spacing for where it should be. So I'll compile and save this. And my approach for my main menu this time will be that I'm going to add another map. So let's close out the blueprint editor, and in maps I'm going to change the name of this one to gameplay, and maybe I'll spell that properly, so let me try that again. And as you can see, if I run the game right now, I just start here and I can shoot and play my teddy bear destruction game without shooting any teddy bears. I can play my teddy bear destruction game just fine. But I want to add another map. So I'm going to right click here and I'll say level. And this new one I'll call menu. So this will be our main menu. And before I forget, I'm going to go to Edit Project Settings, Maps and Modes, and I'll change my starting map to our new menu map instead of our gameplay map. Because we might as well start on the main menu rather than jumping right into gameplay. In the level blueprint for the main menu, we'll start by making it so that the player can only interact with the user interface, and we'll show them the mouse cursor. Then we'll create the main menu widget and we'll add it to the viewport. So we'll start by getting a reference to our player controller. And we'll set input mode to UI only. And we'll connect the begin play pin here so we start executing this blueprint code. We'll also set show mouse cursor. And we'll make it true so we actually can see the mouse cursor. Then we'll create a widget. And the widget we'll create is the menu widget that we're working with. And then finally, we'll add that widget to the viewport. And we need to connect this pin as well, because this is the widget we're trying to add to the viewport. I'll compile and save. And now when we run, you'll see I can hover over each of the buttons, but clicking them doesn't do anything. I will also point out that I'm still displaying the score over here, which is not really something I should be doing in my main menu. We'll fix that before we're done. Okay, let's go back to the menu widget and I'll pick play. And I'll scroll all the way down here because I'm going to do something when I click play. I'll also tell you that if we select graph, I can pick the play button over here and get at those events easily over here as well. And I see that I haven't renamed button 1, so let's come back to the designer, select quit, and call this the quit button. And while we're here, I'll just come down and add an onClicked for the quit button. And for the play button, I'll add an onClicked for the play button as well. And I'm going to swap these two just because they're in these locations on the actual menu. When the player clicks the play button, we want to make it so the player can interact with the game. We want to remove the mouse cursor. We want to open the gameplay level. And we want to remove this widget from its parent, to remove it from the viewport. We'll get a reference to the player controller. We'll set our input mode to game only and hook that up with begin play. We'll set show mouse cursor. And this time we'll set that to false because we don't want the cursor to be displayed in the gameplay level. We'll open the new level by name. We could do it by object reference, but we want to do it by name, and we know the name of the level we want to open. It's the gameplay level with 1Y. And finally, we want to remove the widget from its parent. And the widget we want to remove is self, because we're trying to remove the main menu widget. The quit button is much easier to program. All we need to do is execute, a console command, and I happen to know what command we want to execute, that command is quit. So I'll compile and save, and I'll run the game. I'll show you quit first. There, we quit the game. And if I click the play button instead, then here I am in my level, and I can drive around and shoot teddy bears and so on. So the last thing that we should fix for this particular example is, as I said, when we run the game, we're showing the HUD display of our score in the main menu, and we don't want to do that. You'll notice that if I look at the world settings for this map, you can see here that my game mode is set to none, but in project settings, in maps and modes, we've said we want to use a default game mode of the Teddy Bear Destruct game mode base, which, by the way, has the HUD and displays the HUD. So over here, when we say we don't want to override the default, it uses the blueprint for the game mode that we've been using all along, and that displays the HUD. Instead, let's pick a game mode base here, because we can have different game modes for each level. While setting our default game mode in our project settings is useful if we're going to use that game mode across lots of different maps, it's problematic if we don't actually want that game mode to be active in a particular map. So you can see our gameplay map doesn't override the default game mode, but that's good. We set it to be the game mode we wanted for gameplay. In menu though, we need to override it so it doesn't display the HUD. So I've picked game mode base here, and it just gives us a default pawn and a player controller and so on. And as you can see, when I run the game now, on the main menu, I don't have the HUD displayed because I'm not using the custom game mode that I wrote that displays a HUD. When I click play though, I get my HUD displayed because it's moved to use the default game mode because I didn't override the default game mode for this particular map. To recap, in this lecture we learned how to add a simple menu system to our Teddy Bear Destruction game. In this lecture, we'll add a pause menu to our Teddy Bear Destruction game. And this will be great because once the player starts actually playing the game, they can pause the game and either resume it or quit back to the main menu. Now that we have a couple of menus, I've done some restructuring of my folder structure for my project. In the menus folder, I now have a main menu folder that holds my main menu widget. I renamed that to main menu, and my play button textures. I have a pause menu folder that has a new pause menu widget and my resume button textures. And I have a common folder that holds quit button textures because I use those textures in both my main menu and my pause menu. I've also changed the name of my menu map to main menu because it's the main menu. Let's go take a look at that new pause menu widget. Here's how I've set up the actual widget, and you'll notice this won't take up the whole screen. I did want a semi-translucent border for the pause menu so that it appears on top of the game that's paused and we can still see the game underneath it. That means I had to do things differently from what I've done so far. I needed to add a border that I could size appropriately and color with that semi-translucent color. Unfortunately, borders can only have one child, so I couldn't add both buttons inside this border. So instead, I needed to add a vertical box, and I placed the two buttons inside that vertical box. So border can only have one child, so I couldn't place those buttons like I did in the main menu, Instead, I put them inside that vertical box and then just put both buttons inside there. And both those buttons are set up to highlight when we hover over them and when we press them. And I've set up an on-clicked event for the resume button. And I've set up an on-clicked event for the quit button. So let's go take a look at those in the event graph. This is a much more complicated event graph than you've seen in the previous work I've done with menus, but it is straightforward once I walk through how it works. So what will happen is the player will pause the game and they'll get the pause menu, and then they can choose to either resume the game or quit back to the main menu. So you should think of this as the game is paused, we have the pause menu displayed, and now we're going to click the resume button. What should happen? So I zoomed out to show you the entire event graph, and now I'm going to zoom in so we can focus on what we're doing one step at a time. When the resume button is clicked, we get a reference to the player controller, and we say, with this blue line from the player controller up here to this node, we set input mode to game only. So the player can now only interact with the game. I can only move the launcher up and down and shoot. I can't click on any user interface buttons at this point. And that's okay. By the time I finish processing this resume button on-clicked event, the pause menu widget will be removed from the viewport anyway. But we want to make sure that when we're done with the pause menu, that the player is only interacting with the game. So that's what this first node does with the player controller. We also want to set show mouse cursor to false. We don't want the mouse cursor shown anymore because now we're just resuming the game. We're taking away the pause menu. We don't want to show the mouse cursor anymore. We just want to have the player playing the game. So we've set the input mode to game only. We've made the mouse cursor disappear. And we follow this link, and now we're going to remove from parent self, so that takes the pause menu out of the viewport. And we say we don't want the game to be paused anymore. And that makes sense, right? The player has said they want to resume the game, so we should unpause the game so the player can keep playing the game. If the player clicks the quit button, we're going to set the input mode to user interface only because we're about to return back to the main menu. So the player isn't doing any gameplay anymore. They're just going to interact with the main menu. And this is more important if we were going to have gameplay displayed under the main menu or something, because this would keep the player from moving their launcher around and shooting while the main menu is displayed. It doesn't really matter here because when we get back to the main menu level, the player doesn't have any gameplay to do. The only thing they'll have to do is interact with the main menu. We show the mouse cursor because we're getting ready to go back to the main menu, and the player should have the mouse cursor available to them as they interact with the main menu. We open the main menu by name, and we've seen that node before. When we clicked the play button from the main menu, we opened our gameplay level by name. So this is going the opposite way. We're going from our gameplay level back to our main menu level. And then we still want to remove the pause menu from the viewport and unpause the game. And we want to unpause the game here because we don't want the player to go back to the main menu and come back into the game and have it still paused. So we want to make sure when we close the pause menu and go to the main menu level that the game is not paused. I'll zoom out again. So that's the full behavior of the pause menu widget. But how do we actually get the game to pause and display the pause menu in the first place? There are a couple of ways we can do that. We can code it using blueprints in the player controller, or we can code it in C++ in the player controller. And I have obviously decided to code it in C++ in the player controller. So let's go take a look at the player controller class. Here in the header file, I've added a #include for user widget because I've added a property that I can populate in the blueprints editor for the launcher player controller, and I'm going to populate this property with the pause menu widget. So you should think of this as the player holds an instance of the pause menu that it can make appear in response to player input. Specifically, I've set it up so that the left control key brings up the pause menu. Just in the interest of full disclosure, I originally tried to set up the escape key as my action mapping for pausing the game because that felt intuitive to me. But of course, every time I pressed the escape key, the Unreal editor stopped playing my game, because that's how you stop playing a game in the editor, is hitting the escape key. So I decided that I would use a different key, and I chose to use the left control key. The other thing that I added to the header file is I added a pause game function. Over in the implementation file, I added an additional key binding. So over in project settings in the input section, I added an action mapping for the left control key to an action called pause game. And I'm binding my action here so that when that action occurs, I will call the pause game function here. And the outer parts of these if statements should look familiar to you from when we were talking about menu buttons a couple of lectures ago. So first I make sure the property has been populated, and if it has been populated, I create a widget of that property. And as long as that creation worked okay, I add the widget to the viewport. I'm also going to say, at this point, the player can only interact with the user interface. So here I'm forcing the player to only interact with the pause menu. I show the player the cursor so that they can see if they're near the resume or quit buttons. And finally, I set pause to true. And this actually pauses the game so that the game doesn't keep running under the pause menu. The game is actually paused under the pause menu. Back in the editor, I'll show you that in input, that pause game mapping I was telling you about is the left control key. And I'll also show you that in my blueprint for the launcher player controller, I populated that property with the pause menu widget. So now when I play my game, here I am, I can play, I can shoot, all those great things. And if I hit left control, you can see that the pause menu is displayed on the screen. The game is paused. This teddy bear isn't moving anymore. I can't move my launcher. You can't tell, but I was trying to move or shoot my launcher and I can't. If I resume, I have gameplay control back again and I can keep shooting and so on. If I pause again and quit to the main menu, I can come back into the game. It starts over. It's a new game when I hit the play button again, and everything works fine. I will tell you that I did have to make one modification to my main menu widget, specifically my programming for the play button. So I had to add this little bit of blueprint code at the very end, because if the player is playing the game, brings up the pause menu, which, remember, makes it so they can only interact with the user interface, and then clicks the quit button on the pause menu, now they're back in the main menu and it's great. They should still be only interacting with the user interface. But if they hit play again, I couldn't play at all because my input mode was only for user interface. So this is making sure that when I enter the game from the main menu, I can actually play the game and not just watch things happen and not be able to shoot teddy bears, which was horribly sad for me not to be able to shoot teddy bears. We didn't see this problem in the previous lecture because we never were in the game, change the mode, come back to the main menu and go back into the game again. So that's why we didn't see this problem last time. But now that we have an even more robust menu system, I had to apply this one fix to the main menu. To recap, in this lecture, we implemented a pause menu in our teddy bear destruction game, and we also saw that the blueprints event graph for processing our menu buttons in a pause menu was much more complicated than what we've seen previously for our main menu. This is a different kind of lesson where we'll explore a slightly larger game that uses lots of the ideas that you've learned in this course. And it obviously uses lots of ideas you've learned in previous courses in the specialization as well. I'm only providing the Unreal project in the lecture resources for this lecture, so if you want to download that code, you should do it from this lecture. Let's go take a look at the game. So here's the game. We start at the main menu, and we can see what our highest score has been playing this game, and we can quit out of that high score menu. We can quit from the game. We can play the game, and when we select play, we can play an easy, medium, or hard game. And I'll pick an easy game, and then I'll stop talking so you can see how the game works with all the sound effects. And there you go. We'll go over lots of the implementation details of how the game is built over the course of this module. What will you explore in this lesson? We'll look at the event manager for the game. We'll look at the menus for the game. We'll see how basic gameplay is implemented, and then we'll see how the full gameplay is implemented. We'll look at how to include sound effects in our game, and we'll look at how we can use configuration data in our game. In this lecture, we'll see how we use the event manager in our Feed the Teddies game. Here are our delegate declarations, and we're going to have two delegates for our events in this game. We have a points added event, and we have a game over event. In our event manager code, we have the typical structure for invokers and listeners for both those events. We don't actually need an invoker interface like we did in the teddy bear destruction game because each of these events is only invoked by one class. So the fries actor is the only class that invokes the points added event, and the burger pawn class is the only class that invokes the game over event. So we don't have to build interfaces and have these classes implement those interfaces. We can just directly use the classes. Of course, the code is longer with multiple events, so I can add the points added event invoker and remove it, add the points added event listener and remove it, add the game over event invoker and remove it, and add the game over event listener and remove it. So I need to provide the capability to both add and remove invokers and listeners for every event I have. And in the implementation file, I implement all that functionality as usual, as you saw when I did the event manager for teddy bear destruction. That means that the French fries actor needs to have a points added event included in it, and we need to be able to get access to that points added event, and of course we'll have the French fries remove themselves as an invoker of the event when they're removed from the level, which happens when they get destroyed or when they actually leave the level. And French fries add themselves as an invoker of this event here in the begin play function, just as we've seen before. The burger pawn is the invoker of the game over event. So again, it's holding a game over event here. It exposes a function so we can get a reference to that game over event, and it also removes itself as an invoker of the event when it's removed from the level. And it adds itself as an invoker of that event in its begin play function. So the way we use the event manager in this game is the same as the way we used it when we talked about refactoring the teddy bear destruction game. It's just that we have two events this time. So the event manager code is a little more complicated, but we have simplified some of the code because we don't need to be implementing interfaces. We just have one class that invokes each of those events. To recap, in this lecture we explored how we use the event manager in our Feed the Teddies game. We really have one more step to get our event manager to be commercial quality. What we would probably do is define an interface for each kind of event that gets invoked. For example, an event with one integer parameter, and then the event manager can just use those interfaces instead of hard-coded object or class names like the fries actor or the burger pawn. If we have multiple events that have the same characteristics, for example, one integer parameter, we'd also want to add an enum or an enumeration that had each of the event names as values, and then when we registered or added or removed invokers or listeners to the event manager, we'd also provide a parameter or an argument when we call the function that says which event we're adding to or removing from. In this lecture, we'll explore the menu system in our Feed the Teddies game. We have 5 different menus in this game. This common folder is just the quit menu button textures, but we also have a difficulty menu, a game over widget that I'm calling a menu, a high score menu, the main menu, and the pause menu. We won't bother talking about the pause menu. It's implemented just like I showed you when I showed you how to implement a pause menu. Our main menu widget is also very similar to what we've seen before. We have the play button that leads us to the difficulty menu. We have the high score button that leads us to the high score menu. And we have the quit button that quits the game. Just to show you that the play button is slightly different from what we've looked at before, if we look at the event graph for the play button, you can see when the play button is clicked, instead of setting the input mode for the player controller to gameplay and moving to the gameplay level, we set it to be UI only, and that's what it is right now also, but we're going to just do that to be complete with the things we're doing as we move along on this button click. And we set show mouse cursor to true, and then we move to the difficulty menu, and then we remove this widget from the parent. So we'll move along to the difficulty menu level from here, setting up the player controller to make sure we're still interacting with the user interface. We do similar things with the high score menu button, except we go to the high score menu, and then the quit button is as we've seen before. Let's look at the high score menu next. So this one is a little more complicated. If we look at the event graph, we'll see that not only do we have processing that we do when the button is clicked, but I'm actually doing some processing up here in the construct event. So when we actually build this widget, there's stuff I want to do. And the stuff I want to do is I want to get access to the high score that's saved in our save game object and store it into a variable right here in my blueprint. I've declared a saved high score variable over here, and the way you make new variables is you click plus, and then you click here to pick a data type, including object types and so on, and you give it a name. And now I'm going to just delete that because I don't actually want that variable, but that's how I created that variable. So here when the widget gets constructed, I load the game from the slot, which we've seen me do in C++ code back in the Save Game lecture, but I'm doing it here in the blueprint instead. I do a typecast to the Save Game class that I wrote, and then I access the high score from that class and set the saved high score variable over here to that value. So now I've saved the value of the current high score in my saved high score variable. And we'll see how we actually use that in a moment. When we click the button, we do the typical stuff. We're going to click the quit button to go back to the main menu, and that's all as you've seen before. Back in the designer though, you'll see that I have a vertical box here that has the high score label and then something that I called value. And obviously when we go to this menu, it doesn't show value, it shows the current high score. And how does that actually work? The way that actually works is over here on the right, what I did was right here, I bound that text to the saved high score, that variable that I showed you. And by binding this text box to that variable, I make the text box display the value of that variable. In my difficulty menu, as you saw, I have easy, medium, and hard buttons. Let's take a look at the graph. The way this works is I have a variable that I declared called difficulty. And if the user has clicked the easy button, I set that variable to 0. If they've clicked the medium button, I set it to 1. And if they've clicked the hard button, I set it to 2. So at this point, the difficulty variable holds 0 for easy, 1 for medium, 2 for hard. Then I load my save game and I typecast it. And then I set the difficulty property for my save game object to that variable that I set to 0, 1, or 2 for the difficulty, and then I save the game to the slot. So I'm using my save game slot to store what difficulty the player picked for the game they're about to play. Then I set the player controller to use game only because we're getting ready to go to gameplay. I don't show the mouse cursor. We go to gameplay and I remove from the parent. So this is a good way for me to save information about the difficulty of the game that we're about to play. And when we start playing the game, we'll retrieve that difficulty information so that we can make the game behave in the appropriate way based on the selected difficulty. The last menu that we'll look at is my Game Over menu, which is really a widget that I'll display on top of the game. So I didn't show you this when I demoed the game, but when the game ends, you get this Game Over menu, and it tells you your score, and it tells you the current high score, which may be higher than your score or the same as your score if you just got a new score, and then a quit button that will let you return to the main menu. In our graph, I've declared two variables here, a saved player score and a saved high score, and when the widget is constructed, I get the game mode, because in this game the game mode is the class that keeps track of the player score. So I get the game mode and then I cast it to my feed the Teddies game mode base, and I access the score property and I set that variable saved player score to the score. So now saved player score has gone off to game mode. It's grabbed the score that the game mode stores and it stored it in this variable saved player score. I load the game from the slot, I cast it to the save game, and then I get the high score and I set my saved high score variable to high score. When I click the quit button, I go to UI only for the player controller, I show the cursor, I go to the main menu, I remove the widget from the parent, and I unpause the game. Because when I display the Game Over widget, I'm actually pausing the game when I do that. So I want to unpause the game here. Back in the designer, you'll notice the value of the player score is bound to saved player score, and the value of the high score is bound to saved high score. And just to show you how that game over widget gets displayed, here in my game mode base, I have an end game function that gets called when the game is over. The first thing I do is I try to load from my save game slot, and I've actually included code in the main menu actor to make sure I have a saved game in this save game slot, but we'll be careful anyway. We'll make sure we actually were able to load a saved game, and if we were, then we save the high score property of that saved game instance into my high score variable that I've initialized up here. And of course, I can initialize it like this as well. So on line 110, high score is whatever was saved in the save game instance, or 0 if for some unexpected reason I was unable to load the saved game. And now I check for a new high score. And if I have a new high score, again, being careful here, if I do have a new high score, then I set the property of my saved game to that new high score, and then I save the game to the slot. So now that I've done this processing, the saved game in the slot holds the current high score, even if the current high score is one I just scored on this game. Making sure my game over widget class isn't a null pointer, I have a U property for this widget that I populate in the blueprints editor. I create the widget, make sure it created fine, add it to the viewport, get my player controller, make sure I got my player controller, and if I did, I set the input mode to UI only, so the player is not playing the game anymore. They're only able to interact with this widget, and I show them the mouse cursor and I pause the game. So that's how we actually get the game over widget displayed when the game ends. To recap, in this lecture we explored how to implement a more complicated menu system in our game, including a high score menu, a difficulty menu, and a game over widget that I also called a menu. In this lecture, we'll look at how the basic gameplay is implemented in our game, and we'll also see how we can build a nicer HUD using Slate widgets. We'll start with a reminder of how the basic gameplay works, and then we'll go look at the code that implements it. I have turned off the sound effects so that I can talk about stuff without talking over the sounds of the game. So remember, we pick a game difficulty, and then we go to the game. As you can see on the top, I've implemented a HUD, and I've implemented that HUD using Slate widgets instead of just using the canvas draw text that we used way back when. We have a countdown timer on the upper left. I have a health bar for my burger in the middle, and I have my score in the upper right. Let me see if I can score a little bit here. There we go. I've got some score as well. And as you can see, the game ended when the timer ran out. So the game is over. I scored 20. The high score is 40. That's what my saved game high score is. And then I can quit from here back to the main menu. The other way the game can end is if I run out of health. So there's two ways the game ends. Either the timer runs out or I run out of health. We'll look at the burger pawn first because that's the player's avatar. On begin play, we do the usual stuff, including adding ourselves to the event manager as a game over event invoker, as we saw when we talked about the event manager. I'm also using configuration data, and we'll talk about that in a lecture later in the module. On tick, I move using the pending movement input, just like we've seen ever since we started using player controllers and pawns. When the burger overlaps with something, if the burger overlaps with a teddy bear, we're going to lose health So I use whatever damage the bear inflicts from configuration data and reduce health by that amount. We'll see why I use health percent in a moment. I destroy the teddy bear I just ran into, and I check to see if the game is over. Because if I've just run out of health, the game is over. If I run into a teddy bear projectile, I lose health. I calculate the health percent, I destroy the teddy bear projectile, and I check to see if the game is over. And we'll see why I'm using that health percent when we actually look at the implementation of the HUD. And finally, checking if the game is over. If health is less than or equal to 0, I broadcast that game over event. And my game mode is listening for that event, so it will know to end the game if this event is broadcast. The burger can, of course, shoot French fries, so here's the fries actor. And again, it does the usual stuff, adding itself to the event manager as a points added event invoker, and using configuration data, and getting itself moving using the static mesh component. We make sure we destroy the fries if they go past the top of the screen. French fries are always shot up. When the French fries overlap with something, if we shoot a teddy bear, that's how we actually score points in the game. So we broadcast the points added event, and we destroy the teddy bear, and we destroy the French fries. If the French fries run into other French fries or a teddy bear projectile, we just destroy the other actor and this actor. Both of them are destroyed on that particular collision. If the French fries are being removed from the level, remember, we want to remove ourselves as an invoker, and this happens all the time, right? French fries are leaving the screen all the time. So we want to make sure we remove ourselves from the event manager as an invoker of the points added event. And that's it for the French fries. Our teddy bear actor uses configuration data, gets itself moving with a random force on begin play, checks to see if it's off screen. So if it's off screen, we're going to wrap the teddy bear. So if it goes out on the right hand side, it comes back in from the left hand side. And this is straightforward code that wraps horizontally and vertically. Notice I don't use an else if here, because if I hit a corner, I need to wrap both horizontally and vertically on the same frame. So this isn't an else if here for the wrapping. I check for wrapping horizontally and I check for wrapping vertically, and I might end up doing both on a particular frame. And wrapping itself is a really easy thing to do. If I'm outside on the left, that means that all I have to do is negate my Y, and if I'm outside on the right, all I have to do is negate my Y, and I do similar stuff with Z for top and bottom. If a teddy bear overlaps with a teddy bear projectile, we destroy the teddy bear projectile. We don't kill the teddy bear, but we kill the teddy bear projectile we just ran into. And this is a private utility function that just tells whether or not I'm off screen. Shooting a projectile is standard stuff. I spawn the projectile and then I start the shoot timer again. And a shoot timer makes the teddy bear shoot at random intervals. So I get this random range between the min shot delay and the max shot delay, again using configuration data. And then I set my timer, and when my timer finishes, it calls the shoot projectile function. The last class we'll look at before we go look at the implementation of the HUD is my game mode. So in the constructor, I set the pawn and player controller like we've been doing many times. I add myself to the event manager as a listener for the two events that can be invoked or broadcast in the game. I add a HUD, so I have a property called HUD widget class that I populate in the blueprints editor, and as long as I've remembered to do that, I create the HUD widget, and as long as that worked fine, I add the HUD to the viewport. I also start a 1-second timer. So this is my countdown timer. The configuration data tells me how long each game should last. And so I extract that from the configuration data and set that to my seconds left here as we start playing. So this is currently set to 30. So I set seconds left to 30 when the game starts. And I start a 1-second timer. This is just adding points to the score. This is the delegate that I need when I add myself as a listener. When the game ends, we've already looked at this end game function in game mode when we talked about how we display the game over widget. And this is more stuff for dealing with the event handler. When we're removed from the level, I remove myself as a listener for both those events. And here, starting that 1-second timer, this is really straightforward. We've used timers before. This time, this is not some random amount. This is 1 second exactly. And when the timer finishes, we'll call change seconds left, which reduces seconds left by 1, and then checks to see if time is up. And if time is up, we end the game, but if time isn't up, we start that 1-second timer again. So that's all the C++ code implementing the gameplay. Let's go look at the implementation of the HUD. So here's my HUD widget. As you can see, I have some text labels that don't do anything dynamic, but I do have some elements in the HUD that should change as the game changes. So we have the seconds that are left, we have the health bar that should change, and we have the score. Seconds left and score are text boxes, but the health bar is actually a progress bar. So I used this progress bar for my health bar. If we go to our event graph, you can see when I construct this widget, I do a number of different things. First, I get the player pawn, and I cast to my burger pawn, and I set a burger pawn variable that I've declared over here on the left to be that burger pawn. Then I get my game mode and cast to my feed the Teddies game mode base, and I set this variable over here, the feed the Teddies game mode base variable that I've declared, to that object. So I have a couple of variables that I'm storing when I construct this widget. A variable that holds a reference to the burger pawn, and a variable that holds a reference to the game mode base. If I look at how I bind time left, you can see that I've bound that text block to the seconds left property in the game mode base. We just looked at the code that changes seconds left as the timer counts down, and this will display how many seconds are left. For score, I've done it slightly differently. So the way I actually built this is I'm not binding it to a specific variable. I created a binding, and so if we look at that binding, I take my game mode base, I access its score property, and then I set that score text block to be that value. Now I will say I could have bound this to the game mode base score property as well. That would also have worked fine. I just wanted to show you two different ways that we can actually set something. We can bind to a specific property, or we can write a custom function that actually binds a value to a particular text block. I wanted to show you both ways to do that. Finally, my health bar. I've bound to my burger pawn variable's health percent property. And this is why I needed a health percent property in addition to my health property that I have in my burger pawn, because progress bars want us to have our bound value to have a range from 0 to 1. So I just convert my health that will be from 0 to 100 to be a percentage, which is from 0 to 1, and then I can just directly bind it to this progress bar. So in addition to looking at our basic gameplay, you get to see how we can implement a more robust HUD using slate widgets instead of just drawing text to a canvas. To recap, in this lecture we saw how we used a number of different gameplay classes to implement our basic gameplay, and we also learned how we can implement a HUD using Slate widgets. In this lecture, we'll explore how we can implement homing behavior using an actor component. We'll start by watching the homing behavior for both the teddy bears and the teddy bear projectiles. Again, I have sound turned off so I can talk about it, and I'll play easy. And as you can see, periodically the teddy bears will start trying to chase the burger instead of just moving randomly. And the projectiles also will home towards us. You don't see that much when the teddy bears are low on the screen, but if they're higher on the screen, and particularly on higher difficulties, the teddy bear projectiles actually come over toward the teddy bear, as you just saw there. It turns out that even though we didn't need an interface for our event manager, we actually do need an interface for homing actors. So any actor that's going to have homing behavior needs to implement this homing actor interface. Basically, the actors need to provide a get static mesh function, a get impulse force function, and a get homing delay function. The get static mesh function is so that the homing component that we're going to look at soon can push the static mesh in a new direction. The get impulse force function is so that when the homing component does that, it applies the same magnitude of impulse force that was originally applied to get our homing object moving in the first place, and that makes it so that it doesn't change speed. Our homing object won't change speed, it will just change direction. And we need to get the homing delay for the actor because we don't implement this homing behavior on every tick. We only periodically implement the homing behavior. So on harder difficulties, the homing delay is shorter. So the homing component makes the actor it's attached to home in more regularly toward the burger. And that's how we can affect the difficulty, because actors that home more regularly are going to follow the burger more closely. So any actor that's going to have homing behavior needs to implement this interface. We haven't actually talked about actor components since way back when we talked about manual timers in the second course in the specialization. But this is a great place for an actor component because we have multiple actors that we want to exhibit the same behavior. And it's much better to just implement that behavior in an actor component and then attach this actor component to any actor we want to have that behavior. We're saving a pointer to the burger pawn because that will be our target for homing. We're going to save all the information from the owner so that we don't have to keep looking that up. And we'll use a homing timer that will use that homing delay to decide when we should actually home in on something. We have a function that will move the actor that this component is attached to toward the target. And then we have a function that will figure out what force vector we should apply to do that. In our implementation file for the homing actor component, on begin play, we find the burger so that we can save it as a target so we don't have to look for that burger every time we're going to move toward it. And then we save that owner info. As we've seen before, we can have a pointer to an interface, which we do here, because we know that the teddy bear actor and the teddy bear projectile actor will be using homing behavior, but both of those classes will implement this interface, so we just use a pointer to the interface after we get whoever owns us. So we'll get attached to an actor, and then we'll get that actor, and then we'll cast that actor to the interface so that we can access these three functions that we said any class that implements the interface has to implement. And then we start the homing timer. And when we do that, we set it to the homing delay and we say when the timer finishes, call the move toward target function. And then the move toward target function does what we've seen in the Ted the Collector game, where we stop moving and then we call the get force vector function that we'll look at in a moment, and we pass in the location of the actor that owns this component and the location of the target, the burger, and then we add impulse to the static mesh component of our owner to move our owner in the direction of the burger. And then we start the timer again because we're going to home in again after the homing delay. And this get force vector is exactly the function that you saw me write when we talked about Ted the Collector. In our teddy bear actor, we need a couple of extra pound includes. We say that we're implementing that interface. It will be more efficient for us to save a couple values here, especially impulse force that we'll talk about soon. And we have a pointer to the homing actor component that we're going to attach to this teddy bear actor. In the implementation file for the teddy bear actor, on begin play, we save the static mesh component into a field so we don't have to look it up again to implement our get static mesh function. And here's why we really need an impulse force field here, because we're generating a random impulse force and we need to save that random impulse force. We can't just generate a new random impulse force when the homing component wants to know what impulse force to use. We need to use the one we used originally when we started the teddy bear actor moving. This is code that you saw back when we did manual timers, but here we're seeing it again. So we create a new homing component object, and we say we're going to be the owner of that homing component, and we put it into our homing actor component field. We do our assert to make sure that worked properly, and then we register our component. And here are our implementations of the functions that are required by the interface. Get static mesh, we just return our static mesh component field. Get impulse force, we return our impulse force field. And get homing delay, we actually use our configuration data to get the bear homing delay because we're in the teddy bear actor here. The teddy bear projectile works exactly the same way, except that in our implementation of the get homing delay function, we get the bear projectile homing delay from our configuration data. To recap, in this lecture you saw how we could make teddy bears and teddy bear projectiles exhibit homing behavior. You saw how cool actor components are because we could give the same behavior to multiple objects. And even though I didn't talk about it as I talked about the code, using an actor component is a much better choice than using inheritance in this particular case because the homing behavior is the only behavior that's shared by the teddy bear and the teddy bear projectiles. In this lecture, we'll explore the implementation of our sound effects in our Feed the Teddies game. As you can see, we have 6 different cues that we're going to play as part of the game. We have a burger damage cue, a burger death cue, a burger shot cue, a button click for our menu buttons, a teddy death cue, and a teddy shot cue. So we'll go look at the cues that are played by the burger and the teddy bears first, and then we'll take a look at how we do button clicks in our menus. In our burger pawn, when we take damage from a teddy bear, we play our 2D sound in the usual way. We learned this way back when we learned how to play sound effects. And we're playing our burger damage cue, which I have set as a property that I've populated in the blueprints editor. I play that same sound when I take damage from a teddy bear projectile. When I shoot French fries, I play the burger shot cue. And when I discover that the game is over because I've run out of health, I play the burger death cue. And here in the burger pawn header file, here's where I have those U properties for populating the burger damage cue, burger death cue, and burger shot cue in the blueprints editor. My teddy bear actor plays two different cues, the teddy shot cue when it shoots a teddy bear projectile, and the teddy death cue when the teddy bear dies. So I have these U properties here, so I can populate those in the blueprints editor. And then in the implementation file, when I die because I have a collision with a burger or French fries, I play the teddy death cue. And I will say, I did some refactoring when I talked about basic gameplay and collisions between fries and teddy bears. I just destroyed the teddy bear over there in the French fries, and I refactored a little bit so that I could have the teddy bear play its own death sound on that overlap. So I changed how collisions between French fries and teddy bears work compared to what I showed you previously. So now the way it works is if French fries collide with a teddy bear actor, the French fries destroy themselves and broadcast the add points event, but they don't destroy the teddy bear. The teddy bear detects that overlap here, so it can play its own sound effect. We certainly could have played the teddy death cue over in the French fries, but that's not good object-oriented design. We should have the teddy bear play its own death cue. The other cue that the teddy bear plays is when it shoots a teddy bear projectile, it plays the teddy shot cue. So those are the 5 sound effects that are played from within C++ code. Let's go take a look at the menu buttons. And we'll just look at playing the sound for the buttons in the main menu because it works exactly the same way for every menu button in my menu system. We'll look at the event graph, and you'll see that for each of the menu buttons, I've responded to the onPressed event. And onPressed, for each of these menu buttons, I just play the 2D sound, the button click cue. You might think it would have been easier to just go to the onClicked events for all the menu buttons and play the sound here, and I will confess that I tried that. But I couldn't get it to work. It would never play the sound on a button click. So I play the sound when the player presses the button, and then I do the full click processing in response to the onClicked event, which is of course the player pressing and then releasing the button. I also could have played the sound on released instead of on pressed, but it felt more responsive to the player to actually play the sound on pressed. So that's how I got all of my menu buttons to play the button click sound. For each of the menu buttons in my menus, I add a response to the on pressed event and I play the button click cue. To recap, in this lecture we explored how to include both gameplay and menu button sound effects in our game. In this lecture, we'll look at the implementation of the configuration data in our game. As you probably expected, we're using an Unreal data table to import our game configuration data, except this time we have 34 different configuration data values. So we have way more than we've used in the past when we were doing configuration data. Using our standard technique, we defined a struct to define the structure of that data. So we have a whole bunch of fields here, and then we have a whole bunch of U properties for each of those 34 different fields. We're also using a configuration data actor. We saved the difficulty because there are a number of different functions that return difficulty-specific values, and we save a pointer to our configuration data row, just as you've seen me do in the past. And of course, I populate a U property with my configuration data table, and then I have the standard stuff, and then I have a whole bunch of getters. In the implementation file for my configuration data actor, on begin play, I open the save game, because remember, the save game is where I saved the difficulty from the difficulty menu, and I save that here, and then I retrieve that configuration data row and save that into my field. And many of these getters just return the value from the configuration data row, but some of them are difficulty specific. Starting with min spawn delay for spawning teddy bears, depending on what the difficulty is, I may be using the easy min spawn delay, the medium min spawn delay, or the hard min spawn delay. And I always include a default, so just in case the difficulty is something weird, I just say it's an easy game. So a number of my getters return difficulty specific information. And that's all hidden from whoever is calling the getMinSpawnDelay function. They don't have to care about what difficulty the game is. The configuration data actor knows what difficulty the game is and returns the appropriate value based on the game difficulty and the data that's stored in the configuration data row. So we have implementations for all of the getters that are providing access to the configuration data for the game. I'll just show you one example of a class using the configuration data. The burger pawn on begin play gets and saves a pointer to the configuration data object, and then, for example, if we're going to move, we set a move amount per second variable to whatever the configuration data actor says is the burger move amount per second. And I only used a variable here because I know I use it here and here, and I didn't want to have to call that function twice. So this is one example of an actor using the configuration data, but the actors that need to use the configuration data, I'll use the same pattern of getting and saving a pointer to the configuration data actor and then accessing the appropriate functions to use the configuration data in that configuration data actor rather than using constants. To recap, in this lecture we saw how we can use a configuration data actor to provide configuration data to the other objects in the game, and we also saw that as our games get more complicated, we may end up with lots of configuration data values. This is it! You made it to the end. Not just the end of this course, but the end of the specialization as well. You should take a little time to reflect on what you could do before you started the specialization and what you can do now, because hopefully you can do lots more in terms of game development than you could do when you started. Thank you very much for joining me in all these courses. I had a blast doing them, and I hope you learned a lot and had fun along the way as well. Now you can go off and build even more great games. Cheers.